It is 9:17 in the morning in Chelyabinsk, a working city in the Russian Urals, and the sky is doing something the sky is not supposed to do. A point of light appears low in the east, white and cold, and in under 5 seconds it swells brighter than the sun. People stop on the street and turn to look. That is the mistake. Whatever it is already moving 30 times faster than a rifle bullet, and it has not made a single sound yet. The object was a rock about 19 meters across, roughly the size of a 6-story building, and it had been falling toward that exact morning for millions of years. Nobody saw it coming. Not a telescope, not a satellite, not one of the systems we like to imagine are quietly watching the sky on our behalf. It came out of the direction of the sun, the one blind spot our instruments cannot cover, and it arrived with the casual timing of a thing that does not know we exist. At an altitude of about 23 kilometers, the rock could no longer take the punishment. The air in front of it had compressed into a solid wall, and it detonated. The blast let go the energy of roughly 30 Hiroshima bombs. A flash so bright it threw moving shadows across the snow and scorched the skin of people standing at their windows. And still, for a few more seconds, the city heard nothing at all. Light is fast. Sound takes its time. Then the sound arrived, and behind it the pressure wave. It blew in something like 100,000 square meters of glass across the city. That is the detail that stays with me. Almost everyone hurt that day, around 1,500 people, was cut by their own windows. They had heard the bang, run to the glass to look, and the shock wave reached them while they stood there admiring the light. The sky did not even have to touch the ground to draw blood. This is the part that should keep you up. Chelyabinsk was small. 19 meters is nothing, a pebble by the standards of the things that cross our orbit every year. It injured more than 1,000 people and frightened 1 million, and we received no warning whatsoever. Which leaves the obvious question, the one nobody in charge enjoys answering out loud. What happens when the rock is bigger, and it still comes at us out of the glare of the sun? For an answer, go back to the morning of June the 30th, 1908, to a place so remote it took scientists 19 years to reach it. Deep in the Siberian forest, over the Tunguska River, something exploded in the sky with a force of perhaps 10 to 15 megatons. That is 1,000 times Chelyabinsk, a full 1,000, and there is no crater. Nothing ever hit the ground. It never needed to. The blast flattened an estimated 80 million trees across more than 2,000 square kilometers, laying them down in a vast radial fan, every trunk pointing away from a single empty patch of sky. A man sitting on his porch at a trading post some 60 kilometers away was thrown from his chair, and he said afterward that the heat was so fierce he felt his shirt was about to catch fire. Had that object arrived a few hours later, the turning earth would have set it over Central Europe. It would have erased the capital city. When the first real expedition finally reached the site, led by a mineralogist named Leonid Kulik in 1927, he expected a giant impact pit. He found none, just a graveyard of scorched trunks stretching to the horizon. And at the very center, a strange stand of trees left upright and standing, stripped of every branch, like a forest of telegraph poles. The explosion had come from directly above them and pinned them where they stood. The forest had been slapped flat by something that was never there. Astronomers have a bloodless phrase for the next size up. They call them city killers, rocks 140 meters and larger. And that name is not decoration, it is a job description. An object that size does not burst harmlessly in the high air. It reaches the ground, or close to it, and it releases the energy of hundreds of megatons. The truly enormous ones, the civilization enders, we have mostly found. It is the middleweight class, the merely city-sized deaths, where our map has holes in it. And the holes are large. Of the near-Earth asteroids in that dangerous middle range, we have cataloged only a fraction. Thousands remain out there, unlogged and unnamed, tracing orbits nobody has ever measured. Our detection network is not a shield. It is a sieve, and a coarse one, mostly held together by a small number of underfunded telescopes and a handful of people who do this work while the rest of us are asleep. We are not being watched over. We're getting lucky. Every so often the luck gets a name. In 2004, a rock called Apophis, 370 meters of it, appeared for a few very tense days to have a real chance of hitting Earth in 2029. The odds climbed to about 1 in 37, the highest ever recorded for anything, before better measurements walked them back down to nothing. In 2029, it will still pass closer to us than some of our own satellites, near enough to see with the naked eye. We were never in danger that time. The point is that we did not know it until afterward. There's one direction we simply cannot watch, and it is the worst possible one. Anything approaching along the same line as the sun is drowned in the glare, invisible to ground telescopes until it is nearly on top of us. Chelyabinsk came from exactly there. That is how a 19-meter rock could ambush a modern industrial city in the 21st century in a country with a serious space program and hand it precisely 0 seconds of warning. The gun has a barrel we are not permitted to look down. There is a detail about that February morning that still unsettles the people who study it. On the very same day Chelyabinsk was struck, the world had been watching a completely different asteroid, a known one called 2012DA14, make a close and harmless pass. Every eye that cared was pointed at the object we had tracked. And while we watched the one we knew, the one we did not know slipped in from the other side of the sky and hit us. The two rocks were entirely unrelated. Somehow that is worse. We did hear Chelyabinsk, in a way, just far too late to matter. The blast was so violent that infrasound stations built to catch secret nuclear tests picked up its low rumble as it rolled around the entire planet. The waves circled the Earth more than once. Instruments in Antarctica registered a rock exploding over Russia. It is a strange kind of horror to own a listening system so sensitive it can hear the sky break, and to have it tell you only after the glass is already on the floor. To be fair to our species, we have started to fight back a little. In 2022, a NASA spacecraft named DART deliberately flew into a harmless asteroid called Dimorphos at over 22,000 kilometers an hour, just to find out if we could shove it. We could. We nudged its orbit by a measurable amount. It was a genuine triumph, and I will not undersell it. But it took years of planning against a target we already knew about. The whole nightmare of Chelyabinsk was that we knew nothing at all. Run the wider numbers, and the shape of our ignorance comes into focus. Surveys estimate there are more than 25,000 near-Earth asteroids large enough to flatten a region, and we have found maybe 40% of them. For the smaller, Chelyabinsk-sized bodies, the ones still able to level a town, we have found almost none. Millions of them drift out there. Most will never come near us. The honest translation of all that data is short and unpleasant. On any given morning, we do not actually know what is on its way. So the next time someone assures you the odds of a serious impact in your lifetime are low, believe them. They are right. They are also describing a lottery the Earth has already lost more than once on a long enough clock. The dinosaurs had a very comfortable annual chance too. Right up until the afternoon, they did not. Low probability is not the same as safe. It only means the bill comes due on a schedule too slow for us to feel. We began this whole story inside one such morning, in a city that did nothing wrong and got no warning, its people cut by their own windows while they stood at the glass to watch the light. That is the shape of the oldest fear, the ambush from above. But a falling rock is at least, in principle, a thing you could see. The dark holds worse than rocks. The next danger does not fall on you out of the sky. It is already all around you, every second, and the only thing holding it back is a layer of air you could walk straight through without noticing. Take a breath. Do it now, an ordinary one, the kind you take 20,000 times a day without a single thought. That breath is only possible because of a shell of gas so shallow that if you could drive a car straight up, you would pass through most of the survivable atmosphere in under an hour. Above it there is no air, no pressure, no warmth, and no mercy. And the line between the two is not a wall. It is a fade, and you would cross the fatal part of it long before you ran out of road. We tend to picture space as a distant place, somewhere astronauts go. It is not distant. It begins about 100 kilometers straight up, closer than many people live from the nearest large city. If the Earth were the size of an apple, the entire breathable layer of air would be thinner than the skin on it. Everything you have ever loved, every forest and ocean and human being who ever lived, is smeared across that skin. We do not live in the universe. We live in a bubble it happens to tolerate. So let us be precise about what waits on the other side of that skin, because the truth is stranger than the movies. Push an unprotected human body out into vacuum, and it does not freeze solid in an instant, and it does not burst like a balloon. What actually happens is quieter, and in its way far worse. The pressure that holds your body together simply vanishes, and every fluid inside you starts trying to become a gas. The water in your saliva, your eyes, the soft tissue of your lungs begins to boil. Not because it is hot, because there is nothing pressing down to keep it liquid. Your body swells to nearly twice its size as the water beneath your skin turns to vapor, a condition doctors call ebulism. The gas in your lungs rushes out, and you have, at most, about 15 seconds of useful consciousness before the oxygen, starved blood, reaching your brain, quietly puts the lights out. We know the 15 seconds is real because in 1965 a technician named Jim LeBlanc found out by accident. He was testing a spacesuit inside a vacuum chamber at a NASA facility in Texas when a hose slipped loose and his suit lost its pressure at near-space conditions. He stayed conscious for about 14 seconds. The last thing he remembered before he collapsed was the feeling of the saliva on his tongue beginning to bubble and boil. They repressurized the chamber in time. He lived. Most would not have. The cold is the part people get wrong. Space is not cold the way a freezer is cold, because there's almost nothing out there to carry the heat away from you. A vacuum is a superb insulator. You would not flash freeze. If anything, in direct sunlight, you would slowly cook on one side while the shaded side radiated its warmth away into the dark. Death by vacuum is not really about temperature at all. It is about pressure and about a body coming apart because nothing is left to hold it shut. And then there is the silence, which no film ever gets right because no film can. Sound needs a medium, air or water or something to travel through. In vacuum, there's nothing to carry it. A star could detonate a few kilometers from your face, and you would hear absolutely nothing. Whatever happened to you out there would happen without a soundtrack. No scream would leave your mouth as anything more than a puff of vapor. The universe does not narrate its own violence. For most of human history, this was only theory, a thing we reason out but never had to watch. Then, in June of 1971, 3 Soviet cosmonauts became the only human beings ever to die in space itself. And they died from exactly this. Georgy Dobrovolsky, Vladislav Volkov, and Viktor Patsayev had just spent a record 23 days aboard the world's first space station, Salyut 1. They were heroes. They were on their way home, and their spacecraft was about to betray them over something the size of a coin. As their Soyuz capsule separated for re-entry, a small pressure valve, one meant to open only near the ground, was jolted loose too early and cracked open in the vacuum of space. The cabin air began to hiss out. The men had seconds. They were not wearing pressure suits because the capsule was too cramped to fit 3 men in suits, a decision made years earlier to save room. In the dark and the falling pressure, they fought to find and close the valve by hand and could not reach it in time. The air left, and it took them with it. The capsule flew the rest of its descent on autopilot and landed softly, perfectly, in the grasslands of Kazakhstan. The recovery team ran to it, threw open the hatch, and expected to greet 3 living men. Instead, they found them still strapped into their seats, faces calm, with no obvious sign of what had gone wrong. A little dark discoloration on the skin, a trace of blood at the nose and ears. They looked, the recovery crew said, as though they were merely asleep. It is the only time our species has been killed by open space, and it looked like almost nothing at all. You do not even have to reach true vacuum for the body to start failing. At an altitude of around 19 kilometers, well below where space officially begins, you cross a threshold called the Armstrong limit. Up there, the air pressure has fallen so low that water boils at the temperature of the human body. Your blood does not need the void of space to bubble. It will do it in the thin, cold air over your own planet, at a height only a few kilometers above where passenger jets cruise. The hostile part of the sky begins a great deal lower than we like to think. Officially, the edge of space is drawn at the Kármán line, 100 kilometers up, where the air is too thin for wings to work and you must move at orbital speed just to stay aloft. But that number flatters us. The truly breathable air, the part that keeps a person alive and awake with no machine, is a band only a few kilometers thick, hugging the ground. Climbers call the top of Mount Everest the death zone, and it stands just 8.5 kilometers up. Above that line, with no bottled oxygen, the body simply begins to shut down and die. Astronauts almost always come home changed by one particular sight. Not the whole Earth exactly, but the edge of it. From orbit, the entire atmosphere is a thin blue line drawn along the horizon. So slender it looks like it was added as an afterthought, a haze you feel you could wipe away with a thumb. Every war, every love story, every breath ever drawn, all of it sealed inside that faint blue rind. Many of them describe the same quiet terror hiding underneath the beauty. It looks far too thin to be doing the job it is doing. And it is doing an enormous job. That fragile film holds in the air you breathe, holds out the vacuum, filters the worst of the radiation, and keeps the whole surface at a temperature where liquid water can exist. It is a life support system with no backup, no redundancy, and no off switch you would ever want pressed. We did not build it, and we do not maintain it. We simply arrived inside it, already running, and mistook a rare and delicate accident for the permanent, natural order of things. So the fear here is not a monster, and it is not a falling rock. It is a matter of scale, of how thin the safe part of everything really is. You are standing at the bottom of an ocean of air. The ocean is shallower than you think, and above its surface is a place that would take your body apart in under a minute without ever raising its voice. That is the vulnerability. Now comes the dependence. Because the thin shell over your head is not even the most important thing keeping you alive, and the thing that has came terribly close not long ago to failing us. The same star that gives you every sunrise, every harvest, every warm afternoon you have ever wasted, tried to end the modern world in the summer of 2012. It fired a bolt of superheated matter across the solar system, one large enough to knock civilization back into the age of the candle. It missed us by about 9 days. Not 9 light years. 9 days of the Earth's own travel around its orbit. And almost no one noticed because the thing that nearly hit us was invisible and the place it hit was empty. To understand what we dodged, you have to meet the last time it did not miss. On the morning of September the 1st, 1859, an English astronomer named Richard Carrington was in his private observatory doing something quiet and ordinary. He was sketching sunspots, projecting the sun's image onto a screen to trace the dark blemishes on its face. He had done it for months. He was a gentleman scientist, a brewer's son with a good telescope and a great deal of patience. And he was about to become the first human being to watch the sun attack. As he watched, 2 brilliant beads of white light suddenly flared up among the sunspots. So bright he first assumed a stray beam of raw sunlight had broken through his apparatus. It lasted about 5 minutes, then faded. Carrington had just seen a solar flare in visible light, a thing so rare it has been witnessed only a handful of times in all the years since. He did not know what it meant. He simply noted it carefully, an honest man recording something he could not explain. 18 hours later, the rest of the planet learned what it meant. Overnight, the sky caught fire. Auroras, the shimmering curtains of light normally locked to the far north and far south, blazed across the entire world and down into the tropics. People saw them over Cuba, over Hawaii, over Colombia and the Caribbean. In the mountains of the American West, gold miners woke in the small hours, saw the glow, and began cooking their breakfast, certain that dawn had come. Newspapers reported you could read their fine print outdoors at midnight by the light in the sky. It was beautiful. It was also a warning nobody yet knew how to read. Under all that beauty, the machines were failing. The one great electrical network of the age was the telegraph. Tens of thousands of miles of wire strung between cities, and it began to convulse. Operators watched sparks leap from their equipment. Some took electric shocks off their own keys. Paper caught fire in a few offices. Systems went dead across Europe and North America. The delicate pulse of Victorian communication scrambled by a force nobody had a name for. The 19th century had built its first fragile nervous system, and the sun reached down and touched it. Then came the detail that still gives space scientists a chill. Some telegraph operators discovered they could disconnect their batteries entirely and keep sending messages, running the lines on the current the aurora itself was pushing through the wires. 2 operators in New England did exactly that, and held a full conversation powered by nothing but the storm in the sky. For a few hours, the atmosphere had become the power source, a planet-wide electrical event, and human beings were riding it like a wave, not yet grasping that it could just as easily have killed them. In 1859, this was a marvel with only a small bill attached, because the world of 1859 barely ran on electricity. There was no power grid, no electronics, no satellites, almost nothing to break. A few telegraph offices burned, and the whole affair became a curiosity in the almanacs. If that same storm arrived today, over a civilization that has wired every part of its life into the electrical socket, the bill would not be small. It would be measured in the trillions, and in years, and quite possibly in lives. So it actually crossed 93 million miles of empty space to do all this. Not the flash Carrington saw. That was a solar flare, a burst of radiation, light, and X-rays, and it arrives at the speed of light in about 8 minutes. The real weapon comes behind it, slower and far heavier. A coronal mass ejection, a cloud of 1 billion tons of charged plasma blown off the surface of the sun and hurled outward at millions of kilometers an hour, dragging a knot of tangled magnetic field along with it like a fist. When that cloud slams into the Earth's magnetic field, it shakes it. The whole invisible cocoon around our planet ripples and snaps, and that shaking induces electrical currents in anything long and conductive on the ground below. Power lines, pipelines, railway tracks. The longer the wire, the larger the current the sky forces through it. Current the system was never built to carry. The aurora you would see is only the visible edge of a storm that is, at that very moment, quietly overloading the machinery beneath it. We have already had a small taste, well within living memory. On the 13th of March, 1989, a storm far weaker than Carrington struck, and in about 90 seconds it collapsed the entire power grid of Quebec. 6 million people lost electricity in the dead of a Canadian winter night, some of them for 9 hours. Transformers overheated as far south as New Jersey. It was a minor solar event by historical standards, hardly worth a footnote beside 1859, and it switched off a province like a lamp. That is the scale of our exposure now. The real vulnerability is a piece of equipment most people have never heard of. The high-voltage transformer, the massive humming boxes that step power up and down as it travels across a continent. They are the heart of the grid, and they are exquisitely fragile in the face of these induced currents, which can cook their windings from the inside. Worse, the largest of them are custom-built, often overseas, and can take a year or more to replace. A big enough storm would not merely switch off the lights. It could destroy the machines that make the lights possible, faster than we could ever rebuild them. Which brings us back to the summer of 2012, and to just how close the real thing came. On the 23rd of July that year, the sun let go a coronal mass ejection at the very top of the scale, a genuine Carrington-class monster, moving so fast it crossed the distance to Earth's orbit in under a day. A spacecraft called Stereo, sitting out in space, took the full blast, and survived to send back the data. The scientists who studied it afterward were blunt about it. Had it left the sun just over a week earlier, it would have hit us head-on. That is the meaning of the 9 days. In late July of 2012, the Earth simply happened to be somewhere else along its orbit. The bullet passed clean through the exact patch of space our planet had occupied a little over a week before. Had the timing been slightly different, had that eruption come on another afternoon, you would very likely be reading about the summer the grid died, if you were reading at all. One of the leading researchers later put the odds of a Carrington scale hit in the following decade at roughly 12%. That is not a comfortable number. That is a coin you would not want to flip. Play out the hit we avoided. A continent-wide blackout. Not for hours, but for months, as hundreds of those irreplaceable transformers fail at once. No lights, no refrigeration, no water pumped to upper floors, no working fuel pumps, no functioning banks, no internet, in cities of millions that cannot feed themselves for even a week without deliveries. Satellites blinded, aircraft grounded, the whole delicate machinery of modern life failing on the same afternoon. The estimates run into the trillions of dollars and years of recovery. And all of it would begin with a pretty light in the sky. The truly humbling part is the warning. When a coronal mass ejection is finally close enough for our instruments to measure directly, to learn its magnetic orientation and whether it will actually harm us, we have somewhere between 15 minutes and an hour before it arrives. That is the notice. Enough time, perhaps, to shut a few grids down and save some transformers, if everyone moved perfectly. We have staked the entire modern world on the good behavior of a star we cannot control, cannot predict very far ahead, and never chose. We simply assume it will keep having calm days. It is under no obligation to. But at least the sun is a danger we can name, and one that is more or less understood. The next threat is none of those things. It rains down on you constantly, right now, from the deaths of stars you will never see, particles moving so close to the speed of light that a single one of them once struck the Earth carrying the punch of a heavyweight boxer. And the only reason you're not being quietly torn apart by them is a shield you cannot feel, one that is, at this very moment, beginning to weaken. On the night of October the 15th, 1991, a machine in the Utah desert recorded something that should not have been possible. A single subatomic particle, one proton, smaller than an atom, struck the top of the atmosphere, carrying the energy of a baseball thrown hard enough to hurt. Think about that. Not a swarm, not a beam, one invisible speck of matter, hitting with the force of a fastball to the jaw. The physicists who found it were so rattled they gave it a name that was really just an exclamation. They called it the "oh my God" particle. To feel how absurd that is, you have to hold the scale in your head. A proton is unthinkably tiny, and this one was carrying the punch of a solid, hand-sized object moving fast enough to sting. It was traveling at very nearly the speed of light, so close that if you raced it to a distant star, light itself would win by less than the width of a hair after years on the road. Something out in the dark took a single particle and accelerated it to an energy we cannot come close to reaching in any machine we have ever built. And we still do not know what. The detector that caught it was called the Fly's Eye, a cluster of mirrors sitting out on a military range in the Utah desert, staring up at the night. It did not see the particle itself. Nothing could. What it saw was the flash, the faint blue glow the particle made as it tore into the upper air and shattered into a cascade of secondary particles raining down over kilometers of sky. From that ghost of a signal, the scientists worked backward and arrived at a number so large they checked it again and again, certain they had made a mistake. They had not. The number was a problem, and it still is. There is a theoretical speed limit for particles crossing the universe, a point beyond which they should bleed away energy by colliding with the faint afterglow of the Big Bang itself. The "oh my God" particle sailed straight past that limit as if it were not there. It carried more energy than the ceiling is supposed to allow, which means either it was made very close to us in cosmic terms, or something is happening that our physics has not accounted for. Decades later, with better detectors and thousands more of these monsters on record, the honest answer to where they come from is still a shrug. Step back from the record breakers, and the everyday reality is strange enough. Space is not empty of these things, it is sleeting with them. Cosmic rays, mostly bare protons stripped out of atoms, pour through the solar system at all times, flung outward by dying stars and by engines in deep space we are only beginning to identify. They move at nearly light speed, they carry electric charge, and they do not care in the slightest that you are in the way. Right now, as you sit perfectly still, they are passing through your body. Thousands of them, every second. You cannot feel it, and that is the unsettling part. Every second of your life, a fine invisible rain of particles from the far edges of the galaxy is punching through your skin, your organs, the screen in front of you, the walls of the room. Most pass clean through and touch nothing. A few clip an atom on the way and leave a tiny scar of damage in a strand of your DNA. It has been happening to every living creature since the very first cell. A constant, silent siege that no wall can stop, one we evolved beneath without ever knowing it was there. For the lower energy cosmic rays, we do know the main culprit. Supernovae, the explosions of dying massive stars, act as titanic natural accelerators. Their expanding shockwaves whipping particles up to tremendous speeds over thousands of years. So a real part of this invisible rain is quite literally shrapnel from stellar corpses, the debris of stars that died before the sun was born, still crossing the galaxy and still arriving. But the true giants, the oh my god class, are too energetic even for supernova. For those, suspicion falls on the most violent objects known, the monstrous black holes at the hearts of other galaxies. We're guessing at the return address on a bullet. When one of these particles hits the top of the atmosphere, it does not simply stop. It detonates. It smashes into an air molecule with such violence that it sprays out a shower of new particles, which smash into more molecules, which spray out more, a chain reaction cascading down through the sky. A single primary particle can become billions by the time the shower reaches the ground, spread across an area the size of a city. Some of that debris passes right through you at sea level. You have been standing in the fallout of these collisions your entire life. The reason this rain has not sterilized the surface of the Earth is a thing you have never seen and cannot touch. Our planet has a core of churning liquid iron, and that motion generates a vast magnetic field reaching far out into space, wrapping the whole world in an invisible cocoon we call the magnetosphere. It is not exactly a wall. It is more like a set of grooves carved into space, and charged particles racing in from the cosmos get caught in those grooves and flung away, deflected around us before they can reach the ground. We are alive inside a bubble of magnetism. You can actually see the shield working if you travel far enough north or south. The auroras are cosmic and solar particles being funneled down along the magnetic field lines toward the poles, striking the upper atmosphere and making it glow. That beautiful light is the visible trace of the siege being turned aside. Every green curtain over Norway, every red glow over Tasmania, is a stream of radiation that would otherwise have kept going straight into the world below. The shield does not merely block. It steers the danger toward the two places it can burn away harmlessly, high overhead. This is the part that should sit uneasily with you. That shield is not constant, and right now it is fading. Measurements over the last 2 centuries show the Earth's magnetic field has weakened by around 9%, and the decline appears to be speeding up. A weaker field is a leakier field, one that lets more of the cosmic rain reach lower and lower toward the surface. Nobody thinks the field is about to vanish tomorrow, but the machine in the core is not a steady thing, and it is doing something, and the geological record shows us just how strange that something can get. The clearest warning sign has a name, and it is already here. It is called the South Atlantic Anomaly, a great dent in a magnetic shield stretching over South America and the southern Atlantic, where the field has grown so weak that the belts of trapped radiation dip down close to the surface. It is a hole in our armor, and it is slowly growing wider and deeper. Spacecraft passing over it are bathed in extra radiation. This is not a theory or a forecast. It is a soft spot in the shield of the world, spreading right now over an ocean. Ask any satellite operator, and they will tell you the anomaly is a nuisance that occasionally turns dangerous. The Hubble Space Telescope cannot take observations while it flies through that patch of sky because the radiation floods its instruments with false signals. The International Space Station takes an extra dose of it. Astronauts have reported seeing flashes of light behind their closed eyelids as they pass over, cosmic ray particles striking their own retinas from inside. They are quite literally watching the siege land in their own eyes. Down here, the atmosphere still shields us. Up there, the anomaly is a place you learn to hold your breath through. To see where a fading field can lead, go back about 41,000 years to an event written into rocks and ancient trees around the world. It is called the Lost Champ Excursion, and during it the Earth's magnetic field did far more than weaken. It collapsed to a small fraction of its normal strength, wandered, and briefly flipped north and south trading places for a few centuries before snapping back. For a while, our shield was very nearly gone. The sky would have blazed with auroras at the equator, and the cosmic rain would have poured down harder than any human alive has ever felt. And here is the truly humbling fact. The Lost Champ Excursion was not even a full reversal. Those happen too. On average, every few 100,000 years, the Earth's magnetic poles trade places completely, and the last time it happened for good was about 780,000 years ago, which means by the slow calendar of the planet, we are overdue. During each of these flips, the field grows weak and chaotic for centuries, the shield thins, and the invisible bullets fall harder. We treat the magnetic field as a fixed feature of home. The rocks say it is a flickering candle, and no one can promise it will not gutter in our time. So far, every danger in the dark has been a force, blind and impersonal, obeying physics and nothing else. But the dark holds more than forces. Now, and then it holds visitors. In the autumn of 2017, something entered our solar system that had come from another star entirely, moved in a way nothing had ever moved before, and slipped back out into the night before we could get a proper look. And it made a lot of very serious people ask a very uncomfortable question. In the autumn of 2017, a telescope in Hawaii caught a faint smudge of light moving against the stars, and within days astronomers realized they were looking at something no human being had ever confirmed before. It was not a comet from our own family of worlds. It was not an asteroid on some long loop around the sun. It had come from another star, crossed the unimaginable emptiness in between, passed through our solar system, and was already on its way out. We had a few weeks to look at it. Then it was gone, back into the dark, forever. The telescope was Pan-STARRS, perched on a volcano on Maui, built to sweep the sky for anything that moves. What it found broke the rules at once. Everything that belongs to the sun travels on a closed orbit, an ellipse bound to come back around eventually. This object was on an open path, moving far too fast for the sun's gravity to ever hold it. That single fact was the tell. Its speed and its trajectory could only mean one thing. It was just passing through a piece of somewhere else, briefly on loan to our sky. They named it Oumuamua, a Hawaiian word that means roughly a scout or a messenger reaching out to us from the distant past. It was a good name, and an honest one, because that is exactly what it was, a fragment of another star system that had likely been traveling for hundreds of millions of years before it wandered into ours. Whatever star made it was long behind it, no way to say which one. It carried no message we could read, but it was the first solid proof that the space between the stars is not sealed. Things get out. Things come here. For all of human history, we had wondered whether material from other star systems ever reached us, and now suddenly here was a piece of it close enough to study, if only barely. Every telescope that could be turned toward it was turned, and the more they looked, the stranger it became. Because Oumuamua did not behave the way a well-mannered visiting rock is supposed to behave. It began very quietly to break the expectations of the people watching it. Start with the shape. The way its brightness flickered as it tumbled through space told astronomers it was wildly elongated, far more stretched than any asteroid we know, perhaps several times longer than it was wide. Some pictured a great dark cigar, others a thin flat sliver like a cosmic pancake, turning end over end every few hours. It was reddened, the color of something baked by radiation over eons in deep space. Nobody had ever seen a natural object shaped quite like it. That alone would have made it famous. It was not even the strangest thing about it. The strangest thing was that it sped up. As Oumuamua swung past the sun and began to leave, it accelerated, getting a small extra push that plain gravity could not explain. Now, comets do this. Comets warm near the sun, vent gas like little rockets, and get nudged along their way. But comets that vent gas grow a visible tail, a glowing halo of released material. Oumuamua had none. No tail, no halo, no obvious cloud of anything. It was being pushed by some force, and it was showing us nothing at all that could be doing the pushing. That gap, a push with no visible cause, is where the argument caught fire. Most astronomers reached for a natural answer. Perhaps it was venting a gas that simply does not glow the way ordinary comet gas does, hydrogen or nitrogen ice quietly boiling off. A shard of frozen material, unusual but explainable. But one respected Harvard astronomer, Avi Loeb, made a case the community found either brave or reckless, depending on who you asked. What if the push came from sunlight itself, striking a thin, flat, artificial surface? What if Oumuamua was a sail? What if it was made? It is important to be fair here. There is no proof Oumuamua was anything but a strange natural object, and most scientists think it almost certainly was. But the deeper problem is that we cannot go back and check. It left too fast. By the time we understood how odd it was already receding beyond the reach of our best instruments, dimming into the black. We got one look, a few weeks of blurry data on the first confirmed thing ever to visit us from another star, and then it was gone for good. We will never know for sure. That is the part that lingers. Sit with the shape of that. Something arrived from the depths of the galaxy, moved in a way we could not fully explain, and departed before we could resolve the question, leaving a permanent asterisk in the record. Not because the answer is unknowable in principle, but because we were too slow and it did not wait. It owed us nothing. It did not slow down, did not signal, did not linger to be understood. It simply passed through the room and left by the far door while we were still fumbling for the light. If Oumuamua left us uneasy, its successor was almost a relief. In the summer of 2019, an amateur astronomer named Gennady Borisov, using a telescope he had built himself in Crimea, spotted a second interstellar visitor. This one, later called Borisov, was reassuringly ordinary. It was plainly a comet with a proper, glowing tail, made of the same kinds of ices as the comets born around our own sun. It had also come from another star, and it too was just passing through. But it looked like family. It told us that some of what drifts between the stars is comfortingly familiar. Not all of it, some. The two visitors together carried a lesson that is easy to miss. We found both of them within 2 years of each other, right after we finally built telescopes fast and wide enough to catch such things. That timing is not a coincidence, and it is not comforting. It means these objects were almost certainly passing through all along for the entire history of our species, and we simply never had the eyes to notice. The current estimates suggest that at any given moment, several pieces of other star systems are inside our own, threading silently between the planets, unseen. And if lone fragments of rock and ice can cross between stars, so can whole worlds. This is where it turns genuinely eerie. Scattered across the galaxy, drifting in the enormous dark between the stars, are planets with no sun at all. We call them rogue planets, and they are exactly what they sound like, full-sized worlds, some as large as Jupiter, cast loose and wandering alone through interstellar space, bound to nothing, warmed by nothing, falling through the night on paths that will not bring them home for billions of years, if ever. Nobody is sure how many there are, and the estimates are staggering. Some studies suggest rogue planets may actually outnumber the stars in the Milky Way, which would put their count in the hundreds of billions, perhaps the trillions. They are almost impossible to see because they give off no light of their own, and we usually only catch one when its gravity briefly bends the light of a star far behind it. For every rogue world we have detected, there are countless more we never will. The galaxy holds more than stars and empty space. It is thick with lost worlds, unlit, uncounted, adrift. Try to imagine standing on one. There is no sun in the sky, and there never will be, only the distant frozen pinpricks of other stars, no closer or warmer than they are to us. The temperature at the surface sits barely above absolute zero. The oceans, if there ever were any, are iced down to the bedrock. It is a world in permanent, total, eternal night, sailing through the dark at tens of thousands of kilometers an hour, and it has been doing so in silence since long before there was anyone to be horrified by it. There are hundreds of billions of them. That is the fear at the door in this chapter, and it is a quiet one. Not that something is coming to get us, but that the dark around us is populated, trafficked, full of movement we cannot see. Rocks from other suns, whole planets with no sun at all. Things pass through the space near Earth, unannounced and unnoticed, and they do not stop, and they do not care, and for almost all of them we will never even know they were here. The neighborhood is not empty. We are simply not equipped to see who is walking through it. But you do not have to look out into the wandering dark to find a world that has gone wrong. You only have to look at our nearest neighbors, the two planets closest to us, one on each side. Both were probably once far more like Earth than they are now. And both are dead. One is a frozen husk, and the other is a furnace where it rains acid on a ground hot enough to melt lead. They are not warnings from far away. They are our own possible futures, already written, just one door down. One planet closer to the sun than we are, there's a world almost exactly the size of the Earth, made of much the same rock, born in the same cloud of dust at the same time, right next door. By every early measure, it should have been our twin. Instead, it is the closest thing to hell that physics can build. The ground is hot enough to melt lead. The air would crush you and cook you at once. And high in its poisonous sky, it rains sulfuric acid that never once reaches the ground. Its name is Venus, and it may have looked, long ago, a great deal like home. For a long time, we let ourselves imagine Venus as a warm and welcoming place. It is wrapped in thick white clouds, brilliant and soft, the brightest thing in our sky after the sun and moon. Writers pictured steaming jungles beneath it, oceans, maybe even life. It is nearly the same size as Earth, nearly the same mass, made of the same materials. If you were sketching a second home for humanity from a distance, Venus is the one you would circle first. Then we sent machines to look under the clouds, and the dream died on contact. The surface temperature on Venus is about 465 degrees Celsius. That is hotter than a kitchen oven turned to its highest setting, hotter than the melting point of lead. It is the same crushing heat everywhere, at the poles and at the equator, in the day and through the long night, because the atmosphere is so thick it smears the heat evenly across the entire globe. There is no cool place to stand. There is no shade. Venus is the hottest planet in the solar system, and it is not even the one closest to the sun. Mercury is cooler. Sit with that. The reason Venus is hotter than Mercury is the single most important word in this whole chapter: greenhouse. The air on Venus is almost entirely carbon dioxide, and it is dense beyond imagining, a suffocating blanket that lets sunlight in and then refuses to let the heat back out. The warmth pours in and cannot escape, and it builds and builds until the whole planet glows with trapped energy at a temperature that never falls. It is not nearness to the sun that cooks Venus. It is its own air, The planet is being strangled by its own atmosphere. And that atmosphere is monstrously heavy. Stand on the surface of Venus, and the air would press down on you at about 92 times the pressure at sea level on Earth. That is the pressure you would feel nearly a kilometer deep in the ocean, enough to flatten a submarine. You would not simply burn to death on Venus. You would be crushed and boiled and suffocated all in the same instant by an atmosphere so thick it behaves almost like a fluid. The place is not merely hostile. It is actively, thoroughly lethal in every possible way at once. We know all this in gruesome detail because the Soviet Union, in one of the boldest and least remembered feats of the space age, actually landed machines there. Through the 1970s and 80s, a series of probes called Venera were dropped into that inferno, one after another, most of them dying on the way down. The ones that survived the fall lasted only minutes on the surface before the heat and the pressure destroyed them. But in those minutes, a few of them did something extraordinary. They sent back photographs. The pictures are some of the strangest images human beings have ever taken. A flat, orange, rock-strewn plain, lit by a dim, rusty glow filtering down through the clouds, stretching to a close horizon under a sky the color of a bruise. No movement, no water, nothing but hot broken stone in a sulfurous haze. And then, after a few minutes, the signal ends because the lander has been cooked to death where it stands. Those photographs are our only eyes on the surface of our twin, and they show a still life of a world that killed the camera that took it. Above all that, in the high clouds, is where the acid lives. Venus is wrapped in thick layers of sulfuric acid cloud, and out of them falls a corrosive rain. But here is the cruel detail. That acid rain never touches the ground. It falls from the clouds, and long before it can land, it meets air so hot that it boils back into vapor and rises again. An endless cycle of acid falling and evaporating in a sky that will not let it finish. Even the weather on Venus is a punishment with no release. The question that should haunt you is not how Venus got so awful. It is what Venus used to be, because the growing evidence suggests that for perhaps its first 2 or 3 billion years, Venus may have been temperate, with liquid water oceans on its surface, quite possibly the most Earth-like world in the solar system besides Earth itself. 2 planets, side by side, born together, both with water, both with a chance at life. One became the world you were standing on. The other became the furnace. And the thing that separated their fates was not luck. It was heat. The tragedy of Venus is a feedback loop, and it is one Earth is not immune to. As Venus slowly warmed, its oceans began to evaporate. Water vapor is itself a powerful greenhouse gas, so the more the oceans evaporated, the more heat was trapped, which evaporated more ocean, which trapped still more heat. The loop ran away. The oceans boiled off entirely into the sky. The water was eventually stripped away into space, and what remained was the dry, crushing, acid-choked hell we see today. It did not happen in a day, but once it truly started, it could not stop. That is why astronomers do not talk about Venus as a curiosity. They talk about it as a warning delivered in 465 degrees of heat. It is proof, sitting right next door, that a world can start out temperate and blue and wet, with every ingredient for life, and end up a sterile oven. The line between a living planet and a dead one is not as wide as we would like to believe. It is a matter of degrees, and of a feedback loop that, once tipped, does not tip back. Now turn the other way to the planet on our outer side because it died differently, and its death is just as instructive. Mars is not a furnace. Mars is a frozen, rust-colored desert, so cold and so dry and so thin air that a human standing on it unprotected would be dead in moments, not from heat, but from near vacuum and cold. It is a smaller world and a quieter grave. But the rocks of Mars carry a memory, and the memory is of water. The evidence is written all over its surface, and it is unmistakable now that we have driven robots across it for years. Dried up river valleys winding for hundreds of kilometers, the beds of ancient lakes, rounded pebbles that could only have been smoothed by flowing water, minerals that form only in water's presence. Billions of years ago, Mars had rivers and lakes, and quite possibly a great ocean covering much of its northern half, under a thicker atmosphere and a warmer sky. For a while, early Mars and early Earth may have been two blue worlds side by side. So where did it all go? Mars is small, and being small killed it. Its core cooled and its churning slowed, and it lost the magnetic field that once shielded it, the same kind of shield Earth still has. With the shield gone, the solar wind, that constant stream of particles from the sun, began to strip the Martian air away into space, molecule by molecule, over hundreds of millions of years. As the air thinned, the pressure dropped, and the water could no longer stay liquid. It froze, or boiled away, or fled underground. The rivers stopped. The planet went dry and cold and still, and it has stayed that way ever since. So look at the two of them, our nearest neighbors, one on each side. One cooked to death by its own air. One frozen to death when it lost its shield. Both, we now believe, once had liquid water. Both once had a chance. And on both, the chance is long gone. The water vanished. The surface sterile. The whole story finished before anything on Earth had crawled out of the sea. This is what the neighborhood actually looks like. Two dead worlds, one on each side of us, that used to be more like home. It is tempting to tell yourself that Earth is different, that our world is stable, permanent, safe. The other planets say otherwise, and so does our own past. Because life on Earth has not had one long, easy run. 5 separate times, something has reached into the fossil record and erased almost everything alive. And when scientists trace the causes of those catastrophes, some of the lines lead back off the planet entirely and out into space on what looks disturbingly like a schedule. Life on Earth likes to present itself as a triumphant, unbroken story, a 4 billion year climb from the first cell all the way to us. It is not. It is a story interrupted again and again by near total erasure. At least 5 times, something has swept across this planet and killed the overwhelming majority of everything alive, emptying the oceans and the land in a geological instant. We call them mass extinctions. And when we look for what pulled the trigger, some of the most chilling suspects are not on Earth at all. They're out in space, and they may run on a clock. We know these catastrophes happen because the dead leave a record. In the layered rock of the Earth, read like the pages of a book, the fossils of entire worlds of creatures appear, thrive across millions of years, and then, at a single line in the stone, vanish all at once, never to be seen again. Above that line, the old life is simply gone, and after a long silence, something new and different slowly fills the empty world. Each of those lines is a graveyard the size of a planet, compressed into a band of rock you could cover with one hand. Geologists count 5 of the very worst, the Big 5, spread across the last half-billion years. Each has its own character and its own likely killers, from volcanic hell to sudden cold to poison seas. But the numbers are what stop you. In the worst of them, the fraction of species wiped out was not half and not most. It was very nearly all. Life came within a hair of ending entirely, more than once, on the same planet you were sitting on, and then, each time, barely crawled back from the edge. The worst of them all came about 252 million years ago, at the end of the Permian period, and its name tells you everything. The Great Dying. In a geological blink, something like 9 in every 10 marine species disappeared, and the great majority of land life along with them. This is the closest complex life has ever come to being switched off completely. Whole branches of the tree of life, animals that had ruled the seas for hundreds of millions of years, ended forever in that single catastrophe and never came back. The likely trigger for the Great Dying was homegrown, a colossal outpouring of lava across what is now Siberia that poisoned the air and the seas and cooked the climate for thousands of years. It shows that Earth can murder its own inhabitants with no help at all from the sky, but also proves the machinery exists. It proves that a living, thriving, crowded planet can be scoured almost clean, and that the ordinary rules of survival mean nothing when the whole environment turns against everything at once. Recovery took millions of years. Some of it never came. The extinction we understand best, though, is the one that did come from space, and it is the one you already know. 66 million years ago, the reign of the dinosaurs, which had lasted well over 100 million years, ended in what was very probably a single afternoon. The killer was a rock, an asteroid perhaps 10 to 15 kilometers across, and it struck what is now the coast of Mexico, near a town called Chicxulub, with a violence almost impossible to hold in the mind. The impact released the energy of billions of nuclear bombs in an instant. It punched a crater more than 150 kilometers wide, through a curtain of molten rock across the continent, and set the sky itself on fire as debris rained back down through the atmosphere. Then came the long dark. So much dust and soot was thrown up that it blocked the sun for years. The plants died, the food chains collapsed, and the great cold and hunger finished what the fireball had begun. 3/4 of all species on Earth died. The dinosaurs simply did not make it out. For a long time, nobody knew a rock had done it. The proof came in 1980 from a father and son team, the physicist Luis Alvarez and the geologist Walter Alvarez. They found that the thin layer of clay marking the extinction all over the world was rich in iridium, a metal rare in the Earth's crust, but common in asteroids. There was a smear of extraterrestrial dust laid down across the entire planet at exactly the moment the dinosaurs died. The murder weapon had left its fingerprint in the rock, and the fingerprint had come from space. Once you accept that one mass extinction was mailed from space, you start to look at the others differently. Take the oldest of the big five, the Ordovician extinction, about 445 million years ago, which killed most of the life in the seas at a time when almost nothing yet lived on land. Its cause is debated, but one striking hypothesis points at a weapon we will meet again later in this story, one of the most violent events the universe can produce. A gamma ray burst, a beam of pure radiation from a dying star, thousands of light years away, that may have swept across the Earth. The idea is that such a beam, striking the atmosphere, would have shredded the ozone layer in seconds, stripping away the shield that blocks the sun's ultraviolet light. With the ozone gone, that radiation would have poured down onto the surface and into the top layers of the ocean, killing the tiny, drifting organisms that everything else depended on. It is only a hypothesis. We cannot prove it happened, but it is entirely possible, and that is the disturbing part. A star could have died so far away that we would never have known, and reached across the void to kill nearly everything in our seas. Then, in the 1980s, two paleontologists named David Robb and Jack Sepkoski did something that made the whole field go quiet. They gathered the timing of the extinctions across the fossil record, ran the numbers, and thought they saw a rhythm. The great die-offs, they claimed, seemed to recur roughly every 26 million years, like a slow, ghastly heartbeat. If that were true, extinction would not be a series of unrelated accidents. It would be a pattern, and a pattern that regular needs a clock, and there is no clock on Earth that ticks in tens of millions of years. So people went looking for a cosmic clock, and the ideas they came up with are magnificent and unsettling in equal measure. One is called Nemesis, the suggestion that our sun has a hidden companion, a small dim star or a dark stellar remnant, riding a vast slow orbit, swinging close every 26 million years, and, each time, disturbing the great cloud of comets at the edge of our solar system, flinging a hail of them inward toward the planets. A Death Star, quite literally, on a long leash. We have never found it. That does not mean it is not there. There is another version that needs no hidden star, only the shape of the galaxy itself. As our sun orbits the center of the Milky Way, a journey that takes about 230 million years, it does not travel in a flat line. It bobs up and down through the crowded central plane of the galactic disk like a horse on a carousel, rising and sinking every 30 or so million years. And each time it passes through that dense plane, we are exposed to more comets disturbed, more radiation, more of everything dangerous. Our deaths, in this picture, are written into the rhythm of our own path around the galaxy. Whether or not the clock is real, and the evidence is still argued over, the deeper lesson has already landed. To even ask these questions, you have to open up deep time, and deep time is its own kind of terror. Human civilization is a few thousand years old. Our species, a couple of 100,000. The last mass extinction was 66 million years ago. The Great Dying, 252 million. Written against that clock, all of recorded history, every empire and every war and every person you have ever heard of is a single thin bright line in a book of catastrophes, and the line has barely begun. And that reframes everything. We tend to think of extinction as the exception, a rare tragedy that interrupts the normal state of things, which is life going quietly on. The fossil record says we have it backward. Extinction is not the interruption. It is the recurring event. It is arguably the rule. More than 99% of all species that have ever lived are already gone, and the planet has emptied itself almost completely, over and over, sometimes perhaps on a schedule set by the sky. We are not living in the safe interval between disasters. We are living in a brief pause, and we do not know how long the pause is. Everything so far has come at us from the dark, close to home, things that could kill your body on an ordinary afternoon. But we have been circling the real subject, avoiding the obvious. Because the single most dangerous object in the sky is not a distant asteroid or a hidden companion star. It is the one thing up there we never fear, the one we are glad to see each morning. It has been detonating over our heads for 4.5 billion years, and it is slowly, patiently getting hotter. We call it sunrise, and we treat it as the gentlest thing in the world. It is not gentle. Every morning, a controlled thermonuclear explosion the size of 1 million Earths hauls itself over the horizon, and we squint at it and make coffee. The sun is a hydrogen bomb that has been detonating without pause for 4.5 billion years, held in check only by its own crushing weight. It is the reason you are alive. It is also, on a long enough clock, the thing that will kill this world. And it is getting hotter. A star is the simplest and the most violent thing in the sky, and it exists because of a single unending argument between two forces. On one side, gravity pulling every atom of that enormous ball of gas inward, trying to crush the whole thing down into a point. On the other, the heat of fusion in the core, pushing outward, trying to blow the whole thing apart. The sun is what you get when those two forces fight to a perfect draw. It is not a solid object. It is a balance, an explosion, and a collapse locked together, standing still. That balance is called hydrostatic equilibrium, and it is the most important truce in your life. If the fusion in the core ever pushed a little harder, the sun would swell and cool. If gravity ever won for a moment, the sun would shrink and heat up. Instead, they hold each other, second by second, in a stalemate that has lasted longer than the Earth has had oceans. Everything you are, everything that has ever lived, exists in a narrow, steady warmth thrown off by two titanic forces that have agreed, for now, to cancel out. The engine at the center is almost impossible to picture honestly. In the core of the sun, every single second, roughly 600 million tons of hydrogen are crushed together and fused into helium. 600 million tons, gone every second for billions of years. A small fraction of that mass is converted directly into pure energy, and that energy is the sunlight on your skin. The sun is very slowly turning itself into light and throwing itself away in every direction, and it has enough fuel to keep doing it for billions of years more. The conditions that make this possible are beyond anything on Earth. At the core, the temperature is around 15 million degrees, and the pressure is hundreds of billions of times the air pressure at sea level. Hydrogen atoms that would normally repel each other are slammed together so hard and so fast that they merge. This is fusion, the same reaction we can only trigger on Earth for a fraction of a second inside a bomb. The sun does it continuously, in a region larger than many entire stars, and has done so without a single pause since before the first life stirred. And all of that is happening 8 minutes ago. The sunlight reaching your eyes right now left the surface of the sun about 8 minutes and 20 seconds earlier, because even light, the fastest thing there is, takes that long to cross the 93 million miles between us. You never see the sun as it is. You only ever see the sun as it was. If it vanished this instant, snuffed out completely, you would go on feeling its warmth and seeing it hang in the sky for 8 more minutes, entirely unaware that the thing keeping you alive was already gone. The 8 minutes is only the last leg of a far stranger journey. The energy in that sunlight was made in the core, but it does not fly straight out. The sun is so dense that a packet of light born in the center bounces and scatters, absorbed and re-emitted over and over, taking a drunken random walk that can last tens of thousands of years before it finally reaches the surface and escapes. So the warmth on your face was forged in the heart of the sun back when our ancestors were still learning to make fire. It has been trying to get out ever since. You might wonder why the whole thing does not simply blow up all at once. And the answer is a kind of grace built into the physics. The sun is self-correcting. If the core fuses a little too fast, it heats up, expands slightly, and that expansion cools it back down, slowing the reaction. If it slows too much, it contracts and heats and speeds up again. The bomb regulates itself. It is a runaway explosion that has, somehow, taught itself restraint, and that restraint is the only reason the sky is not on fire. But restraint is not the same as constancy, and this is the fact almost no one is ever told about the sun. It is not stable in the long run. It is brightening. As the core fuses hydrogen into helium, the helium ash builds up, and the core slowly contracts and heats, which makes the sun burn a little more fiercely with every passing in. The sun today is roughly 30% brighter than it was when the Earth first formed. It is a dimmer switch being turned up agonizingly slowly, and it does not stop it comfortable. That slow brightening solves an old puzzle and opens a new dread. Billions of years ago, when the sun was dimmer, the young Earth should by rights have been frozen solid, and yet we know it had liquid water and early life. The faint young sun is a genuine scientific riddle. But the flip side of that riddle is the part that matters here. If the sun was much fainter in the deep past, then it is climbing steadily toward being much brighter in the future. And the Earth sits in a narrow band of warmth that will not stay put. So there's a countdown, and it is shorter than the one you have heard about. Everyone knows the sun will die in about 5 billion years. Almost no one knows that the Earth will become uninhabitable long before that. In roughly 1 billion years, perhaps a little more, the steadily brightening sun will have grown hot enough to push our world past the edge. The oceans will begin to evaporate in earnest, and the same runaway greenhouse that murdered Venus will come for Earth. Not in 5 billion years, in one. Play it forward, and it is a slow, quiet apocalypse. As the sun brightens, the extra heat drives more water vapor into the sky, which traps more heat, which drives up more vapor. The oceans boil away into the atmosphere over millions of years. The water is broken apart by sunlight in the upper air and lost to space. The land dries and cracks. Long before the sun becomes a monster, its ordinary, gradual warming will have turned the blue planet into a hot, dry, sterile rock. The end of life on Earth is not a bang. It is a rising temperature that never stops rising. Let that reset your sense of the timeline. Complex life has existed on Earth for around 600 million years. The window that remains, before the brightening sun sterilizes the surface, is only about 1 billion more. In the grand story of our planet, we are not near the beginning. We are past the middle. The age of life on Earth is more than half over. And the thing closing the window is not some rare disaster or distant threat. It is the same sun that will rise, warm and ordinary, tomorrow morning. There is something clarifying about that, and something cold. The countdown was running long before we arrived, and it will keep running long after we are gone. The sun does not know we are here. It is not warming us on purpose, and it will not sterilize us out of malice. It is simply a ball of fusing gas, obeying the only rules it has, brightening because that is what stars do, indifferent to the thin film of life that happened to arise in its glow and mistake a temporary warmth for a permanent home. So the most familiar object in your entire life, the one you have never once been afraid of, is a slow bomb with a lit fuse and a date attached. It gave us everything, and it will take everything back, and it feels nothing about either. That is the sun in its long, patient, ordinary middle age. But middle age ends, and when the sun finally runs out of the hydrogen in its core, it does not fade quietly. It does something enormous, something we have watched other stars do, and something with our own world's name written directly into it. Set your imagination about 5 billion years into the future. The sun has spent its entire hoard of core hydrogen, the fuel that kept it burning steadily since before the Earth existed, and now the long balance is ending. What comes next is not a gentle dimming. It is the most violent transformation the sun will ever undergo, and it ends with our planet either burned to bare glowing rock or erased from existence entirely. This is not speculation. We have watched it happen to thousands of other stars. We know the obituary. We even know, roughly, the date. It begins with a paradox. When the core finally runs out of hydrogen to fuse, you might expect it to cool down. It does the opposite. With the fusion in the very center sputtering out, there is nothing left to push back against gravity, so the core begins to collapse in on itself, and collapsing makes it hotter, not colder. The temperature climbs higher than it has ever been, and that rising heat ignites a shell of hydrogen wrapped around the dead core, a ring of fire burning fiercely around shrinking heart. That shell burns far more furiously than the old core ever did, and it dumps a torrent of new energy into the outer layers of the sun. The star cannot contain it. The outer envelope, all that gas, begins to swell outward, and as it expands, it cools, its color sliding from white toward angry orange and then deep red. The sun is becoming a red giant. It puffs up like something rising in an oven, growing not by a little, but by a factor of hundreds, ballooning out into the space where the inner planets now orbit. The scale of the swelling is difficult to take seriously. At its largest, the red giant sun may grow to something like 200 times its current size, its bloated surface reaching out past the orbit of Mercury, then past Venus, expanding into the space those worlds occupy today. Mercury will almost certainly be swallowed whole, vaporized inside the sun's own outer layers. Venus, the twin we visited earlier, very likely meets the same fate, drawn into the fire. The furnace planet, in the end, becomes part of the furnace. And then there is Earth, and here the story gets genuinely uncertain, which is somehow worse than a clean answer. As the sun swells and loses mass, the planet's orbits drift outward, and the Earth may edge a little farther out, just possibly staying beyond the reach of the sun's surface. Or the drag of the sun's expanding outer atmosphere may slow it, pull it inward, and swallow it after all. Astronomers still argue over which it will be. But it hardly matters to anything living, because long before the sun's surface arrives, the Earth is already dead. Picture that final Earth in its last act. The sun no longer rises as a bright disk. It fills a huge swath of the sky, a vast, dim, swollen red thing, close enough to look almost touchable, its surface churning. The temperature at the ground climbs past the point where rock itself begins to glow and soften. The oceans are gone, boiled away a billion years earlier. The atmosphere has been stripped off. Whatever record remained of US, of cities, of oceans, of the entire history of life, is baked into slag on the surface of a cinder. And still the sun keeps growing. Inside the dying star, the drama is not over. The collapsing core keeps heating until it crosses a new threshold, hot enough now to fuse helium, the ash left over from the hydrogen burning. In stars like the Sun, this ignites suddenly in a runaway event called the helium flash, a burst of fusion so intense that for a few seconds a single star can pour out energy on the scale of an entire galaxy, all of it buried inside, invisible from the outside. The Sun steadies again, briefly, now burning helium into carbon, buying itself one last short chapter of life. But this reprieve is brief and unstable. Helium burns fast, and the Sun, now a swollen and restless giant, begins to pulse, throbbing in and out, growing less and less able to hold on to its own outer layers. With each heave, it flings great shells of gas off into space. The star is coming apart, gently, in slow motion, shedding the material it spent billions of years assembling. It is not exploding. It is exhaling, over and over, casting the outer Sun away into the dark until only the naked core is left. What it leaves behind is one of the most beautiful and misleading objects in the universe. The gas the Sun sheds spreads out into a vast, glowing, intricate cloud, lit from within by the searingly hot core now exposed at its center. We call these clouds planetary nebulae, and they're stunning, the delicate, colorful rings and shells you have seen in the most famous images from our telescopes. Every one of them is a death. Each is the discarded body of Sun laid out across light years, glowing softly as it disperses. You can go out and look at what awaits the Sun if you have a good enough telescope. The Ring Nebula in the constellation Lyra, the Helix Nebula with its great staring eye, the Cat's Eye with its layered shells. Every one is a star like ours, a little further along, caught in the act of dying and dressing its own death in color. When astronomers look at those objects, they're not looking at something exotic and far removed from us. They're looking at a home movie of our own future, filmed on other stars, playing on a loop across the sky. At the heart of that fading cloud sits the thing the Sun truly becomes. Not a monster, not a giant, but a small, dense, dead ember called a white dwarf. All that remains of the core, crushed by gravity into a ball roughly the size of the Earth, yet carrying something close to half the mass of the entire Sun. A single spoonful of it would weigh several tons. It no longer fuses anything. It generates no new energy. It simply sits there, unimaginably hot at first, glowing white from leftover heat, with nothing left to burn. And this is how the Sun ends, not with a bang, but with the longest, slowest fade imaginable. The white dwarf has no fuel, so it can only cool, radiating away its stored heat into space, dimming from white to yellow to red across billions upon billions of years. In theory, given enough time, it will cool all the way to a cold, dark, crystalline cinder called a black dwarf. But the strange part is this. The universe is not yet old enough for a single black dwarf to have formed. Not one. The Sun's true final state lies further in the future than the entire age of the cosmos so far. There is a particular kind of vertigo in knowing the date of your own home's destruction. Not fearing it, not preventing it, simply knowing it, the way you might read the year on a distant tombstone. Everything humans have ever built or hoped for, the whole future of any life that may one day descend from us, all of it unfolds in a shrinking window before that swollen red sun fills the sky. We are not living under an open sky with an endless future. We are living inside a countdown, in a house with a demolition date already set, and the wonder is how rarely we look up and remember it. What makes all this land differently from the earlier fears is that there is no dodging it. An asteroid might miss. A solar storm might arrive on a quiet day. But the death of the Sun is not a risk. It is a schedule. It is written into the amount of hydrogen in the core and the unbending laws of fusion. And no shield, no technology, no run of luck changes it by a single year. If anything of us is to survive, it will not be here. It cannot be here. The only certainty is that the home will burn on time as promised. And yet, gentle as it is, our Sun's slow fade is nothing beside what larger stars do. The sun is small. It is well behaved. It dies quietly in its own bed. But scale a star up, make it 8, 20, 100 times heavier, and everything changes: the life, the death, the violence. There's one such giant hanging in your winter sky right now. The shoulder of a famous constellation, a red point of light, so vast the human mind cannot hold it. It is dying, and when it goes, it will not exhale. It will detonate. The sun feels enormous to us, and it should. You could line up over 100 Earths across its face and pour more than 1,000,000 into its volume. But the sun is a dwarf. Out among the stars, there are things so vast that if you took one and set it down where the sun now sits, its glowing surface would swallow Mercury, Venus, the Earth, Mars, and reach on toward Jupiter, engulfing the entire inner solar system as though it were nothing. These are the supergiants and the hypergiants, the true monsters of light. And one of them is hanging in your night sky, right now, waiting to explode. Go outside on a winter evening and find Orion, the hunter, one of the easiest constellations to spot in the northern sky. Look at his upper shoulder, at the star that glows a little orange against all the cold white ones around it. That is Betelgeuse, and casual as it looks, it is one of the largest stars we can see with the naked eye, a red supergiant so bloated and so unstable that astronomers watch it the way you might watch a sick relative, wondering quietly whether tonight is the night. To grasp Betelgeuse, you have to abandon your sense of scale entirely. It is something like 700 times wider than the sun. If you could pluck the sun out of the center of the solar system and drop Betelgeuse in its place, its surface would engulf Mercury, Venus, Earth, and Mars, and swell outward nearly to the orbit of Jupiter. Everything we call home would be deep inside the star, not near it, not orbiting it, inside it. And Betelgeuse is not even close to the largest star we know of. It is merely the largest one hanging over your house. The sheer size does strange things to time. Light, which crosses the whole width of our sun in a couple of seconds, would take hours to travel from one side of Betelgeuse to the other. If the surface flared on one edge, the far edge would not learn of it for most of a day. It is so vast and so diffuse that its outer layers are thinner than the air you breathe, a colossal, glowing fog hundreds of millions of kilometers across, held together by its own faint gravity, endlessly churning. A thing that big should not be able to hold itself together at all, and it can barely. Because Betelgeuse is not a young star in its prime. It is old, and it is dying right at the end of its life, even though it has existed for only a few million years. That is the brutal bargain of the giants. The bigger a star, the faster it burns through its fuel, so the most massive stars live the shortest lives. Betelgeuse has already raced through nearly all of its existence, and is now fusing heavier and heavier elements in its core in a last, desperate effort to keep itself alight. That effort has a hard ending, and the ending is close. For a few months, not long ago, it looked as though the ending might be here. Starting in late 2019 and running into early 2020, Betelgeuse did something it had never done in the history of careful observation. It dimmed, dramatically. It lost around 2/3 of its brightness, fading so much that you could see the difference with your own eyes in Orion's shoulder. Astronomers around the world swung their instruments toward it, and a single electric question ran through all of them. Was the monster finally about to blow? The answer, when it came, was almost anticlimactic and also revealing. Betelgeuse had not been about to explode. It had belched. The star had thrown off a great cloud of gas from its surface, which cooled and condensed into dust, and that dust drifted across the star from our point of view, dimming it like smoke passing over a lamp. It was not a death rattle. It was the star sneezing. But it was a reminder that these giants are restless, unstable things, forever shrugging off pieces of themselves, and that we truly cannot predict from one year to the next what they will do. What we do know is this: Betelgeuse will explode. It is certain. When it exhausts the last of the fuel it can fuse, its core will collapse, and it will die as a supernova, one of the most violent events in the universe. What nobody could tell you is when. It might happen 100,000 years from now. It might have already happened. The light of the explosion crossing the 600 or so light years toward us at this very moment, due to arrive tonight, or next century, or never in any human lifetime. We are watching a fuse of unknown length. And when the light of it finally reaches us, it will be a spectacle unlike anything in recorded history. Betelgeuse going supernova would blaze so brightly that it would rival the full moon, a single searing point of light visible in broad daylight, casting shadows at night, for weeks or even months. Every human alive would see it. It is far too distant to harm us, thankfully. But for a while our sky would carry two suns, one of them the corpse light of a dead giant, and no one who saw it would ever forget it. As grand as Betelgeuse is, it is not the ceiling. The largest known stars make it look modest. There are red hypergiants with names like UY Scuti, Stevenson 2 to 18, and VY Canis Majoris, stars so enormous that the numbers stop meaning anything. Some of them are well over 1,000 times the width of the sun, perhaps closer to 2,000. These are among the biggest single objects in the entire universe, and they sit at the very edge of what is physically possible for a ball of gas to be. Try to hold one in your mind. If you placed one of the true giants, VY Canis Majoris, where the sun is, its surface would extend past Jupiter, out toward the orbit of Saturn. A jet airliner flying at cruising speed would need hundreds of years just to circle it once. Light itself needs the better part of a day to cross it. These are not stars the way you picture stars, tidy bright points. They are slow, unstable, dying mountains of thin, glowing gas, so large that our entire solar system would rattle around loose inside them like a seed in a cathedral. And every one of them is living on borrowed time. The reason there are so few of these giants, the reason they are rare and precious to astronomers, is that they burn out almost as fast as they form. A star like the Sun lives for 10 billion years. A supergiant like Betelgeuse lives for perhaps 10 million, 1,000 times shorter. They are the mayflies of the stellar world, blazing with unimaginable brilliance for a cosmic instant, and then dying young. To see one at all is to catch it in the last brief flash of a very short life. There is a particular unease in standing under a thing that large and that unstable, even at a safe distance. We like to imagine the stars as fixed and eternal, the one constant backdrop to all our small human dramas. But the giants give the lie to that. They swell and shrink. They pulse. They shed their skins. They flicker on the edge of catastrophe. Betelgeuse alone has visibly changed within our lifetimes. The night sky is not a painting. It is a slow-motion film of enormous objects living and dying, and some of them are very near the end. So the next clear night, find that orange star on the hunter's shoulder and really look at it. You are seeing light that left a dying monster 6 centuries ago when the star was already old. You are looking at something so vast our whole world would vanish inside it, so unstable it could tear itself apart at any moment, so far along in its dying that its explosion may already be on its way to you across the dark. It is beautiful. It is also a countdown you can watch with your own eyes. Because the fate waiting for Betelgeuse and for every one of these giants is the same, and it is the most violent single event that ordinary matter can produce. When a star this massive dies, it does not fade like the sun. It does not exhale its layers gently into a pretty nebula. It collapses in less than a second and rebounds in an explosion so bright it can briefly outshine 100 billion other stars combined. To understand the giants is to understand that they are all walking toward the same door. And on the other side of that door is the supernova. For a few weeks, a single dying star can outshine everything around it. Not the moon, not a planet. Its entire galaxy. One star, at the moment of its death, can blaze more brightly than the combined light of 100 billion other suns. All the stars in the galaxy that holds it, put together. We call it a supernova, and it is the most powerful explosion of ordinary matter in the universe. It is also, strangely, the most creative event there is. Everything you love was assembled inside one. To see how it happens, go back inside a giant star like Betelgeuse in the last stage of its life. Over millions of years, it has been fusing lighter elements into heavier ones, and now it is layered like an onion. Hydrogen fusing in the outermost shell, then helium beneath, then carbon, oxygen, neon, silicon, each burning hotter and faster in the deeper layers, each shell fusing in a shorter and shorter time. The outer layers might burn for thousands of years. The innermost, in the final days, burn for a matter of hours. The star is racing towards something, and it does not know how to stop. The racing ends at iron. When the core finally fuses its way to iron, the star has hit a wall built into the laws of physics. Every fusion up to this point has released energy, and that outward flood of energy is what held the crushing weight of the star at bay. But fusing iron does not release energy. It absorbs it. So the moment the core becomes iron, the fire that has held back gravity for millions of years simply goes out. The support vanishes, and the full weight of a giant star comes down on a core that can no longer hold it. What happens next happens faster than you can think the word. The iron core, larger than the Earth, collapses in on itself in less than a single second, its outer edge falling inward at up to a quarter of the speed of light. Temperatures and pressures reach levels that have no equal anywhere outside this exact moment. The core is crushed so hard that its atoms break, electrons rammed into protons, until the whole thing becomes something new, a ball of solid neutrons, the densest matter that can exist without becoming a black hole. And then the falling core hits that wall of neutrons and stops dead. And what falls must bounce. The outer layers of the star are still plummeting inward at enormous speed when they slam into that suddenly rigid neutron core and rebound, a shockwave exploding back outward through the infalling star. At the very same instant, the newborn core releases an almost incomprehensible flood of ghostly particles called neutrinos, so many of them, carrying so much energy that even though neutrinos barely interact with anything at all, their sheer torrent helps blast the outer star apart. The collapse becomes an explosion. The dying inward becomes a detonation outward. It all takes seconds. The numbers on that neutrino burst are genuinely hard to believe. In the few seconds of a core collapse, the star releases more energy in neutrinos alone than the sun will emit in its entire 10 billion year lifetime. Something like 99% of the explosion's energy pours out as these near ghostly particles, invisible, passing through the whole star and out into space as if it were not there. The blast of light we actually see, brilliant enough to outshine a galaxy, is the leftover 1%. The real event is a scream of neutrinos we can barely detect at all. The visible result is a fireball on a scale that mocks language. The outer layers of the star, the mass of many suns, are hurled outward at thousands of kilometers a second, tens of millions of kilometers an hour. They expand into a vast, glowing cloud that will keep growing for thousands of years, a supernova remnant, seeding space with the wreckage of the star. And for a few weeks before it fades, that single explosion shines with the light of billions of suns, a beacon that can be seen clear across the observable universe. Human beings have watched this happen and written it down. In the year 1054, Chinese and Arab and other astronomers recorded a new star that suddenly appeared in the sky, so bright it was visible in broad daylight for over 3 weeks, and at night for nearly 2 years, before slowly fading away. Today, if you point a telescope at that exact spot, you find a Crab Nebula, a beautiful tangle of glowing filaments still rushing outward, the shredded corpse of the star those astronomers watched die almost 1,000 years ago. We have the eyewitness report and the body matched across a millennium. The most important one in modern times exploded in 1987 in a small galaxy near our own, and it changed how we watch the sky. Hours before the light of Supernova 1987A arrived, detectors deep underground on Earth caught a tiny pulse of neutrinos, a handful of ghost particles out of the unthinkable flood, the first breath of the explosion reaching us ahead of its own light. For the first time, we had felt a star die from the inside, sensed the collapse of its core directly. It was a strange kind of intimacy to detect the death of a star before you could even see it. Our own galaxy is quiet in this respect, almost suspiciously so. The last supernova clearly seen to explode within the Milky Way was recorded by Johannes Kepler in 1604, and before that Tycho Brahe watched one in 1572, each a new star blazing where none had been. Since then, for over 400 years, nothing. Given how often these explosions should occur in a galaxy our size, we are, statistically, overdue for another. Somewhere out among the massive stars of the Milky Way, a core has quite possibly already collapsed, and the light of it is on its way. And now the story turns, because a supernova is far more than a magnificent act of destruction. That crushing final second and the blazing explosion that follows is a forge. The pressures and temperatures are so extreme that they slam lighter atoms together into the heaviest elements, the ones that could never form in the calm core of an ordinary star. Gold, silver, uranium, iodine, and the explosion then flings all of it out into space, scattering the newly minted elements across light years, seeding the galaxy with the raw material of future worlds. Follow that scattered material forward in time, and it settles into clouds, and those clouds collapse into new stars and new planets. And some of those planets have iron cores and liquid water and, eventually, life. The iron in the blood moving through your body right now was made in the heart of a dying star. The calcium in your bones, the oxygen filling your lungs, the carbon that forms the backbone of every molecule in you. All of it was forged inside stars, and much of it was scattered by the violence of supernovae, long before the sun was ever born. This is not a poem, whatever it sounds like. It is a literal biography of the atoms that make you. You are, in the most exact and physical sense, assembled from the debris of dead stars. Every person you have ever loved is a temporary arrangement of stardust that a series of ancient explosions happened to scatter into this corner of space. The same event that ranks among the most annihilating forces in all of nature, that can sterilize everything for light years around it, is also the only thing in the universe that could have made the material of a human being. Creation and destruction in the supernova are the very same act. Sit with that contradiction, because it is the heart of this chapter. The thing that builds you is the thing that could unmake you. There is no gentle version of a supernova, no benevolent forge that hands out gold without also being able to erase a nearby world in an afternoon. The universe does not separate its creation from its violence. It uses the same furnace for both. The atoms of your body carry the fingerprints of catastrophes so enormous they briefly outshone whole galaxies, and you would not be here without a single one of them. And that raises an uncomfortable question. If a supernova can seed life across light years, what does it do to anything that happens to be too close when it goes off? The answer is grim. A supernova within a few dozen light years of Earth would be a catastrophe, flooding our world with radiation, stripping the ozone, and quite possibly triggering a mass extinction. We do not think one is due nearby anytime soon. Betelgeuse, when it goes, is safely distant. But the galaxy is crowded with massive stars, and being near one when it dies is a fate you would not survive. There is an event in the universe so violent that it makes a supernova look restrained. It is the single most powerful kind of explosion since the birth of the cosmos itself. In a matter of seconds, it releases more energy than the sun will produce in its entire lifetime, and it does not spread that energy out politely in all directions. It focuses it into a narrow beam and fires it across the galaxy like a rifle shot. We call it a gamma-ray burst. And the truly frightening thing is that if one were aimed at Earth, we would not see it coming, because it travels at the speed of the very light that would warn us. For decades, we did not even know these things existed, and when we found them, it was by accident while watching for something else. In the 1960s, at the height of the Cold War, the United States launched a fleet of satellites called Vela to watch for the gamma rays a secret nuclear test would produce. The satellites did detect gamma ray flashes, but they were coming from the wrong direction. They were not coming from the Soviet Union or from anywhere on Earth. They were coming from deep space, from far outside the galaxy, and no one had any idea what could possibly make them. It took years to understand, and the answer was almost too much to accept. A gamma ray burst is what happens, in one version, when a truly massive star, far bigger than the ones that make ordinary supernovae, collapses at the end of its life, and its core falls straight into a black hole. As the star implodes, it flings two colossal jets of matter and radiation outward from its poles, moving at very nearly the speed of light. Those jets punch out through the star and race into space, and where they are pointed, they carry an almost unthinkable concentration of energy. Astronomers sometimes call the star that produces one of these a hypernova, and the name is earned. It is a supernova, and then some, an explosion tens of times more energetic than an ordinary stellar death, wringing out every last drop of a giant star's collapse and channeling much of it into those two beams. Where a normal supernova throws its energy away in every direction, a hypernova hoards it, aims it, and fires. It is the difference between a grenade and a bullet. And the bullet, in this case, can cross a galaxy. The concentration is the whole point and the whole horror, because a gamma ray burst does not shine in every direction like a normal star or even a supernova. Its energy is squeezed into those narrow beams, perhaps only a few degrees wide. That focusing is what makes it so absurdly bright along its axis. And it means that from any given burst, only the tiny fraction of the universe lying directly in the path of one of those beams ever receives the shot. Everyone else sees nothing. The burst is a searchlight in the dark, and you only exist in its story if it happens to sweep across you. The bursts themselves are brief, which somehow makes them more unnerving. Some last only a few thousandths of a second, others a minute or two, a spasm of gamma rays, and then silence. But each one is followed by an afterglow, a fading wash of X-rays and visible light as the jet plows into the gas around the dead star. And is that afterglow hunted down by fast-moving telescopes within minutes? That lets us pin down where in the universe the shot came from. A flash lasting seconds from an event that ended a star, glimpsed billions of years after the fact. There's a shorter, quicker kind of burst as well, and it comes from a different catastrophe entirely, one we will return to soon. When two dead stars, two neutron stars, spiral together and collide, the collision fires off its own brief gamma ray burst, over in less than 2 seconds. Long or short, the mechanism differs, but the result is the same, a beam of gamma radiation so intense it can be seen from clear across the observable universe, from explosions that happened when the cosmos was a fraction of its current age. And these bursts are unimaginably far away, which is the only reason we can study them in comfort. The typical gamma ray burst goes off billions of light years from Earth, in some distant galaxy, and even at that colossal distance, our instruments light up. Think about what that means. We are detecting easily an explosion so far away its light has been traveling toward us for most of the age of the universe. Anything capable of being that bright, that far off, is carrying a violence that does not belong to the same category as anything we have discussed so far. In October of 2022, we got a demonstration that these things can reach out and touch us, even from unthinkable distances. A gamma ray burst arrived at Earth so powerful that astronomers nicknamed it the brightest of all time. It came from about 2 billion light years away, an ocean of distance, and yet when its radiation swept over the Earth, it disturbed our planet's upper atmosphere, ionizing the ionosphere, the effect measurable by instruments on the ground. A dying star 2 billion light years away reached across the visible universe and left a mark on the air over our heads. And it was not even aimed straight at us. So the obvious question is what a nearby one would do. And here the comfort ends. If a gamma ray burst went off within a few thousand light years of Earth, still an enormous distance, and one of its beams was pointed our way, the effect would be devastating. The blast of gamma radiation would tear apart the ozone layer in a matter of seconds, the shield that protects all life from the sun's ultraviolet light. With the ozone gone, that ultraviolet flood would pour down onto the land and into the oceans, killing the base of the food chain and, quite possibly, most of the life on the planet. This is not merely a thought experiment. There's a real suspect. Remember the Ordovician extinction, more than 400 million years ago, that emptied the ancient seas. One serious hypothesis holds that it was triggered by exactly this, a gamma ray burst somewhere in our galaxy, its beams sweeping across the young Earth, stripping the ozone and unleashing a lethal wave of radiation onto a world that had barely begun to live. We cannot prove it, but it fits, and that is enough to keep the possibility alive that one of the great extinctions was a sniper shot from a dying star. The strangest part of this whole danger is the matter of aim, or the lack of it. A gamma ray burst does not seek anything out. It does not target. It simply fires its beams along whatever axis the dying star happens to be spinning on, blindly, into the dark. The overwhelming likelihood is that any given burst points nowhere near us. But that is luck, not safety. There is no protection, no defense, no early warning. There's only the geometry of where a distant star's poles happen to be pointing, and whether, by pure chance, one of them lines up with the Earth. And we do have candidates to keep us honest, stars in our own galaxy that could one day produce such a burst. The most talked about is a system called WR104, a rapidly spinning massive star around 8,000 light years away, exactly the kind that can collapse into a gamma ray burst. For a while, some observations suggested that its spin axis, and therefore its potential beam, might be pointed close to the direction of Earth. Later work has softened that worry considerably. But the very fact that we can point at a specific star and ask, seriously, whether its barrel is aimed at us, tells you something about the universe we live in. There is a particular flavor of dread here that none of the earlier chapters quite reached. An asteroid we might see coming. A supernova builds up over time, and its danger arrives spread out and diluted. But a gamma ray burst gives no warning at all, because the burst itself travels at the speed of light. The gamma rays and the visible flash arrive together in the same instant. There is no flicker in the sky beforehand, no signal running ahead to say it is on its way. If it ever came for us, the first sign and the last sign would be the same, and by the time you registered it, the damage would already be done. So a gamma ray burst is a weapon that needs no aim, only alignment. It is fired blindly across the galaxy by stars that do not know we exist, and it will either miss us by an enormous margin, as it almost certainly will, or it will not, and we will never see the difference until it is over. It is the purest form of fear that runs through all of astronomy, the fear of the thing you cannot detect, cannot dodge, and cannot answer. A shot in the dark from a shooter with no eyes in a room the size of the universe. A teaspoon of it would weigh more than a mountain. Scoop up a single spoonful of this stuff and it would tip the scales at billions of tons, more than the combined weight of every human being alive. It is the crushed core of a dead star, and it is the densest object in the universe short of a black hole. But density is not even the frightening part. The frightening part is that these corpses are not inert. They are still active, still spinning, still armed. And in 2004, one of them, from halfway across the galaxy, reached out and physically struck the Earth. To make one, you go back to the supernova. When a massive star collapses, if it is not quite heavy enough to form a black hole, its core is crushed into something else, a neutron star. All the gravity that was trying to make a black hole succeeds in doing something almost as extreme. It rams the electrons and protons of the core together into pure neutrons, packing them as tightly as the particles inside an atomic nucleus. An object with more mass than the sun is squeezed down until there is no empty space left in it at all. What remains is not really a star anymore. It is a single, city-sized atomic nucleus. The numbers on that density break the mind a little. In a normal atom, almost all of it is empty space. The nucleus, a tiny speck with the electrons far away. A neutron star is what you get when you crush out all that emptiness, when you take the matter of an entire sun and remove the gaps. The result is so dense that if you could somehow hold a sugar cube of it, that little cube would weigh as much as a mountain or as the whole of humanity stacked together. It is matter compressed to the absolute limit of what matter can bear. And all of that is packed into something astonishingly small. A neutron star holding more than the mass of our sun is only about 20 kilometers across, the size of a city. You could drape it over a large town. It would fit inside the ring road of a modern metropolis. Standing on its surface, if you could exist there for even an instant, the gravity would be around 100 billion times what you feel on Earth. You would not be crushed. You would be smeared, spread across the surface in a layer single atom thick, before you had time to finish the thought. What is inside a neutron star may be the strangest matter in existence, and we genuinely do not fully know. Under such crushing pressure, the neutrons near the surface are thought to arrange themselves into bizarre shapes that physicists, with rare humor, have named nuclear pasta, sheets and tubes stronger than steel by a factor no ordinary material approaches. Deeper down, no one is certain what the matter becomes, whether it stays neutrons or dissolves into something we have no name for. The heart of a neutron star is a laboratory running an experiment we cannot reproduce and cannot see inside. These objects were first found not by seeing them, but by hearing them tick. In 1967, a young astronomer named Jocelyn Bell, working in Cambridge, noticed a strange, absurdly regular pulse of radio waves coming from one spot in the sky, a beat so precise it repeated every 1/3 seconds, steady as a metronome. Nothing natural was supposed to be that regular. For a short, thrilling while, the researchers half-joked that it might be a signal from another civilization, and they labeled it LGM for Little Green Man. It was not aliens. It was something almost stranger. What she had found was a pulsar, a spinning neutron star. As these corpses spin, they fire beams of radiation out of their magnetic poles. And if one of those beams happens to sweep across the Earth with each rotation, we see a pulse like the flash of a lighthouse. And they spin fast. A neutron star can rotate dozens, even hundreds of times every second, an object heavier than the sun and the size of a city, whirling so fast its surface moves at a good fraction of the speed of light. The regularity that fooled us into thinking of aliens was just the ticking of the fastest, heaviest flywheel in nature. The precision of that ticking is almost eerie. Some pulsars keep time so reliably, spinning so steadily, that they rival the best atomic clocks human beings have ever built. We can predict their pulses years in advance, down to fractions of a millionth of a second. A dead star, crushed beyond recognition, flung out by a stellar explosion, keeps better time than almost anything in your house. And they're scattered all through the galaxy, thousands of them, silently sweeping their beams around and around, some of them ticking away since before there were mammals on Earth. But among the neutron stars, there is a rarer, angrier breed, and this is where the real menace lives. A small fraction of them are born with magnetic fields of monstrous, almost unbelievable strength. We call them magnetars, and their magnetic fields are the most powerful known to exist anywhere in the universe. Trillions of times stronger than the Earth's, thousands of times stronger than an ordinary neutron star's. The magnetism is so intense, it warps the very shape of the atoms near the surface. If it has a peer for sheer physical extremity, it is only the black hole. The field of a magnetar is not an abstraction. It is lethal at a distance that has to be described to be believed. Come within about 1,000 kilometers of a magnetar, and its magnetic field would be strong enough to kill you, not by any force you could feel, but by distorting the electron clouds of every atom in your body, disrupting the chemistry that holds you together. Your cells would simply stop working. You would be unmade by magnetism alone, dissolved at the molecular level, while still hundreds of kilometers from ever touching the thing. No creature could survive within reach of one. And these magnetars are not stable. Their colossal magnetic fields are under such strain that sometimes the crust of the star, its solid outer shell, cracks and shifts, a starquake, releasing a spasm of energy in an instant. Most of the time, these are minor flickers. But on rare occasions, a magnetar lets go of a giant flare, the most energetic magnetic event known, and one of those on the 27th of December in 2004 gave us a demonstration none of us will forget from a magnetar called SGR 180620 on the far side of the Milky Way. That magnetar sat roughly 50,000 light-years away from Earth, on the opposite side of the galaxy's crowded center, about as far as an object in our own galaxy can be. Distance, you would think, should have made it harmless. It did not. In 0.2 of a single second, that giant flare released more energy than the sun pours out in 250,000 years. In 1/5 of a second, it was for that instant the brightest object in the sky beyond the solar system, brighter in gamma rays than the full moon, from 50,000 light-years away. And then it reached us. When the wavefront of that flare arrived at Earth, after crossing 50,000 years of space, it was still strong enough to physically affect our planet. It slammed into the outer atmosphere and ionized it, compressing the Earth's magnetic field and disturbing the ionosphere, the same upper layer our radio signals bounce off. Instruments in orbit were briefly blinded. A dead star on the far side of the galaxy, twitching once, reached across an almost inconceivable gulf and left its fingerprint on the air above our heads. That has happened. It is not a hypothetical. Pause on the strangeness of that. We tend to think of the dead as finished, as spent, as past being able to hurt anyone. The universe disagrees completely. These stars are already dead. They exploded long ago, and yet their crushed corpses remain among the most dangerous single objects we know of, spinning, blasting radiation, wrapped in fields that could dissolve you from 1,000 kilometers, occasionally reaching clear across the galaxy to touch a planet they will never know exists. Death, for a star, is not the end of its power. Sometimes it is the beginning of it. There is a thought here that connects to everything still ahead. We have been climbing a ladder of density and violence, from ordinary matter to the crushed cores of dead stars, and each rung has been more extreme, more indifferent, more alien than the last. The neutron star sits near the top of that ladder. There's only one rung above it, one thing denser and stranger and more final than a neutron star. But before we reach that, there is one more scene the corpses have to show us, and it is the one where two of them meet. On the 17th of August, 2017, for the first time in history, human beings did more than see a cosmic catastrophe. We felt it. Two dead stars on the far side of the galaxy, 130 million light-years away, finished a slow dance that had lasted longer than there have been animals on Earth, and crashed into each other. And the shock of that collision reached us as light, and also as a tremor in the fabric of space itself, a wave that stretched and squeezed every object it passed through, including the Earth, including you, as it rolled across the planet. The two objects were neutron stars, the crushed corpses we just met, each heavier than the sun and only a city wide. They had been born from separate supernovae, and instead of drifting apart, they had fallen into orbit around each other, two dead things circling in the dark. And they were doomed to meet, because a pair of objects that heavy, whirling around each other, does something strange to the space around them. It stirs it, it sends out ripples, and those ripples carry energy away, so the two stars slowly, inexorably, spiral closer. This is not a quick death. Two neutron stars can circle each other for hundreds of millions, even billions of years, spiraling in so gradually that for almost all of that time, nothing seems to be happening at all. But it is Every orbit sheds a whisper of energy into gravitational waves, and every whisper tightens the orbit fraction. The pair falls closer over the eons, orbiting faster, radiating harder, until in the final seconds the whole slow catastrophe suddenly runs away with itself, and a dance measured in geological ages ends in a single heartbeat. The idea that space itself can ripple goes back to Albert Einstein, who predicted it in 1916 as a consequence of his theory of gravity, and then spent years doubting his own prediction. In his picture, space and time are not an empty stage on which events play out. They are a single flexible fabric, space-time, that bends and warps in the presence of mass. And if you take a heavy object and shake it violently enough, it should send waves rippling outward through that fabric at the speed of light, like ripples spreading on a pond. He thought we would never be able to detect them. They were far too faint. He was almost right about that. A gravitational wave, as these ripples are called, is a stretching and squeezing of space itself. As one passes through you, the distance between everything, every atom in your body, the whole room, briefly grows a little longer in one direction and shorter in the other, then snaps back. It is not a wave moving through space. It is a wave of space, but the effect is unbelievably tiny. Even a wave from a colossal cosmic collision, by the time it reaches Earth, changes distances by less than the width of an atomic nucleus. Detecting that seemed, for a century, completely impossible. And then, in September of 2015, we did it. A pair of enormous instruments in the United States, together called LIGO, finally caught a gravitational wave rolling through the Earth. It had come from two black holes, far out in space, spiraling together and merging into one. For the first time, humanity had directly sensed a ripple in space-time, confirming what Einstein had scribbled down a century earlier and doubted ever since. It was one of the greatest scientific achievements in history, and it opened an entirely new way of perceiving the universe, not with light, but with the trembling of space itself. The sensitivity of LIGO is hard to overstate and worth pausing on because it borders on the absurd. Each detector is a pair of tunnels, each 4 kilometers long, with laser beams bouncing along them. To catch a gravitational wave, LIGO must measure a change in the length of those tunnels smaller than 1/10,000th the width of a single proton. It is like measuring the distance to a faraway star and detecting a change the width of a human hair. That is the scale of delicacy required to feel the universe shake. And in 2017, that impossible instrument caught something new. This time, the wave was different. It was longer, and it climbed in pitch, a rising whine lasting not a fraction of a second, but nearly 100 seconds, sweeping upward as the two objects whirled faster and faster. This was not two black holes. It was the two neutron stars in the final throes of their death spiral, circling each other hundreds of times a second, closer and closer, up to the very last moment before impact. Astronomers can turn that signal into sound, and when they do, it ends in a rising chirp, the actual song of two dead stars about to collide. Picture the final instant. Two objects, each with more mass than the sun, packed into a ball the width of a city, slamming together at a good fraction of the speed of light. The collision is so violent that it briefly forms a single, wildly spinning, hyperdense object and possibly, in the very next moment, collapses it into a black hole. In that instant, the merger releases a burst of energy that outshines everything around it, a flash of gravitational waves, gamma rays, and hot ejected matter. The two dead stars annihilating each other in a spasm that reshapes the space around them. But the truly historic thing about that August night was what came next, less than 2 seconds later. As the neutron stars finally merged, a satellite in orbit, watching for gamma rays, caught a short burst of them from the very same patch of sky, arriving just under 2 seconds after the gravitational wave. There it was. The two neutron stars colliding had produced a gamma ray burst, the very kind of kill shot we spoke of, and we had felt the collision and seen its flash almost together. Two completely different messengers, gravity and light, from a single event, arriving nearly hand in hand. What followed was one of the great scrambles in the history of science. Within hours, the alert went out, and telescopes all over the world and in orbit swung toward that corner of the sky, racing to catch the light of the collision before it faded. And they found it, a new point of light in a distant galaxy, glowing where nothing had been before. For the first time ever, we were watching the aftermath of a neutron star collision in real time, in every kind of light we could gather, guided there by the tremor it had sent through space. The glow they found has a name that undersells it, a kilonova. As the two neutron stars tore each other apart, they flung out a cloud of their own ultra-dense matter. And in that superheated debris, the heaviest elements in the periodic table were forged in an instant. This is the other great factory alongside the supernova, where the universe makes its heavy elements. And in the days that followed, the fading colors of that kilonova told the astronomers exactly what was being made in the wreckage. The answer was staggering. That single collision manufactured gold. Not a little. The merger is estimated to have forged something like several times the entire mass of the Earth in gold alone, along with platinum and other precious metals, all created in seconds and blasted out into space. Every wedding ring, every gold coin, every scrap of the metal humans have fought and died over for all of history was made this way in the collision of dead stars long before the Earth existed. The most precious thing we know is quite literally the shrapnel of a catastrophe between two corpses. Step back and consider what that one night in 2017 actually meant. We had confirmed, beyond any doubt, that space and time are not a fixed and empty backdrop. They're a physical thing, a medium, a fabric that can be stretched, that can carry waves, that can ring like a struck bell when something violent enough happens. We had heard the universe vibrate, the ground of all reality, the stage on which every event we have discussed takes place, turn out to be not solid ground at all, but something closer to a taut, trembling surface. And that changes the character of everything that comes next. Up to now, the frightening things have been objects, rocks, stars, corpses, all of them things inside space, things that move through the fabric. But if the fabric itself can bend and ripple and stretch, then a new kind of question opens up. What happens if you bend it too far? What if you take that fabric and pull it, warp it, deform it so violently that it does not spring back, but tears or folds in on itself, or pinches off into a place from which nothing can ever return? That is not a hypothetical. It is the next thing we have to face, and it is the deepest wound the universe can inflict on itself. Everything so far in this story could kill your body. What comes next does something far stranger than death. It removes you from the universe entirely, past a line you can cross in only one direction, into a place where the very ideas of space and time break down. We have spent this whole movement among the furnaces. Now we arrive at the holes they leave behind. There are places in this universe where if you wanted to leave, you would have to travel faster than light. And since nothing can travel faster than light, the meaning is absolute and total. You cannot leave. Not you, not your ship, not a radio signal, not a single photon of light, not ever. These are the black holes, and they're the closest thing physics has to a genuine trap, a boundary you can cross going in and never, under any circumstances, cross coming back out. Everything else in this film could kill you. A black hole does something worse. It keeps you. To understand why, start with something ordinary, a ball thrown into the air. Throw it gently, and it falls back. Throw it harder, and it climbs higher before falling. Throw it hard enough, and it never comes back at all. It escapes into space. For Earth, that speed, the escape velocity, is about 11 kilometers a second. Every world and every star has one, a speed you must beat to break free of its gravity forever. The bigger and denser the object, the higher that speed climbs. and there is nothing in the laws of physics that says it has to stop below the speed of light. So imagine cranking gravity up. Take an object and make it denser and denser, packing more mass in a less space, and the escape velocity at its surface rises and rises. Compress the sun down to a ball a few kilometers across, and the speed you would need to escape its surface would reach 300,000 kilometers a second, the speed of light itself. Push even a hair beyond that, and you have crossed a threshold that changes everything. Now, not even light is fast enough to get away. And once light cannot escape, nothing can. The boundary where this happens is called the event horizon, and it is the defining feature of a black hole. It is not a wall. It is not a surface you could touch. It is a line drawn in empty space, a place where the geometry tips over, marking the point of no return. Outside it, with enough speed, escape is still possible. Cross it, even by a hair, and every possible path, every direction you could move, now leads inward toward the center. The way out simply ceases to exist, not because it is blocked, but because there is no longer any such direction as out. That last idea is worth sitting with, because it is where intuition fails. Inside the event horizon, moving toward the center is not a choice you could resist with a powerful enough engine. It becomes as inevitable as the passage of time. Just as you cannot stop tomorrow from coming, you could not stop yourself from falling deeper, because the warping of space and time is so severe that the center lies in your future, the way next week lies in yours. There is no thrust, no cleverness, no force that helps. Every road leads down. Falling becomes simply what the future is. And whatever crosses that line is gone from our universe for good. No information, no light, no signal can climb back out to tell us what happened inside. The event horizon is a perfect one-way membrane, a place where the outside world loses all further contact with whatever fell in. It is, in the most literal possible sense, an edge of the observable universe, a surface beyond which our reality simply has nothing more to say. Whatever is in there is as unreachable to us as the far side of the end of time. Where do these traps come from? We have already watched one being born. When a star far more massive than the sun dies, and its core is too heavy to hold itself up even as a neutron star, nothing can stop the collapse. Gravity wins completely. The core falls inward without limit, past neutron density, past every barrier, crushing itself down toward a single point, and it wraps an event horizon around itself as it goes. The furnace burns out, the light goes dark, and what is left is a hole in space where a star used to be. Black holes come in a startling range of sizes, and the small ones are, in a way, the most unsettling. The rule is that the more mass you cram past the threshold, the bigger the event horizon. Compress the entire sun into a black hole, and its horizon would be only about 3 kilometers across, a dark sphere you could drive around in an afternoon. Compress the Earth, and it would be the size of a marble. All the mass, all the gravity, unchanged but folded into a point and cloaked in a horizon smaller than a coin. Density beyond anything the mind can hold. By their nature, black holes are invisible. They emit no light because light cannot escape them. Against the black of space, a black hole is blacker still, a hole in the darkness. For most of the history of the idea, this made many scientists doubt they were real at all. How do you find something whose entire defining trait is that it cannot be seen? For decades, a black hole was a monster known only by rumor, a solution to Einstein's equations that even Einstein himself suspected nature would never actually build. We find them, in the end, by what they do to everything around them. A black hole cannot hide its gravity. We see stars whipping around an invisible point at enormous speeds, orbiting nothing visible. We see gas heated to millions of degrees as it spirals in, screaming in X-rays before it disappears. We see the telltale distortion of light bending around an unseen mass. The monster is invisible, but its handprints are everywhere, and by reading those handprints, astronomers built an overwhelming case that these things are real and common and near. Then, on the 10th of April, 2019, we finally saw one. Not the black hole itself, which can never be seen, but its silhouette. A global network of radio telescopes, working together as a single instrument the size of the Earth, called the Event Horizon Telescope, had spent years staring at a supermassive black hole in a distant galaxy. And they produced an image, blurry, orange, unmistakable. A ring of glowing gas, and at its center, a round patch of perfect darkness. The shadow of a black hole, cast against the light of everything falling into it. That patch of darkness was the event horizon of a monster in a galaxy called M87, some 55 million light-years away. And it is worth understanding what you were looking at in that image, because it is almost too much. That single black hole contains about 6.5 billion times the mass of our Sun. Its event horizon is larger than our entire solar system. You could pour every planet, the Sun, and all the space between them into it, and it would barely register. And it was the very first one we ever laid eyes on. The image landed with a strange weight, and it is worth naming why. For a century, black holes had lived in equations and imagination, more idea than object. Suddenly here was a photograph, direct proof that these things are out there, that the point of no return is a real place with a real edge, that somewhere 55 million light-years away is a boundary across which a whole galaxy's worth of matter has fallen and will never return. The trap was no longer theoretical. We had its picture on the front page of every newspaper on Earth. What makes a black hole different from every danger we have discussed comes down to a single word, and the word is forever. An asteroid impact ends. A star's death, however vast, plays out and finishes. But a black hole is not an event. It is a permanent condition, a piece of the universe from which the exit has been deleted. Whatever falls and is not destroyed in the ordinary sense, not scattered like a supernova's ashes to become something new. It is removed, sealed away, held beyond the reach of everything else that will ever happen. It is the first truly irreversible thing. We're not built to feel that, not really. Everything in human experience is, in principle, reversible or at least recoverable. Broken things can be mended or mourned or replaced. Even death leaves a body, a memory, an echo in the world. A black hole offers none of that. It is a clean, absolute subtraction from reality, a place where things go to stop existing for the rest of the universe, with no remainder and no return. To stand at the edge of one would be to stand at the edge of the only true forever there is. But standing at the edge is not the same as falling in. And the fall itself, it turns out, is stranger than the destination. Because as you drop toward a black hole, two completely different things would happen at once, one to your body and one at a time. What you would experience and what someone watching from a safe distance would see are so wildly different that they seem to describe two separate events. One of you would be stretched into a thread of atoms. The other would hang at the edge, frozen, dimming for all eternity. Suppose you decided to find out for yourself. You climb into a ship pointed at a black hole and fall. What happens to you next depends entirely on who is telling the story, because the fall into a black hole is not one event. It is two, and they contradict each other completely. In one version, the one you would live, you're stretched into a thin thread of screaming atoms. In the other, the one your friends watching from safe distance would see, you slow down, turn red, freeze at the edge, and hang there, dimming for the rest of eternity. Both are true. That is the problem. Let us take your version first, the one your own body would experience, and it is grim in a very physical way. As you fall toward a black hole, you fall feet first. Let us say, and your feet are closer to it than your head. Gravity is stronger the closer you are, so your feet are pulled harder than your head. On Earth, this difference is far too small to feel. Near a black hole, it becomes monstrous. The pull on your feet grows so much stronger than the pull on your head that it begins to stretch you. Physicists, who are not always solemn, gave this process a faintly ridiculous name: spaghettification. As you fall deeper, the difference in gravity between your feet and your head grows without limit, and you're drawn out longer and thinner like a strand of pasta, or like taffy pulled between two hands. At the same time, you're squeezed from the sides, funneled inward. Your body becomes a thread. Then the thread becomes a stream of individual atoms. You're not crushed so much as pulled apart, stretched into a line of particles falling toward the center. And it would be fast, and it would be silent. There is no air near a black hole to carry a scream, and the fall happens at a good fraction of the speed of light. By the time the tidal forces grew strong enough to truly matter, you would have only seconds or less of awareness left. The last thing your eyes might register before you're drawn out into a thread is the sky around the black hole warped into a bright, distorted ring, the entire universe behind you bent and smeared into a glowing halo around the darkness ahead. Then the stretching, and then nothing. When this happens depends on the size of the black hole. And here is a genuinely strange twist. For a small black hole, one made from a single star, the tidal forces are so fierce that you would be spaghettified while still well outside the event horizon, torn apart before you ever cross the point of no return. But for a truly enormous black hole, a supermassive one, the gravity changes so gradually at the horizon that you could cross it and feel absolutely nothing. No video, no yod. You would sail across the most important boundary in the universe without the slightest sensation that anything had changed. Think about what that means. You could pass the event horizon of a giant black hole, cross the line beyond which return is impossible, and not even know you had done it. The sky above you would still shine. Your instruments would read nothing unusual for a while. You would be, by every law of physics, already doomed, already sealed off from the universe forever, and it would feel like nothing at all. The most irreversible step you could ever take, and there's no marker, no gate, no moment where you feel the door close behind you. It has simply already closed. The black hole at the center of our own galaxy, Sagittarius A star, is one of these gentle giants. It holds 4 million times the mass of the sun, and its horizon is so large that you could cross it, in principle, and still have time, by your own watch, to look around at the warped and glittering dark before the center claimed you. It is 26,000 light years away, far too distant to threaten us. But it is there right now, a real door in the middle of the Milky Way, and everything I am describing is what would truly happen if you reached it. Now switch to the other story, the one seen by someone watching you fall from a safe distance, because their view of your fall is utterly different, and this is where time itself comes apart. Near a black hole, gravity does more than pull on matter. It warps time. The closer you get to the event horizon, the slower your time runs compared to the watcher far away. Not as an illusion, not as a trick of the light, but really, physically. Your seconds stretch longer and longer as measured by them. And as you approach the horizon, that stretching runs toward infinity. So here is what your distant friend actually sees. As you fall, you appear to move slower and slower. Your ship's clock, if they could read it, ticks more and more sluggishly. You do not plunge across the horizon. Instead, you seem to ease toward it, decelerating, approaching, but never quite arriving. To the outside universe, you never cross the event horizon at all. You slow to a crawl, then to a near stop, hovering forever at the very edge, an image frozen at the threshold, while from your own point of view you fell straight in ages ago. And as you appear to freeze, you also fade. The same warping of time stretches out the light coming from you, dragging its color toward the red, then the infrared, then beyond, until it dims past the point of detection. Your frozen image at the edge grows darker and redder and fainter, second by second, but never quite vanishes, in theory lingering there, smeared across the horizon, dimming toward black for the rest of time. Everyone you ever knew would see you not as gone, but as a fading smudge stuck forever at the edge of the dark. These two truths cannot both be a single simple story. and yet both are correct. You fall in quickly and fatally in a matter of moments by your own clock, and you never fall in at all, hanging at the edge forever by the clock of the outside world. There is no contradiction in the mathematics. There is only a violent collision with our intuition, which insists there is one universal now, one shared time, ticking for everyone. A black hole proves there is not. Time is local. Time is negotiable. And near the horizon, it stops meaning what we thought it meant. None of this comes from imagination or loose speculation. It falls straight out of the mathematics of general relativity, worked out over a century ago, tested again and again, and never once found wrong. The frozen image, the infinite stretching of time, the impossibility of ever watching something cross the horizon from outside, all of it is written into the same equations that guide our spacecraft and keep the satellites in your phone honest. This is not a ghost story. It is arithmetic, and the arithmetic says that near a black hole, time and space trade places and the ordinary rules dissolve. There's a stranger consequence still, one that reaches beyond your own death. Because time near the horizon runs so slowly compared to the wider universe, an observer falling toward a black hole could, in principle, see the outside cosmos speed up. Look outward as you approach the edge, and you might watch stars racing through their lives, galaxies wheeling and colliding, the entire future history of the universe playing out above you, faster and faster, compressed into your final moments. You would fall into something stranger than a hole in space. You would fall into a kind of fast forward on all of eternity. Whatever your fall looks like from outside, from your own vantage, it does end, and it ends at the center. Beyond the horizon, drawn inexorably inward, you would rush toward the point at the heart of the black hole, where all the matter that ever fell in is gone. And this is where the strangeness stops being merely about time and bodies, and becomes something far deeper, because at the center of a black hole, according to our very best theories, is a place where the laws of physics themselves stop working. We will get there, but first there's a crisis to face at the edge. Because everything I have just described, the freezing, the fading, the smeared image at the horizon, hides a contradiction so severe that it has nearly broken modern physics. If your image and all the information about you appears to stay frozen at the horizon forever, then in some sense your information is still there, still part of our universe, pressed against the edge. But black holes, it turns out, do not last forever. They slowly evaporate. And when a black hole finally disappears, the question of what happened to everything that fell and becomes a paradox that our two greatest theories of reality answer in flatly opposite ways. That paradox is where our story reaches its turning point. Up to now, everything terrifying has been a matter of danger, things that could destroy your body, your world, your species. From here on, the fear changes shape entirely, because a black hole threatens far more than your life. It threatens something we did not even know could be threatened. It threatens the idea that reality has to make sense at all, and no one, not the smartest minds alive, can yet explain the contradiction it has opened. For most of this film, the word terrifying has meant something simple. It can kill you. From this chapter onward, it means something else, something worse, and there is no going back to the old meaning once you have felt this one. Because black holes appear to be doing something that our deepest, most trusted laws of physics say is flatly, absolutely impossible. They appear to be erasing information from the universe. And when the best minds who have ever lived try to explain how that can be, they find that their two greatest theories of reality call each other liars. This is the hinge of the whole story, so let me say plainly what has changed. Until now, the horror has been about danger, about the countless ways the cosmos can end a life or a world. That horror was at least comprehensible. A rock, a beam, a fire, a fall. But what a black hole threatens is stranger and, in a way, more disturbing than death. It threatens coherence. It threatens the quiet assumption underneath everything, the assumption that reality follows consistent rules, that the universe is at bottom a place that makes sense. And that assumption is exactly what is now in doubt. The trouble began, fittingly, with Stephen Hawking. In 1974, working out the consequences of quantum physics near a black hole, he discovered something that shocked even him. Black holes are not perfectly black. They glow very faintly. Down at the event horizon, the strange rules of the quantum world cause a black hole to leak a slow, dim trickle of radiation into space. It is unimaginably weak for a large black hole, far too faint to ever detect directly. But it is real, and it changes everything, because it means a black hole is not eternal. The mechanism is subtle, and any short description is a caricature. But here is the flavor of it. Empty space, according to quantum physics, is not truly empty. It seeds with pairs of particles constantly flickering into existence and annihilating again, borrowed briefly from nothing. Normally, they vanish as fast as they appear. But right at the edge of a black hole, occasionally, one of a pair falls across the horizon while the other escapes. The escaping particle carries away a tiny scrap of the black hole's energy. Bit by bit, particle by particle, the black hole pays for this and slowly shrinks. So black holes evaporate. Given enough time, a black hole does not last forever. It radiates its mass away into that faint glow, growing smaller and smaller over spans of time that dwarf anything we have discussed. But the direction is clear. Left alone in an empty universe, every black hole will eventually dwindle and dwindle, and at the very end, wink out entirely. The most permanent, most irreversible object in the cosmos turns out to have an expiration date after all. And that fact, which sounds almost hopeful, is where the nightmare begins. The timescales are absurd and worth stating just to feel them. A black hole the mass of the sun would take something like 10 to the 67th power years to evaporate, a 1 followed by 67 zeros. The supermassive giants take far longer still, up toward 10 to the 100th power years, a length of time so vast that calling it unimaginable is a wild understatement. The universe is only about 14 billion years old. These evaporation times are longer than that by a margin that makes the entire history of the cosmos so far round down to nothing. But they are finite, and finite is the key word. Here is the catch that broke everything. The radiation leaking out of a black hole, that faint Hawking glow, is featureless. It is just heat, thermal noise, the same bland static regardless of what the black hole is made of. It carries no fingerprint, no imprint, no memory of the things that fell in. A black hole that swallowed a library and a black hole that swallowed an equal mass of dead stars would, as they evaporate, give off exactly identical radiation. And when each has fully evaporated, there is nothing left. No black hole, just a puff of anonymous heat drifting in space. To see why that is a catastrophe, you have to understand what physicists mean by information. Not facts in a book, but the precise details of every particle, its position, its motion, its state, the total data that specifies exactly what something is. One of the most fundamental principles in all of physics, older and more trusted than almost anything, is that this information can never truly be destroyed. It can be scrambled, hidden, spread out beyond any hope of reading it, but in principle is always still there, always preserved. The universe, at its deepest level, does not forget. This is not a minor rule. It is woven into the entire structure of quantum mechanics, the theory that governs everything small and has never, in a century of the most precise experiments ever performed, been found wrong. Quantum mechanics insists that if you knew the complete state of the universe right now, you could in principle run the equations backward and recover its exact state at any point in the past. Nothing is ever fully lost. Reality keeps a perfect, unbroken ledger of itself. Erase a single entry, and the whole logic of the theory collapses. And now you can see the collision, and it is head-on. General relativity, Einstein's theory of gravity, says that whatever falls into a black hole is gone, and that the black hole then evaporates in a featureless radiation carrying none of it back. Quantum mechanics says that is impossible, that the information must survive somehow, because information cannot be destroyed ever. Both theories are triumphs. Both have passed every test we have ever devised. And on this one question, the fate of everything that falls into a black hole, they do not merely disagree. They call each other wrong. That is the black hole information paradox, and it is not a puzzle at the edge of physics. It is a wound at the center of it. Two of the most successful ideas in the history of human thought, the two pillars on which all of modern physics rests, produce a direct, flat contradiction, and we cannot yet say which one is lying. Somewhere in our understanding of reality, at the deepest level, there is a mistake, a crack, and a black hole is the place where that crack shows. For half a century, the greatest physicists alive have thrown themselves at it. It is still not resolved. For a while, some hoped the answer would be gentle, that the information quietly seeps out in subtle correlations in the radiation. Then, in 2012, a group of physicists sharpened the paradox into something even worse. They showed that the obvious ways to save the information seem to require something monstrous at the event horizon. Not the calm, unremarkable boundary that relativity promised, the one you could cross without feeling a thing. Instead, a wall of blazing energy, a firewall that would incinerate anything falling in the very instant it arrived. And that leaves an impossible choice, which is why the firewall idea caused such alarm. Either information is destroyed when a black hole evaporates, and quantum mechanics is broken, or a violent firewall sits at every event horizon, and Einstein's principle that the horizon is an ordinary, unremarkable place is broken. One of our two great theories has to give. There seems to be no option that keeps both intact. The universe appears to have backed us into a corner where something we were certain of, something fundamental, simply has to be wrong. Now, I want to be honest, because there has been real progress in recent years. New ideas drawn from the strange mathematics of quantum information have begun to suggest that the information may in fact escape, encoded in ways far subtler than anyone first imagined, that the ledger may be preserved after all. Many physicists are cautiously hopeful, but no one has a complete, agreed, intuitive answer, and the deeper lesson has not gone away. For decades, the smartest people on Earth have known that our picture of reality contains a contradiction and have not been able to fully explain it away. Sit with what that actually means, because this is the turning point of everything. It is not that a black hole is dangerous. It is that a black hole is a place where our description of reality stops being consistent with itself. It is a hole in space, and also in our understanding of what is even allowed to be true. The floor we have been standing on this whole time, the belief that the universe ultimately obeys a single coherent set of rules, has a gap in it. And through that gap, you can see straight down into not knowing. And if the edge of a black hole breaks our theories, the center annihilates them completely, because we have not even reached the worst of it. Fall past the horizon, past the paradox, all the way down to the very heart, and you arrive at a single point where the equations do not merely disagree or grow strange. They return infinity. They give up. They hand back the mathematical equivalent of a scream. That point is called the singularity, and it may be the truest edge of human knowledge there is. We have fallen a long way in this film, but this is the bottom. At the very center of every black hole, our mathematics does something it does almost nowhere else in all of science. It breaks. Feed the equations the conditions at the heart of a black hole, and they do not return a large number or a strange number. They return infinity. And in physics, when your equation hands you infinity, it is not describing reality. It is confessing that it has failed. It is the mathematical sound of a door slamming shut on human knowledge. This place is called the singularity, and it is where all the matter that ever fell into the black hole ends up. Everything, every star, every atom, every scrap of what crossed the horizon is crushed down toward a single point. Not a small region, a point, a location of zero size and according to the plain reading of the equations, infinite density. All that mass, all that gravity, packed into no space at all, is the most extreme condition the universe permits, and it sits hidden at the core of every one of these objects. Try to picture it, and you cannot, which is itself the point. We can imagine something very small, a grain, a speck, an atom. The singularity is not small. It is sizeless. It has been compressed past small, past tiny, past the smallest thing you can conceive, all the way down to a mathematical point with no extent in any direction. Density is mass divided by volume, and when the volume becomes zero, the density becomes infinite, and infinite is not a quantity. It is a symptom. It is what the math says when it no longer knows what it is talking about. Reality may be a little more baroque than a single point. Most black holes spin, and for a spinning black hole, the mathematics predicts not a point, but a ring singularity, an infinitely thin loop of crushed matter. Some solutions even hint at stranger things beyond it, tunnels, other regions, doorways that almost certainly do not survive contact with real physics. The honest summary is that once you pass the horizon, our equations offer a menu of increasingly unhinged possibilities, and we have no way to check which, if any, is true. The interior of a black hole is the least understood real place in the universe. We have seen infinities appear in physics before, and every previous time, they were a sign that our theory was incomplete, that we were missing something. The infinity in a black hole is different only in that we have not yet found the something. It signals loudly that general relativity, the theory that has flawlessly described gravity for over a century, that predicted black holes in the first place, cannot describe its own creation. At the singularity, relativity predicts a place where relativity itself no longer works. The theory writes its own suicide note and hands it to us. The strangeness runs deeper than density, because inside a black hole, space and time change roles. Out here, you can move freely through space, but are dragged helplessly forward through time toward the future. Cross the event horizon, and that swaps. The singularity is not a place sitting at the center that you could steer around or hover above. It becomes a moment in your future, as unavoidable as tomorrow. You do not fall toward the singularity the way you fall toward the ground. You fall toward it the way you fall toward next Tuesday. It is not somewhere you go. It is a time that arrives. That is why nothing can save you once you are inside, no matter how powerful your ship. You cannot avoid a moment in time by steering. There is no thrust that turns you away from the future. Every path, every possible motion, every choice leads to the singularity because it lies ahead of you in time rather than in space. The black hole does not trap you by surrounding you with walls. It traps you by rewriting the geometry so that the exit is in the past and the crushing point is in every possible tomorrow. And we will never see it, not this singularity or any other, and that is not a technological limitation we might one day beat. The singularity is wrapped inside the event horizon, and no light, no signal, no information from it can ever reach the outside universe. Whatever bizarre physics is happening at the center of a black hole is sealed away behind a boundary that nothing can cross outward. The universe has, in effect, drawn a curtain around the one place where its own rules fall apart and hung a sign on it that reads, "You may not look." Physicists even have a name for this hiddenness. They call it cosmic censorship, the apparent rule that nature always cloaks its singularities behind event horizons, never leaving one naked and exposed to view. Whether that rule is truly ironclad is still debated. But if it holds, it means the breakdown of physics at the center of a black hole is not merely hard to observe. It is impossible to observe, in principle, forever by anyone from the outside. The one place that could teach us what lies beyond our current physics is also the one place we are permanently forbidden to see. To describe what really happens at the singularity, we would need a theory we do not have, a theory of quantum gravity, one that unites Einstein's gravity with the quantum physics of the very small. At the singularity, both regimes apply at once. The gravity is overwhelming, so relativity matters. The scale is smaller than an atom, so quantum physics matters. And those two theories, as we have already seen, do not get along. Forced to work together at the heart of a black hole, they produce nonsense, that fatal infinity. We have been trying to marry them for the better part of a century, and we have failed. We do have candidate theories that reach toward quantum gravity, ideas with names like string theory and loop quantum gravity, brilliant, mathematically dazzling attempts to describe what happens where Einstein's picture fails. But after decades of work, none has been confirmed by a single experiment, because the conditions they describe exist nowhere we can reach except inside black holes, where we cannot look. We are in the strange position of holding elaborate maps of a country we can never visit and can never photograph, with no way to tell if any of the maps are right. There's a real chance the infinity is not real. Many physicists suspect that a true theory of quantum gravity would step in at the last moment and smooth the singularity away, replacing that impossible point with something merely extreme but finite, some exotic state of matter crushed to an unthinkable but definite density. Perhaps there is no genuine infinity, only the failure of an incomplete theory. That would be a relief. But even if it is so, we may never be able to confirm it, because the answer is hidden behind a horizon that permits no reply. And that is the particular vertigo of the singularity, worse in its way than the fires and the falls. The problem runs deeper than not knowing what is down there. It is that we may be permanently unable to know that this is not a temporary gap in our science, but a wall built into the structure of reality itself. Most mysteries feel like locked doors we might one day open. This one feels like a door with nothing behind it that we are allowed to reach, a question the universe has arranged so that no answer can ever get back to us. Stare into that long enough, and something shifts in how you see the whole cosmos. We like to believe the universe is knowable, that with enough time and cleverness we could, in principle, understand all of it. The singularity is the universe quietly informing us otherwise. It is a place at the heart of some of the most common objects in the sky, where knowledge simply stops, where the very concepts we use to think, space-time, cause-effect, dissolve into meaninglessness. The abyss here does not even have features to fear. It has the absence of features. It is a blank where reality should be. There is a temptation, faced with all this, to look away, to file the singularity under things too abstract to matter, a mathematical curiosity with no bearing on your life. Resist it just for a moment, because the same collapse that produces this unknowable heart is one of the most ordinary events in the universe. Stars die and make these things constantly. The cosmos is manufacturing regions where its own laws break down as casually as it makes rain. The unknowable is not exotic. It is common, and it is nearby, and the next chapter will show you just how close to home it truly gets. Because these wounds are not scattered thinly at the far edges of creation. They gather at the centers of things. Almost every galaxy we have ever studied has one enormous black hole sitting at its very heart, and the largest of them are so vast they defy the imagination, even after everything we have already seen. Our own galaxy has one. You are at this very moment slowly circling it. And the story of these central monsters is the story of what the universe is actually built around. Look up at the band of the Milky Way on a dark night, that soft river of 100 billion stars, and understand what it is turning around. At the center of our galaxy, and at the center of nearly every galaxy in the universe, sits a single object of monstrous mass, a supermassive black hole. Our own is comparatively modest. Some are so enormous they could swallow our entire solar system whole, not once, but billions of times over. Galaxies are not built around light. They're built around these. Every star you can see is orbiting a throat. The one at the heart of the Milky Way has a name, Sagittarius A star, and for a long time we could only infer that it was there. It sits about 26,000 light-years away, buried behind thick clouds of gas and dust at the galaxy's crowded center, invisible to ordinary telescopes. We could not see it, but we could watch what it did to its neighbors. And what it does to its neighbors gives the whole game away. For decades, two teams of astronomers, one led by Reinhard Genzel and one by Andrea Ghez, tracked individual stars near the galactic center, watching them year after year. And they saw those stars doing something astonishing. They were whipping around a single invisible point at blistering speeds. One star, called S2, races around that point once every 16 years, reaching a top speed of thousands of kilometers a second. Something unseen, something with the mass of millions of suns, was flinging entire stars around like stones on strings. In 2020, that work won the Nobel Prize. It was the closest thing to proof a black hole can offer. From the orbits of those stars, the mass of the hidden object could be weighed with precision, and the answer was staggering. Sagittarius, a star, holds about 4 million times the mass of our Sun, all of it crushed inside a region that would fit comfortably within the orbit of Mercury. For million suns, folded into a dark sphere smaller than the inner solar system. It is not the biggest black hole by a long way, but it is ours, and it has been sitting there at the center of everything we call home since long before the Earth existed. And in 2022, we finally saw its shadow. The same Event Horizon telescope that had imaged the distant giant in M87 turned its planet-sized gaze inward toward the heart of our own galaxy and produced a picture of Sagittarius, a star itself. There it was, the same haunting shape, a ring of glowing gas around a circle of perfect black, 26,000 light-years away, at the center of the wheel of stars we live inside. We had taken a portrait of the monster in our own house. Let that settle for a moment, because it is easy to keep at arm's length, and it should not be. You're not sitting still. The Earth is orbiting the Sun, yes, but the Sun, dragging all of us with it, is orbiting Sagittarius, a star, sweeping around that central black hole once every 230 million years or so, at nearly 200 kilometers a second. You have been falling in a great slow circle around a supermassive black hole your entire life. And so has everyone who has ever lived. The throat at the center of the galaxy is the thing we all quietly revolve around. As unnerving as our own black hole is, it is calm, well-fed, and quiet these days. To see what these things can really do, you have to look far across the universe, and therefore far back in time, to the young cosmos, where some of them were not quiet at all. In the early universe, many supermassive black holes were feeding voraciously, and when one of these giants feeds, it does not do so in darkness. It becomes the single brightest kind of object in all of creation. We call them quasars. A quasar is a supermassive black hole in the act of gorging. As enormous amounts of gas spiral inward toward the event horizon, they pile up into a swirling disk, and friction and gravity heat that disk to millions of degrees. Before the matter vanishes over the edge, it blazes, pouring out light across the whole spectrum with unbelievable intensity. The black hole itself emits nothing, but the doomed matter, screaming its way down into it, shines brighter than anything else in the universe. It is the glow of destruction, the light of things falling to their end. The brightness is almost impossible to overstate. A single quasar, a single feeding black hole, can outshine its entire host galaxy, all 100 billion of its stars combined, by a factor of 100 or more. Some quasars are so luminous we can see them from the very edge of the observable universe, across nearly the whole span of cosmic time. They are among the most distant objects we know, tiny points of light that turn out to be the most violent engines in existence, each one a black hole tearing apart a galaxy's worth of gas and lighting up the cosmos as it does. And because their light has taken so long to reach us, every quasar we see is a window into the deep past. The quasars blaze in the young universe, billions of years ago, when galaxies were forming and gas was plentiful and the central black holes were still ravenous. When we look at them, we are watching the childhood of galaxies, a time when the monsters at their centers were still growing at a furious rate. It raises a question that keeps astronomers up at night. How did these things get so big, so fast, so early? Because get big they did, and the largest known black holes are on a scale that makes even the word supermassive feel inadequate. Consider one with the unglamorous name TON 618. It is a black hole so vast that it holds roughly 66 billion times the mass of our Sun. Not 4 million, like ours. 66 billion. It is one of the most massive single objects ever discovered anywhere in the universe. A black hole heavier than many entire small galaxies, sitting alone and feeding in the distant dark. The size of a thing like that breaks the mind the way the singularity did, but in the opposite direction, by being too large rather than too small. The event horizon of TON 618 is not the size of a star or of a solar system. It is estimated to be well over 1,000 times the distance from the Earth to the Sun across, larger than our entire planetary system by a wide margin. Light itself would take weeks to cross it. You could pour our whole solar system, and thousands more like it, through that horizon, and it would swallow every one without a ripple. So here's the picture we're left with, and it inverts everything comforting about the night sky. We tend to think of a galaxy as an island of stars, a great glowing city of light. But at the center of that city, in nearly every case, is one of these devourers, and the entire city is arranged around it, orbiting it, held in its grip. The black hole is not a stranger lurking at the edge of the galaxy. It is the anchor at its very heart, the thing the whole structure was built around and continues to turn upon. And they grew up together, the galaxy and its black hole, which is stranger still. Astronomers have found a tight relationship between the mass of a galaxy's central black hole and the properties of the galaxy itself. A link so consistent it cannot be coincidence. The two are bound together, feeding and shaping each other over billions of years. The black hole is not a parasite that moved in later. It is woven into the life story of the galaxy from the very beginning, as fundamental to it as the stars. To have a galaxy at all seems to mean having a monster at its core. It changes the meaning of the word home. Every star we have ever named, every world that might harbor life, every place a civilization could arise, sits somewhere in a galaxy, which means every one of them is orbiting a supermassive black hole, held forever in the gravity of an object from which nothing returns. The warm, familiar architecture of the cosmos, the spiral arms, the glowing disks, all of it turns out to be scaffolding around a central abyss. The home of every star, in the end, is a throat. But at least these giants sit still, blazing beacons at the centers of galaxies, exactly where we expect them. There's a far more frightening kind of black hole, and it does not announce itself, and it does not stay put. Scattered through the dark between the stars, invisible, silent, and utterly undetectable unless they happen to be feeding, are the wandering ones. Black holes drifting alone through interstellar space, and you would never know one was near until it was far too late to matter. Somewhere in the galaxy, right now, black holes are drifting between the stars in total darkness. Not at the centers of galaxies, where we know to look. Not locked in orbit with a bright companion star that gives them away. Alone, silent, coasting through the empty spaces between the suns, emitting nothing, reflecting nothing, giving no sign at all of where they are. And there is, at present, no reliable way to find one until it is almost on top of you. This is the oldest fear our species has, the thing hunting in the dark, and the universe has built it on a scale we can barely stand to consider. We have been picturing black holes as fixed things, anchored at the hearts of galaxies, or paired with a doomed companion. But most black holes are neither. Every time a massive star dies and collapses, it can leave behind a stellar black hole, a few times the mass of the Sun, folded into a dark sphere a few kilometers across. And these are made all over the galaxy, in every corner where big stars live and die. Most of them are not at any center. They are just out there, in the ordinary dark, scattered through the same space the stars occupy. Worse, many of them are moving. When a massive star explodes as a supernova, the blast is rarely perfectly symmetric, and that lopsided explosion can kick the newborn black hole hard, like the recoil of a gun, flinging it off through the galaxy at high speed. These are sometimes called runaway black holes, and they wander far from where they were born, cutting across the galaxy on long, lonely trajectories, no longer bound to any star or any center. They drift at tens or hundreds of kilometers a second through the same dark that our own sun is sailing through. The thing that makes them so frightening is not their power. A stellar black hole is far less massive than the giants at galactic centers. The thing that makes them frightening is that they are invisible in the most complete sense of the word. A black hole gives off no light of its own, and a black hole with nothing nearby to feed on, no gas, no companion star, has no glowing disk to reveal it either. It is simply a moving patch of nothing, darker than the dark around it, sweeping silently through space, betraying its presence to no telescope we have. How many of these unseen wanderers share the galaxy with us? The estimates are sobering. Our Milky Way is thought to contain something on the order of 100 million stellar black holes, the corpses of all the massive stars that have died across its long history. 100 million of them, and the overwhelming majority are not feeding, not paired, not visible in any way. They are out there in the dark, uncounted and unmapped, and for almost all of them we have absolutely no idea where they are. We have gotten indirect confirmation that this crowd is real from an unexpected source. Since 2015, gravitational wave detectors have been catching black holes merging with each other again and again, all across the sky, far more often than many expected. Every one of those detections is a pair of black holes that were dark and silent right up until the instant they collided. If that many are out there in pairs, colliding often enough for us to hear them regularly, then the number drifting alone, never colliding, never feeding, never making a sound must be enormous. The detectors are quietly telling us the dark is crowded. The detection problem is close to absolute. Think about what it would take to find one. It emits no light. It reflects no light. It is only a few kilometers across, a speck against the immensity of space. Unless it happens to be passing through a cloud of gas, or drifting near a star can steal from, there is nothing at all to see. You could have one crossing the outer solar system and not know, because there would be no glow, no signal, no warning. The only thing it cannot hide is its gravity, and even that only reveals itself in rare, fleeting alignments. It took until 2022 for us to catch a single one, isolated and alone, and even then only by a fluke of geometry. Astronomers were watching a distant star when its light briefly brightened and shifted in a very particular way, as if something massive and invisible had passed directly between us and it, bending the starlight with its gravity like a lens. When they worked out what the unseen object must be, the answer was a lone black hole, several times the mass of the sun, drifting through space about 5,000 light years away. The first confirmed rogue, found only because it happened to cross in front of a star. That technique is called gravitational microlensing, and it is the one thin thread by which we can catch these things. When a massive object passes almost exactly in front of a more distant star, its gravity bends and magnifies the star's light for a little while, a brief brightening that then fades as the object moves on. It is spectacularly rare, requiring near-perfect alignment, and it only works if we happen to be watching the right star at the right instant. It is less a search than a matter of luck. We do not hunt these predators. We occasionally, by accident, notice one has walked past. So imagine, then, what we could not see coming. Suppose one of these wanderers were on a path toward our solar system. It would give no warning. There would be no light, no signal, nothing for our telescopes to catch, until it was extraordinarily close. And it would not even need to strike the Earth to end us. A black hole passing anywhere through the inner solar system would wreck it with gravity alone, flinging the planets out of their orbits, tearing the delicate clockwork of our worlds into chaos. The Earth could be thrown into deep space or into the sun without the black hole ever touching it. I should be fair about the odds because they are genuinely tiny. Space is unfathomably vast and empty. The black holes are few by comparison, and the chance of one passing close to us in any human timescale, or even in the whole remaining lifetime of the Earth, is extraordinarily small. This is not something to lie awake over, but small is not zero, and that is the whole unsettling point of this chapter. The threat is not that it is likely. The threat is that if it ever did happen, we would not see it, could not stop it, and would have no warning at all. And there may be an even stranger population of these things, one that would have been hunting in the dark since almost the beginning of time. In the chaos of the first fraction of a second after the Big Bang, when the infant universe was unimaginably dense, some regions may have been dense enough to collapse directly into black holes, with no star involved at all. These are the primordial black holes, and if they exist, they could come in a vast range of sizes, from smaller than an atom to larger than a star, seeded through the cosmos before the first galaxy ever formed. We have never confirmed one, and they remain hypothetical. But the idea is taken seriously enough that primordial black holes are a leading candidate for one of the deepest mysteries in all of science, the identity of dark matter, the invisible stuff that outweighs everything we can see. It is possible, genuinely possible, that a significant part of the universe is made of ancient black holes, scattered everywhere, dark and silent, left over from the first instant of creation. If so, they would be the ultimate unseen presence, woven into the very structure of the cosmos. Whether primordial or stellar, feeding or starving, the black holes we cannot see touch something the deep part of the human mind understands immediately. Since our ancestors first huddled around fires, we have feared the predator beyond the light, the thing in the dark that watches, that moves, that we cannot see but that can see us. The rogue black hole is that fear made cosmic and made literal. A hunter that emits no light, makes no sound, and reveals itself only in the instant before it is too late. It is the dark itself, given mass and motion. There is no comfort to offer here, so I will not invent one. These wanderers exist. They are out there in their millions. They are effectively undetectable, and they're drifting through the same dark our own small warm world is drifting through. Almost certainly none of them will ever come near us. But the sky, which we like to think of as a fixed and gentle backdrop, is in truth full of silent, moving, invisible traps, and we have mapped almost none of them. We share the galaxy with predators we cannot see. But we have been talking about black holes at their quietest, when they are starving, dark, and still. When one of these things actually feeds, the veil comes off, and the result is some of the most violent behavior in the entire universe. We have watched in real time a black hole reach out across space, catch a living star, and tear it apart like tissue. That is not a theory or a simulation. We have the footage, and it reveals destruction not as a rare catastrophe, but as the ordinary, everyday appetite of the cosmos. In 2019, and on a handful of other occasions, astronomers watched something that ought to be impossible to witness. They saw a black hole catch a star, a whole living star, drag it in, stretch it out, and tear it apart in real time from across the universe. A star, one of the most substantial objects there is, shredded like a wet tissue and swallowed. We did not deduce it or model it. We saw the flash. And once you have seen it, you understand that in this universe, destruction is not an occasional disaster. It is a meal. The event has a clinical name, a tidal disruption event, and it begins with a piece of very bad luck. In the crowded core of a galaxy, near the central supermassive black hole, stars are packed close and orbits are chaotic. Every so often, a star gets nudged onto a path that carries it to near the black hole. It does not need to cross the event horizon to be doomed. Long before it reaches that boundary, The black hole's gravity reaches out and takes hold of it, and the star's death begins while it is still a great distance away. What kills it is the same force that would stretch you into a thread, only now applied to something the size of the sun. The side of the star facing the black hole is pulled far more strongly than the far side. That difference in pull, the tidal force, grows greater than the star's own gravity holding it together. And so the star begins to stretch. It is drawn out, distorted, pulled from a sphere into an egg, and then into a long, thin streamer. The entire star spaghettified, unwound into a ribbon of stellar material tens of millions of kilometers long. Half of that ribbon is flung back out into space at enormous speed. The other half falls inward toward the black hole, and this is where the fireworks begin. The infalling stream of shredded star cannot dive straight in. It swirls around the black hole, piling up into a searing accretion disk, matter grinding against matter, heating to hundreds of thousands of degrees, blazing across the sky. For months, sometimes years, the black hole that was dark and quiet flares to life. Glowing with the light of the star it is digesting. That flare is what we see across hundreds of millions of light years. From a star's point of view, if a star could have one, the end would come with terrible speed. One orbit, it is whole, an ordinary sun going about its business. The next time it swings past the black hole, the tidal forces exceed what holds it together, and in a matter of hours it is unmade, its material strung out into a glowing arc. A structure that took millions of years to form, and might have burned for billions more, is undone in an afternoon by nothing but the geometry of getting too close. There is no explosion, no fight, just a stretching and then a stream. We have now caught dozens of these events, and each one is the recorded death of a star. A galaxy that was ordinary suddenly brightens at its core, flares for a season, and slowly fades, and we know that somewhere in there, a sun with its own planets, perhaps its own quiet possibilities, wandered too close and was eaten. There is something almost obscene about being able to watch it happen. To point an instrument at a distant galaxy and observe, in the light, the exact signature of a star being torn apart and consumed by the darkness at its center. One of the most dramatic came in 2011, and it did something extra. As the black hole shredded the star, it fired a jet of matter and radiation straight out along its axis, at very nearly the speed of light, and by chance that jet was pointed almost directly at Earth. For a while, we were staring down the barrel of a black hole in the act of feeding, watching a beam of energy from a star's destruction aimed right at us from billions of light years away. It could not harm us at that distance, but we were briefly in its sights. And these feasts are not rare exceptions. They are simply the visible, dramatic version of something the universe does constantly, everywhere, all the time. Across the cosmos, supermassive black holes are feeding, quietly or violently, pulling in gas and dust, and the occasional unlucky star, growing as they go. When a black hole feeds steadily, its whole galactic center lights up into what we call an active galactic nucleus, one of the brightest, most energetic phenomena in all of nature, a permanent engine of destruction glowing at the heart of a galaxy. The engine at the core of that light is the accretion disk, and it deserves a moment because it is one of the most powerful machines the universe knows how to build. Matter spiraling toward a black hole does not fall gently. It orbits faster and faster as it descends, rubbing against itself, compressed and heated by unimaginable forces, until the innermost edge is moving at a large fraction of the speed of light and glowing at millions of degrees. A feeding black hole converts matter into energy more efficiently than almost any process in nature, far more efficiently than the fusion that powers the stars. But the most spectacular thing a feeding black hole does is throw some of its meal back. Twisted magnetic fields in the accretion disk can seize a portion of the infalling matter and hurl it outward from the black hole's poles, in two narrow jets, at more than 99% of the speed of light. These are relativistic jets, and they're among the most violent structures in the universe. Beams of matter and energy fired out of the region around a black hole with a focus and a power that dwarfs everything else a galaxy can do. The reach of these jets is difficult to comprehend. The jet fired from the black hole in the galaxy M87, the same one we photographed, extends outward for some 5,000 light years, a straight blue beam longer than the distance between us and thousands of nearby stars, shooting clear out of the galaxy's core. Other jets stretch for hundreds of thousands, even millions of light years, far larger than the galaxies that launch them. A single black hole, a region smaller than our solar system, can fire a beam of energy across a distance that would take light longer to cross than the age of complex life on Earth. When one of these jets happens to point directly at Earth, we call the object a blazer, and we are, in effect, looking straight into the muzzle of a black hole's cannon. The energy that reaches us from such objects can be extraordinary. High-energy radiation and particles flung across the universe from the immediate surroundings of a feeding monster. We are far too distant for any of them to threaten us. But the fact remains that scattered across the sky are black holes with their weapons aimed, by pure chance, in our direction, and we can feel the faint touch of their fire. These jets are so powerful that they do not merely light up the sky. They reshape their galaxies. As a jet plows out through a galaxy, it heats and blows away the very gas that the galaxy needs to form new stars, effectively regulating, even shutting down, the birth of stars across the whole system. The black hole at the center, through its feeding and its jets, reaches out and controls the fate of a galaxy hundreds of thousands of light years across. The devourer is also, strangely, a kind of governor deciding how many stars a galaxy is allowed to make. Step back, and a disturbing picture assembles itself. We often imagine violence in the cosmos as a series of accidents, rare catastrophes interrupting a mostly peaceful order. It is the reverse. Across the universe, at this very moment, black holes are tearing stars apart, swallowing worlds, firing beams across galaxies, and reshaping the structures they live in. This is not the exception. This is the ongoing metabolism of the cosmos. It's normal, everyday functioning. Destruction is not a malfunction of the universe. It is closer to its appetite, running quietly and constantly in every galaxy, including our own. And it makes you look at the calm night sky differently. That serene field of stars is a snapshot, a single frozen instant of scene that is, on longer timescales, unthinkably violent. Galaxies feed. Black holes grow. Stars are consumed. The peacefulness we perceive is only a matter of our own brief lifespans, too short to see the slow carnage playing out above us. Speed the universe up, and the gentle sky becomes a churning, cannibalistic thing, devouring itself in slow motion, endlessly, everywhere. And this cannibalism operates on the largest structures there are. The eating does not stop at stars. Galaxies devour galaxies. The great islands of light themselves collide, merge, and consume one another. And it is happening right now, to us. Our own Milky Way is on a collision course with another great galaxy, one already visible in our night sky. And the two are falling toward each other at over 400,000 kilometers an hour. The crash has, in a real sense, already begun. Everything we have discussed so far has been, in a sense, out there happening to other stars, other worlds, in distant corners of the sky. This one is happening to us. Our galaxy, the entire Milky Way, is falling toward another great galaxy, and that galaxy is falling toward us, and the two are closing at over 400,000 kilometers an hour. They will collide. It is not a possibility or a distant risk. It is a certainty already in motion, and in a real sense the collision has already begun. The other galaxy has a name you may know, Andromeda, and it is the nearest large galaxy to our own. On a very dark night, far from any city, you can actually see it with your naked eye, a faint smudge of light in the constellation that shares its name. That smudge is not a star. It is an entire other galaxy, 1 trillion or so suns, about 2.5 million light years away. It is the most distant thing the unaided human eye can see, and it is coming toward us. We know it is approaching because of the color of its light. When an object moves toward you, the light it emits is shifted slightly toward the blue end of the spectrum, and Andromeda's light is blue shifted. It is bearing down on the Milky Way at roughly 110 kilometers every second, closing the gap between us by that much with every tick of the clock. It has been falling toward us, and we toward it, pulled together by our mutual gravity across the emptiness for billions of years already. Two titans drifting into a slow embrace. The impact is still a long way off, some 4 billion years or so in the future, give or take, and newer measurements have added some uncertainty about the exact timing and geometry. But the broad outcome is not in serious doubt. In a few billion years, the Milky Way and Andromeda will meet, pass through each other, and eventually merge into a single, larger galaxy. The two great spirals that have circled the local universe for eons will become one, and there is no force anywhere that will stop it. You might expect a collision between two galaxies, each holding hundreds of billions of stars, to be the most catastrophic event imaginable. A sky full of suns smashing into one another, worlds shattered by the billion. And it is not. It is almost the opposite, and the reason why is one of the most quietly devastating facts in all of astronomy. When these two galaxies collide, with all their trillion or more stars between them, the number of stars that will actually strike each other is expected to be, essentially, zero. How can two galaxies pass straight through each other and have nothing collide? Because a galaxy is almost entirely empty space. The stars within it are so tiny compared to the distances between them that they're like a few grains of sand scattered across an entire continent. When you slide one such continent through another, the grains almost never meet. The galaxies will merge, their shapes will be torn and rebuilt by gravity, but the individual stars will simply glide past one another through the vast gulfs of nothing that separate them. The collision is real. The crowding is an illusion. What actually changes in the collision is not the stars, but the shapes. As the two galaxies pass through and fall back together over hundreds of millions of years, their gravity distorts them beyond recognition. The elegant spiral arms are pulled into long, streaming tails of stars flung out into space. Great bursts of new star formation flare up as gas clouds are finally shocked into collapse. Over 1 billion years and more, the two galaxies dance separate and fall back together again and again, until at last they settle into a single vast blob of stars, a new galaxy with no spiral arms at all. And anyone alive to see it, if anyone is, would witness the most spectacular sky in the history of our world. Over the millions of years of the approach, Andromeda would swell from a faint smudge into a vast structure spanning the heavens, its glowing disk and spiral arms filling a huge portion of the night sky, brighter and larger with every passing age. There would come a time when two galaxies hung overhead at once, tangled together, their combined light washing out the darkness. A sky of unimaginable grandeur, and a sign that home was being unmade and remade around them. Where we be in all of this? The sun, and whatever is left of the Earth, would most likely be flung by the gravitational chaos onto a wholly new orbit, quite possibly hurled far out into the sparse outskirts of the merged galaxy, or tossed inward toward its center. We would not be destroyed by the collision itself, in all likelihood. We would simply be relocated, our whole solar system picked up and thrown to a different address in a galaxy that no longer looks anything like the one we were born in. Though by then, the sun's own death may already have ended our story. The merged galaxy even has a nickname, half joking, that astronomers use, a blend of the two names, sometimes Milkomeda. It would be a giant elliptical galaxy, a smooth, featureless swarm of aging stars, with none of the beautiful spiral structure that defines the Milky Way today. The great pinwheel we live in, the one whose band arcs across our summer skies, will not last. It is a temporary shape, a phase destined to be torn apart and reassembled into something rounder, dimmer, and older. Even a galaxy is not permanent. And at the hearts of the two galaxies, the two central monsters will find each other. As the galaxies merge, their two supermassive black holes, ours and Andromeda's, will sink toward the center of a new combined galaxy and begin to orbit one another, drawing slowly closer over millions of years, exactly as the pairs of dead stars did in an earlier chapter, but on a scale billions of times greater. Two black holes, each holding millions of suns, spiraling together at the core of a newborn galaxy. In time, those two black holes will meet and merge into one still larger black hole. And when they do, they will send a wave through the fabric of space-time so vast it beggars comparison. A gravitational ripple carrying more energy in an instant than all the stars in both galaxies emit in light. The same kind of tremor we strain to detect from two colliding dead stars, but from two supermassive black holes, a shudder in the ground of reality on a scale we can barely put into words. The merger of galaxies ends, as so much does, in the merger of monsters. If this all sounds like a singular, cataclysmic fate, understand that it is nothing of the kind. It is routine. This is simply how galaxies grow. The Milky Way we live in today is itself the product of countless earlier mergers, built up over billions of years by swallowing smaller galaxies whole. We can still see the evidence, streams of stars threading through the halo of our galaxy. The shredded remains of dwarf galaxies our Milky Way has already eaten. We are, right now, in the middle of digesting several more. Our galaxy is a cannibal, and always has been. Andromeda is the same, grown fat on its own devoured neighbors. And so is every large galaxy in the universe. The great islands of light do not sit serenely apart from one another for all time. They pull, they fall together, they collide, they merge, they consume. What looks on a human timescale like a fixed and eternal arrangement of galaxies is actually a slow, grinding process of assembly and cannibalism, playing out across billions of years, and utterly unstoppable once gravity is set in motion. That is the note this movement ends on, the note of inevitability at the very grandest scale. Even the largest structures in existence, the galaxies themselves, are not safe, not stable, not permanent. They are on collision courses set in motion long ago, falling toward one another across the dark, destined to be torn apart and remade. Nothing holds still. Nothing lasts. And the thing that drives it all, the gravity that pulls galaxy toward galaxy, is the same patient force that has haunted every chapter of this story. But here, at the edge of this collision, something unexpected has slipped into view, hidden inside the reassurance that no stars will hit. To say that two entire galaxies can pass straight through each other and touch nothing is to admit just how staggeringly empty they are. And that emptiness, it turns out, is the real horror waiting in the next movement. Pull back far enough from all this violence, and you find that the true terror of the universe is not what fills it. It is how much of it is nothing at all, and how utterly alone we are inside that nothing. Point at the nearest star to our sun. Not the sun itself, the next one. It is called Proxima Centauri, and it is so far away that the fastest object human beings have ever built, flying without stopping, would take more than 70,000 years to get there. 70,000 years. Longer than our entire species has existed as we know it. And that is the closest star there is. The distance to all the others only climbs from there, into numbers that stop meaning anything. Space is not mostly empty. Space is almost entirely empty, and we live alone in a very small, warm spot. To feel the true size of that gap, you have to shrink it down to something you can hold. Imagine the sun is a single grain of sand sitting on a table in front of you. On that scale, the Earth is a speck of dust you could barely see, circling a few centimeters away. And the nearest star, Proxima Centauri, that next grain of sand, it would not be on the table. It would not be in the room. It would be several kilometers away, another lonely grain across a whole city with nothing but empty air the entire way between. That is what the crowded night sky never quite tells you. When you look up at a field packed with points of light, you are seeing an illusion of closeness. Those stars are staggeringly far apart, separated by gulfs of pure nothing so vast that light itself, moving at 300,000 kilometers every second, takes years to cross even the very smallest of them. The pretty scatter of the heavens hides the truth. Each of those points is a sun, marooned in an ocean of dark, unimaginably distant from every other one. Slow down on that phrase, light year, because we throw it around too casually. A light year is the distance light travels in a single year, and light is absurdly fast. In 1 second, a beam of light could circle the Earth 7.5 times. Let it run at that speed for a whole year, without pause, and the distance it covers is about 9.5 trillion kilometers. Now understand that the nearest star is more than 4 of those away. Over 40 trillion kilometers of nothing, just to reach the closest neighbor we have. We have actually sent something out toward that dark, and its journey tells the whole story. In 1977, we launched Voyager 1, and it has been flying outward ever since, faster than any human object at some 60,000 kilometers an hour. After more than 40 years, it has finally, barely, left the sun's domain and crossed into interstellar space. And yet, if it were aimed at Proxima Centauri, which it is not, it would need around 70,000 more years to arrive. Our fastest, farthest ambassador, after a lifetime of flight, has crossed almost none of the gap to the very nearest star. And here's the part that should unsettle you before we even leave the neighborhood. Our own solar system, the sun and all its planets, is itself mostly emptiness. The distances between the planets are so large that if you shrank the sun to the size of a beach ball, the Earth would be a small marble 100 meters away, and the outer planets would be kilometers off, with nothing but void in between. We call it our solar system, our home, and it is already overwhelmingly nothing. The planets are rare specks in a vast dark hall. The space between the stars is emptier still, emptier than any vacuum we can make on Earth. Out there, in the interstellar medium, matter is so thinly spread that on average you would find only about 1 atom in every cubic centimeter of space, a lone atom drifting in a volume the size of a sugar cube. Compare that to the air you are breathing, with its tens of billions of molecules in that same tiny space. Interstellar space goes beyond empty as humans use the word. It is empty on a level the mind cannot really picture. And that emptiness is not a neutral, comfortable emptiness. It is bitterly, killingly cold, only a few degrees above the absolute zero at which all motion stops. And it is utterly dark, lit by nothing but the distant, indifferent pinpricks of faraway suns. There is no warmth out there between the stars, no shelter, no ground. To be lost in interstellar space would be to hang in a freezing black void so large that the nearest source of heat, our own sun, would be just another cold-looking star among thousands. The dark between the stars is the most hostile place imaginable, and there is more of it than anything else. We touched this in the last chapter, when 2 whole galaxies could pass through each other and nothing would collide, and it bears repeating because it is the key to everything that follows. Our galaxy holds a few 100 billion stars, and it looks, in photographs, dense and luminous and full. It is not. It is a thin scattering of tiny bright specks across an immensity of empty space, more sparse than a handful of dust motes drifting through a cathedral. The Milky Way is not a crowd of suns. It is a near vacuum with a few stars in it. Spread that thinness across the light years, and you begin to grasp the isolation. Between us and Proxima Centauri lie some 40 trillion kilometers of near-perfect nothing, dark, cold, and all but featureless. No landmarks, no way stations, just the faint sleet of cosmic rays and the occasional lost atom, across a distance so great that our brightest signals arrive, their whisper faint, and their light reaches us 4 years after it leaves. That is the moat around our island. Not water, not desert, but light years of empty, freezing dark. It is worth saying plainly what that means for us, because it is easy to soften. We are, for all practical purposes, marooned. The sun and its handful of worlds sit alone in an enormous void, cut off from every other star by distances that no human lifetime, and quite possibly no human technology, will ever cross. Whatever else is out there, whatever wonders or dangers, is separated from us by an emptiness so profound that reaching it may simply not be possible for beings like us. We are an island, and the sea has no far shore we can walk to. This emptiness has a cruel consequence for the dream of ever reaching out. Any message we might send to even the nearest star takes over 4 years to arrive, and any reply another 4 to come back, a conversation with a decade of silence between each word. Reach for a more typical star, hundreds or thousands of light years off, and a single exchange would outlast entire civilizations. The distances do more than isolate us physically. They isolate us in time, stretching any possible contact across spans so long that both speakers would be long dead before a dialogue could finish. There's a specific loneliness in that, different from the earlier fears. An asteroid or a black hole is a thing that could reach us. This is the opposite. This is the fear that nothing can reach us, and we can reach nothing, that we're sealed inside a bubble of warmth adrift in an ocean of cold and dark so wide that it functions as a wall. All the company the universe might hold is on the other side of a distance that may as well be infinite. We are not surrounded by neighbors. We are surrounded by absence. There's a famous photograph taken by that same Voyager spacecraft as it left the solar system, looking back. In it, the Earth is a single pale point, less than a pixel, a tiny mote suspended in a shaft of scattered sunlight, almost lost in the vastness. Everything that has ever happened to our species happened on that speck. Every war, every love, every name you know, and around it, in every direction, stretches an ocean of dark so enormous that the speck is not even a rounding error. That image is the truest portrait of our situation that exists. So this is where the whole character of the fear begins to change. Up to now, the horror has been about violence, about the things the universe can do to you. From here, the horror becomes about emptiness, about how little there actually is, and how much of everything is simply nothing at all. The void between the stars is only the first taste of it. Loneliness, it turns out, is not a mood the cosmos occasionally allows. It is the default condition of the universe, and we are living in the rare exception, a small lit room in an endless dark house. And when you pull back further, past the stars, past even the galaxies, you find that the emptiness runs deeper than mere distance. Because most of the universe is not simply empty. The thing that outweighs every star and world and living creature combined, by more than 5 to 1, is something we cannot see, cannot touch, and cannot name. It fills all of space. It shaped everything, and it is passing through your body right now, silently, as though you were not even there. Here is a fact that took me a long time to actually believe, rather than merely know. Most of the matter in the universe is invisible. Not hidden, not far away, but fundamentally invisible, something that gives off no light, blocks no light, and cannot be seen by any instrument we have ever built. And there is far more of it than everything we can see. All the stars, all the planets, all the gas and dust and people add up to a small minority of the matter in the cosmos. The rest is dark, unknown, and unnamed, and it is passing through your body right now. The first hint came in 1933 from an irascible Swiss astronomer named Fritz Zwicky, who was studying a great cluster of galaxies. He measured how fast the galaxies within it were moving and got an answer that made no sense. They were racing around far too quickly. There was nowhere near enough visible matter in the cluster, not enough stars and galaxies to generate the gravity needed to hold them together at those speeds. By all rights, the cluster should have flown apart long ago. Something unseen was holding it, something with a great deal of mass and no light. He called it dark matter, and was largely ignored for 40 years. The idea could not be ignored forever, and the person who forced the issue was an American astronomer named Vera Rubin. In the 1970s, she was measuring how fast stars orbit within spiral galaxies, expecting a simple pattern. Stars near the bright center should move quickly, and stars out in the sparse edges should move slowly, just as the outer planets orbit the sun more slowly than the inner ones. That is what gravity and the visible matter predicted. That is not at all what she found. What Rubin found, galaxy after galaxy, was that the stars at the outer edges were moving just as fast as the ones near the center. They were not slowing down at all, and that should have been impossible. Moving that fast, the outer stars should have been flung off into space, the whole galaxy unraveling. Instead, they held together, orbiting far too quickly for the amount of visible matter present. The only way to explain it was to conclude that each galaxy is embedded in a vast, invisible cloud of unseen mass, a halo of dark matter, whose gravity keeps the racing stars from flying away. So the galaxies are not really the glowing spirals we see at all. Those bright pinwheels of stars are just the visible core, the luminous part, floating inside a much larger sphere of something invisible that vastly outweighs them. The dark matter is the real structure. The stars are a bright decoration draped on top of it. Everywhere astronomers looked, the same thing appeared. Galaxies, clusters of galaxies, the whole cosmos, all behaving as though they held far more mass than we could see, all shaped and held by an invisible scaffolding we could detect only by its gravity. And when the accounting was finally done, the proportions were humbling. For every kilogram of ordinary matter in the universe, the kind that makes up stars and planets and you, there are roughly 5 kilograms of dark matter. 5 to 1. The stuff we can see, everything we have ever studied, every atom of every element is outweighed more than 5 to 1 by something we cannot see at all. We spent our entire history studying the universe, and it turns out we were only ever looking at the small, bright minority of it. The reason it is invisible comes down to how it interacts, or rather how it does not. Everything we can see, we see because it touches light, it emits light, absorbs it, or reflects it. Dark matter appears to do none of these things. It ignores light completely. Light passes straight through it as if it were not there, and it passes straight through light in return. It seems to feel only gravity, and perhaps one other faint force, and nothing else. It is matter that has opted out of almost every way that things can be perceived, present only in the pull it exerts. Which means it is not somewhere far off. It is here. Dark matter does not clump into planets or stars, because without the ability to shed energy as light, it cannot collapse and settle the way ordinary matter does. Instead, it forms vast diffuse clouds, and our whole galaxy is sitting inside one. That means it is all around us and passing through us constantly. Billions of dark matter particles are very likely streaming through your body every second, through the earth, through everything, without touching a single atom, silent and unfelt, like ghosts for whom our solid world is not even there. You might reasonably ask how we can be so sure of something we cannot see or touch. And the answer is that its gravity leaves fingerprints everywhere. One of the clearest is the way it bends light. A large enough concentration of mass warps the space around it, and light passing by is deflected, so that clumps of dark matter act like great invisible lenses, distorting and magnifying the images of galaxies far behind them. We can map the dark matter by watching how it warps the light of the distant universe, drawing the shape of the invisible from the way it bends the visible. The most convincing evidence of all came from a cosmic collision, a place called the Bullet Cluster, where 2 great clusters of galaxies smashed through each other. The ordinary matter, the hot gas, dragged and piled up in the middle, slowed by the impact. But the gravity, mapped by lensing, did not stay with the gas. It sailed on ahead, carried by two clouds of something invisible that had passed straight through the wreck without slowing, exactly as dark matter should, feeling gravity but not the collision. There, laid out across the sky, was the invisible stuff separated from the visible, caught in the act. And dark matter did more than hold galaxies together. It built them. In the early universe, it was the dark matter with its gravity that first gathered into a vast web of invisible structure, and only then did ordinary matter, the gas that would become stars, fall into those dark clumps and light up. The luminous universe formed inside a scaffolding of the invisible, like frost gathering on an unseen window frame. Every galaxy, including ours, sits where it does because dark matter pulled there first and pulled the ordinary matter in. We are, in a sense, decorations hung on a structure we cannot see. So we are certain it is there. What we do not know, after decades of the most sensitive experiments ever devised, is what it actually is. We have theories, exotic particles with names like WIMPs and axions, and elaborate detectors buried deep underground, shielded from all interference, waiting patiently for a single dark matter particle to bump into an ordinary atom and reveal itself. They have waited for years. So far, nothing. The most abundant matter in the universe remains at the level of what it is made of, a complete blank. We know it is there. We have no idea what it is. Sit with the strangeness of that, because it is one of the most humbling facts in all of science. We have built a magnificent understanding of the universe, its stars and galaxies and forces, and it turns out to describe only a thin sliver of what is actually out there. The great bulk of the matter in existence is a stranger to us, something we cannot see, cannot catch, and cannot name, that outweighs everything familiar by more than 5 to 1 and shapes the entire cosmos with its unseen hand. We are not the main event. We are the visible froth on top of something else. And it changes how you should picture reality itself. We tend to imagine the universe as the thing we see, the glowing web of stars and galaxies. But that luminous universe is like the white caps on a dark ocean, a thin, bright scum riding on the surface of something vast and hidden. The stars, the galaxies, all the light there is are only tracing out the shape of the dark matter underneath, clinging to it, held by it. We live in the small, glowing, comprehensible part of a cosmos that is mostly invisible to us, and always has been. There's an uncanniness to this that goes beyond the earlier fears. It is not that something dangerous is out there in the dark. It is that the dark is most of what is real, and it is fundamentally alien to us, indifferent to light and to us, mingling with our bodies and our world without ever announcing itself. We're made of the rare kind of matter, the exception, the minority stuff. The universe's true majority material is a phantom that fills all of space, passes through us as if we were not here, and does not care in the slightest that we exist. But dark matter is not spread evenly through the cosmos, and neither is anything else. When you map out where all this hidden mass gathers, and where the galaxies cling to it, an astonishing structure appears, the largest structure in all of existence. And its most striking feature is not the parts that are full, it is the parts that are empty. Because in between the great threads of galaxies lie holes in the universe, so enormous that a person standing inside one might believe they were alone in all of creation. There is a hole in the universe about 330 million light years across, and inside it, there is almost nothing at all. Where there should be thousands of galaxies, there are only a handful scattered so thinly across that emptiness that they might as well be alone. It is called the Boötes void, and it is one of the largest known empty spaces in existence. And it is not some freak anomaly. When we finally mapped the universe at the largest scales, we discovered that this is what the cosmos is mostly made of. Not galaxies, holes. For most of history, we could not see this because we could not see far enough. It was only in the last few decades, as telescopes grew powerful enough to measure the distances to millions of galaxies, that astronomers could build a three-dimensional map of the universe, plotting where the galaxies actually sit in the great volume of space. Nobody knew what the map would look like. Many expected the galaxies to be scattered more or less evenly, like grains of sand thrown across a floor. That is not what the map revealed. What it revealed was a structure so vast and so intricate that it stopped people in their tracks. The galaxies are not spread evenly at all. They are arranged into an enormous, delicate, branching network, threads of galaxies strung together across hundreds of millions of light years, meeting at bright, dense knots, spreading out into sheets and walls. It looks uncannily like a web, or the branching of neurons in a brain, or foam on the surface of the sea. Astronomers call it the cosmic web, and it is the largest structure that exists, the grand architecture of the entire universe. Trace the web, and you find galaxies gathered along luminous filaments, like dewdrops strung along a spider's thread. Where the filaments cross, galaxies pile up into massive clusters, the great cities of the cosmos. From these nodes, the threads stretch outward for hundreds of millions of light years, connecting cluster to cluster in a single continuous network that spans the observable universe. Everything, every galaxy, every star, every world sits somewhere on this web, clinging to its threads. It is beautiful in the way that only something almost unbearably large can be. But the threads and the knots are not the real story. The real story is what lies between them, because the cosmic web is mostly not web. In between the bright filaments, filling the overwhelming majority of the volume of the universe, are the voids. Enormous, rounded, nearly empty bubbles of space, tens or hundreds of millions of light years across, containing almost no galaxies at all. The luminous web is thin and stretched, wrapped around vast pockets of nearly perfect nothing. The structure is real, but it is a structure of absence. The proportions are staggering. If you picked a random point somewhere in the universe, the odds are overwhelming that it would fall not on a galaxy, not on a filament, but deep inside one of these voids, surrounded by emptiness in every direction for tens of millions of light years. The voids make up something like the great majority of all the space there is. The galaxies, the stars, all the light are crowded onto the thin surfaces and threads between them. Most of the universe, by volume, is void. The lit parts are the exception. The Boötes void that Holy began with is simply one of the largest and best known of these emptinesses. Discovered in 1981, it is a roughly spherical region, some 330 million light years wide, and within that immense volume, astronomers have found only a few dozen galaxies, where a normal patch of universe that size would hold many thousands. It is not completely empty, but it is empty enough to be genuinely disturbing, a bubble of near nothing large enough to hold our entire local neighborhood of galaxies many times over. There's a line that astronomers sometimes use about the Boötes void, and it has stayed with me. If the Milky Way sat at the center of a void that size, we would not have known other galaxies existed until well into the 20th century. The nearest ones would be so far away, across such a gulf of emptiness, that our telescopes would have shown us only darkness in every direction, and we would have concluded that our galaxy was the whole of creation. There are places in this universe where an intelligent species could arise and reasonably believe itself utterly alone, because within reach it would be. Sit with that thought, because it is one of the loneliest in all of cosmology. Somewhere out there, in the heart of a great void, there may be galaxies for whom the rest of the universe is effectively invisible, so distant and so faint that it never registers. Their sky would be almost empty, a scattering of their own stars, and beyond that, nothing. Whatever beings might live, there would look up into a darkness far deeper than ours and find no evidence that anything else exists at all. The universe is capable of hiding itself from its own inhabitants, simply through the size of its empty spaces. And this reframes the whole idea of cosmic structure in a way that is hard to shake. We speak of the large-scale structure of the universe, the web, the filaments, the great walls of galaxies. But structure implies stuff, arrangement, presence. What we're really mapping when we map the cosmic web is the shape of the emptiness. We are tracing the thin edges of an immense collection of holes, drawing the boundaries between one vast nothing and the next. The structure of the universe is, in the end, mostly a very detailed map of where things are not. And once again, the web is not truly made of the galaxies we see. The filaments follow the dark matter, that invisible majority from the last chapter, which long ago collapsed into this branching network under its own gravity and pulled the glowing galaxies along its threads. The cosmic web is the skeleton of the dark, made faintly visible by the light that clings to it. What we perceive as the grand structure of everything is really the luminous residue, coating an invisible frame, itself strung across an immensity of void. And the seeds of this entire structure were unimaginably small. The whole cosmic web, every filament and wall and void, grew from tiny ripples in the density of the infant universe, quantum fluctuations blown up to cosmic size in the first instant of the Big Bang. Where the early universe was a hair denser, gravity pulled in more matter over billions of years, building the filaments. Where it was a hair thinner, matter drained away, leaving the voids. The largest structures in existence are the grown-up shadows of the smallest ripples imaginable, stretched across the sky over the entire age of time. The largest single structures we have found within this web-stream belief. There are so-called great walls, sheets of thousands of galaxies stretching across the cosmos. One of them, the Hercules Corona Borealis Great Wall, may extend for around 10 billion light-years, a structure so vast that light would need much of the age of the universe to cross it. These are the biggest things that exist, and between them, and around them, and through them, still, the voids yawn, immense and dark, holding almost nothing, making up the true bulk of reality. So here is the picture at the grandest scale we can reach, and it is a strange inversion of everything we started with. We began this whole story frightened of the things in the sky, the rocks and stars and black holes. Now we have pulled back so far that the things themselves have almost vanished, dwindled to bright threads and specks lost in an overwhelming emptiness. The dominant feature of the universe, the thing there is by far the most of, is nothing. Pure, dark, cold, immense nothing, with a faint glowing web of matter stretched thinly across it. It should humble the sense of importance we carry about our own existence. Everything we have ever known, the Earth, the Sun, the entire Milky Way, is a single tiny bead on one thread of one small region of this web, adrift on the shore of one of countless voids. We are not at the center of anything. We are not in a crowded or important place. We are a mote of matter clinging to the edge of an ocean of emptiness so large that the mind, honestly, cannot hold it and was never built to. But even out here, adrift on the edge of the void, we are not standing still. Something is pulling us. Our entire galaxy, and all the galaxies near us, are being dragged across this web toward a single region of space at over 2 million kilometers an hour. We can measure the pull precisely. We know the direction, and yet we cannot clearly see what is doing the pulling because it is hidden and it is enormous, and we are falling toward it whether we like it or not. You're not sitting still, not even close. Even after you account for the Earth spinning and orbiting the Sun, and the Sun orbiting the galaxy, there is a leftover motion, and it is enormous. Our entire galaxy, along with every galaxy near us, is being pulled through space toward one particular region of the sky at over 2 million kilometers an hour. Something out there is dragging us, and everything we can see, toward it. We can measure the speed and the direction with great precision. What we cannot do is get a clear look at what it is. We know we are moving because of the oldest light in existence. Filling all of space is the faint afterglow of the Big Bang, a bath of microwave radiation left over from the birth of the universe. And it should look the same in every direction. It is not quite. It looks very slightly warmer in one direction and cooler in the opposite one. And that tiny imbalance is the signature of our own motion. We are rushing toward the warm side, and that rush, measured against the afterglow of creation itself, comes out to more than 600 kilometers every second. When astronomers worked out the direction of that motion, it pointed toward the constellations of Centaurus and Norma in the southern sky, toward a region where the galaxies for a great distance around all seem to be flowing the same way we are, as if pouring toward some vast unseen drain. Whatever is out there, it is not pulling only us. It is pulling everything for hundreds of millions of light years in every direction around it, drawing in a whole enormous region of the universe. They gave it a fittingly ominous name, the Great Attractor. The Great Attractor was uncovered in the 1980s by a team of astronomers who became known, half fondly, as the Seven Sarai. They were studying the motions of galaxies and noticed that a whole region of the sky, including our own galaxy, seemed to be streaming coherently toward one spot, far faster than the general expansion of the universe could explain. It was a bold and controversial claim that some unseen giant was tugging on a vast piece of the cosmos. Decades of work since have only confirmed it. The pull is there. We are in its grip. The Great Attractor is a concentration of mass so immense that its gravity is steering the motion of thousands of galaxies, ours among them. And you would think that something with that kind of pull, dominating a huge swath of the local universe, would be easy to find and study. It is not, because by an almost cruel accident of geometry, the Great Attractor lies almost directly behind the crowded, glowing, dusty disk of our own Milky Way from our point of view. The one direction we most need to see is blocked by the very galaxy we live in. Astronomers call that blocked region the zone of avoidance, because for most of history, that is what the great galaxy surveys had to do with it: avoid it. The dense band of the Milky Way, thick with stars and gas and dust, drowns out and hides whatever lies beyond. And the thing pulling us sits right there, in the worst possible place, veiled behind the light and murk of our own galaxy. We're being dragged toward something that is quite literally obscured from view by the very structure we are riding on. We have not been completely blind. By peering through the murk in wavelengths that pierce the dust, in X-rays and radio and infrared, astronomers have managed to glimpse what hides back there. And they have found, behind the veil, a great crowd of galaxy clusters, a genuine concentration of enormous mass, exactly where the pole points. The Great Attractor is real. It is a vast overdensity of galaxies and dark matter, a deep gravitational valley in the cosmos, and our whole region is sliding down into it. But when they added up its mass, something did not quite fit. The Great Attractor, as huge as it is, did not seem to be quite massive enough to explain all of our motion. So astronomers looked further, straight through and beyond it, and found something larger still. Far past the Great Attractor, around 650 million light years away, sits the Shapley concentration, the largest known collection of galaxies in our part of the universe, a supercluster of superclusters, a staggering pile of mass. It appears that the Great Attractor is only a way station, and that we, in it, are all being drawn toward that even greater mass beyond. To make sense of all this flowing and falling, astronomers redrew the map, and in 2014, they gave our home a new and larger name. They traced the motions of thousands of galaxies to find the full extent of the region that all flows together, all draining toward the same attractor. And they called that vast structure Laniakea. It is a supercluster over 500 million light years across, containing 100,000 galaxies, and the Milky Way sits far out on one of its distant fringes. Laniakea, in Hawaiian, means immeasurable heaven. Our true address is the outskirts of an immeasurable thing sliding inward. There is a map of Loneliest that I find hard to look at without a shiver. It shows the flow lines, thousands of galaxies drawn as streams all bending and pouring toward a single region, like water finding a drain or iron filings around a magnet. And there on one thin outer streamline is a tiny marker for the Milky Way, our entire galaxy reduced to a single flowing point on the far edge of the basin, caught in the current, sliding with everything else toward the deep place at the center that we cannot clearly see. Think about what it means to be unable to see where you're going at the scale of a whole galaxy. Every traveler, every migrating bird, every ship has at least the possibility of glimpsing its destination. We do not. We are moving faster than anything in human experience toward a place that is hidden from us behind our own galaxy and veiled beyond that by sheer distance. We know it is there only by the way it pulls. We are, in the most literal sense, being carried blindfolded toward a bottom we will never be shown. What makes this a fear rather than just a fact is the helplessness woven into it. We did not choose this motion. We cannot alter it. We are being pulled, our whole galaxy and everything in it, toward a destination we can barely perceive at a speed that dwarfs anything human, and there is nothing to be done about it and nowhere to hide from it. It is gravity on the grandest scale, indifferent and irresistible, and we are simply a mote caught in its flow, falling toward a valley in the dark whose bottom we have never seen. I should be honest about how this story likely ends, because it has a twist. We may never actually arrive. The pull of the great attractor and the Shapley concentration is real, and it is drawing us in. But there is another force at work in the universe, one we have not yet discussed, that is pushing everything apart faster and faster, and on the largest scales it appears to be winning. In the end, that expansion may tear the flowing galaxies away from one another before they ever reach the bottom of the valley. We are falling towards something and being pulled away from it at the same time. But set the destination aside, and the fact of the motion remains, and it is its own kind of vertigo. Right now, as you read this, you and everything you have ever known are hurtling through space at over 2 million kilometers an hour, toward a place with a name but no clear face, pulled by a mass we can only partly see, part of a flow of 100,000 galaxies all sliding the same way. You feel none of it. There is no wind, no sensation, no sign. But the motion is real, and it is vast, and it never stops. It is the ultimate version of very old unease, the feeling of being moved by forces you cannot see or control. We like to believe we are still anchored at rest in a stable place. We are not. We are falling, all of us together, through the dark, towards something enormous and hidden. And we have been doing so since long before a species existed, and will continue long after it is gone. The ground was never solid. The stillness was always an illusion. We are, and always have been, in motion toward the unknown. And that other force, the one that may yet tear us away from the great attractor before we ever arrive, is the strangest thing in all of modern cosmology. In 1998, astronomers made a discovery that overturned everything we assumed about the fate of the universe. The expansion of the cosmos, they found, is not slowing down as it should. It is speeding up. Something is pushing all of space apart, harder every moment, and we have named it only to disguise the fact that we have almost no idea what it is. In 1998, two rival teams of astronomers, working separately and expecting the same ordinary answer, discovered something that broke the universe. They set out to measure how quickly the expansion of the cosmos was slowing down. Every reasonable assumption said it must be slowing, dragged on by the gravity of all the matter within it. Instead, both teams found the opposite. The expansion is not slowing at all. It is speeding up. Something is pushing the entire universe apart, faster and faster, and decades later we still cannot say what it is. We just gave it a name: dark energy. To feel the weight of that, you have to go back to a discovery from the 1920s, when the astronomer Edwin Hubble found that the universe is expanding at all. He noticed that nearly every distant galaxy is rushing away from us, and the farther away a galaxy is, the faster it recedes. This was one of the most profound findings in human history. The universe was not static and eternal. It was growing, every galaxy flying apart from every other, which meant that long ago everything had been together in a single hot, dense beginning we now call the Big Bang. It is important to understand what is actually expanding, because it is stranger than it sounds. The galaxies are not flying apart through space, like debris from an explosion moving out into a room. It is space itself that is stretching, growing larger between the galaxies, carrying them apart as it swells. Imagine dots drawn on the surface of a balloon as it inflates. No dot moves across the rubber, yet every dot grows farther from every other, because the surface between them is expanding. That is the universe. The space between things is being created everywhere, all the time. For most of the 20th century, the great question was how this expansion would end, and everyone assumed gravity would be the deciding factor. All the matter in the universe pulls on all the other matter, and that pull should act as a brake, slowing the expansion over time. The only real question was whether gravity was strong enough to halt the expansion entirely and pull everything back together, or whether the cosmos would coast outward forever, slowing but never quite stopping. Nobody seriously expected a third answer. Nobody expected the brake to turn out to be an accelerator. The way to find out was to look deep into the past, and that is what the two teams set out to do. They used a special kind of exploding star, a type of supernova that always detonates with very nearly the same true brightness, which makes it a kind of standard candle. If you know how bright something truly is, and you measure how bright it appears, you can work out exactly how far away it is. By finding these supernovae in very distant galaxies, the teams could measure the expansion of the universe billions of years ago and compare to now. The results stunned everyone, including the people who found it. The distant supernovae were fainter than they should have been. They were farther away than the expected amount of slowing would allow. The only way to explain it was that the expansion of the universe had not been slowing down over the billions of years since that light was emitted. It had been speeding up. The galaxies are flying apart faster now than they were in the past, and faster still tomorrow. The cosmos is not coasting to a gentle stop. It is coming apart at an accelerating rate. What made the discovery impossible to dismiss was that two independent teams, using different galaxies and slightly different methods, and in one case actively hoping to prove the other wrong, arrived at exactly the same impossible conclusion. The universe is accelerating. The finding was so solid and so revolutionary that it earned the Nobel Prize, and it forced physicists to accept that the vast majority of the universe is made of something entirely unknown, a mysterious energy woven into space itself, pushing outward against all the gravity there is and winning. They called it dark energy, and the name is a confession. It is dark because we cannot see it, and it is energy because it seems to be a property of space that carries a kind of pressure, a push. But beyond that, we are guessing. When we add up how much of it there must be to drive the acceleration we observe, the number is staggering. Dark energy appears to make up something like 68% of everything in the universe, more than dark matter and ordinary matter combined. The dominant ingredient of reality is a force we named yesterday and do not understand. The leading guess is both elegant and deeply unsettling. It may be that empty space is not truly empty, that the vacuum itself, the pure nothing between the galaxies, contains a faint intrinsic energy, a pressure built into space as a basic feature of existence. If that is true, then every cubic meter of vacuum pushes gently outward. And here is the terrible part. The more space there is, the more of this energy there is, and so the harder the push becomes. As the universe expands, it creates more empty space, which creates more dark energy, which accelerates the expansion, which creates still more space. And yet when physicists try to calculate how much energy empty space should contain, using our best theory of the quantum vacuum, they get an answer that is wrong by a factor so absurd it is almost funny. The prediction misses the measure value by up to 120 orders of magnitude, a 1 followed by 120 zeros. It is often called the worst prediction in the history of physics. So we know dark energy is there, we can measure its effect on the entire universe with precision, and our deepest theory of what it might be is off by the largest margin of error ever recorded. That runaway loop means the acceleration feeds on itself. In the deep past, when a universe was small and dense, the gravity of all its matter dominated, and the expansion did slow. But as space expanded and matter thinned out, a crossover came a few billion years ago when dark energy overtook gravity and took control. From that moment on, the fate of the universe was sealed. Dark energy will only grow more dominant, the expansion only faster forever. We happen to be living right around the turning point, watching the accelerator take over from the brake. There is a lovely, humbling twist buried in the history of this. Decades earlier, Einstein had put a term very much like dark energy into his own equations, a cosmological constant, a pressure in empty space, in order to keep the universe from collapsing. When Hubble showed the universe was expanding, Einstein threw the term out and reportedly called it his greatest blunder. But the 1998 discovery brought it roaring back. The blunder was real after all. Einstein had glimpsed dark energy by accident, decades before anyone could measure it, and then talked himself out of the truth. Take a step back and feel what this does to the whole story we have been telling. Every chapter so far has assumed a stable stage, a fixed arena of space in which the stars and galaxies play out their violent lives. That assumption is wrong. The stage itself is not fixed. It is expanding, accelerating, being torn wider every second by a force that makes up most of the universe and that we cannot explain. The actors are in motion, and so is the theater itself, growing without limit, pulling the actors apart from one another faster all the time. You will not feel any of this, and neither will the Earth or the solar system, or even our galaxy, at least not for an unthinkably long time. On small scales, gravity still easily wins. The atoms in your body, the Earth around the Sun, the stars bound in the Milky Way, are all held together far too tightly for the gentle push of dark energy to matter. The expansion only asserts itself across the vast, near empty gulfs between galaxies, where there is little gravity to resist it. It is a whisper of a force, locally, but spread across the emptiness of the whole universe. That whisper decides the fate of everything. And that changes the ending of everything. A universe whose expansion is slowing might one day stop, or fall back together, or at least settle. A universe whose expansion is accelerating does none of these things. It comes apart, more and more violently, without end. The galaxies will be carried away from one another faster and faster, until the distances between them grow so vast and grow so quickly that they begin to vanish from each other's skies entirely. The acceleration does more than shape the universe. It dismantles it, and it has already begun. Follow that acceleration far enough into the future, and it leads to one of the most quietly devastating ideas in all of science. Because if the galaxies keep rushing apart faster and faster, then one by one, they will recede beyond the point where their light can ever reach us again. The sky will slowly empty, and the beings who live in that far future will look up into a darkness so complete that they will have no way of ever knowing the universe was once full of light. The cosmos is preparing to erase the evidence of its own past. The universe is in the process of erasing its own history. Because the expansion of space is accelerating, the galaxies are being carried away from one another faster and faster, and this leads to a conclusion that is genuinely one of the saddest in all of science. There will come a time, in the far future, when the night sky is empty. When any beings who exist then will look up and see nothing beyond their own galaxy, and we'll have no way, none at all, of ever discovering that the universe was once vast and full of light. The cosmos is forgetting itself, on purpose, forever. Here's how it happens. As dark energy accelerates the expansion, every distant galaxy is receding from us at an ever-increasing speed. The farther away a galaxy is, the faster the space between us grows and the faster it flees. Right now, we can still see billions of galaxies, their ancient light reaching us across the void. But that light is fighting an expanding tide. And as the expansion accelerates, more and more galaxies are being swept up to recession speeds so great that their light can no longer make headway against the growing gulf. This is where a genuinely mind-bending fact enters. Because space itself is expanding, and because there is more and more of it between us and a distant galaxy, that galaxy can effectively recede from us faster than the speed of light. Nothing is moving through space faster than light. That rule holds. But the space in between is growing so fast that the total distance increases faster than light can cross it. And once a galaxy is receding that quickly, the light it emits can never again reach us. It is, from our point of view, gone, cut off, beyond recovery, forever. There's a boundary that marks this point, a cosmic horizon, much like the event horizon of a black hole, but turned inside out. Instead of a boundary you cannot escape from, it is a boundary beyond which nothing can ever reach you. As the expansion accelerates, this horizon draws inward, and galaxies cross it one by one, slipping past the edge of the visible universe. When a galaxy crosses that line, its last light dims and reddens and fades, and then it is simply gone, forever beyond the reach of anything we could ever do or build. In fact, it has already started, in a sense that should stop you. Most of the galaxies we can currently see are, right now, already beyond our reach. The space between us and them is expanding so fast that even light we sent today at the ultimate speed would never arrive. We can still see their ancient light they emitted long ago when they were closer, but they themselves are already gone, unreachable, on the far side of a boundary we can never cross. The emptying of the universe is not a distant event waiting to begin. It is already underway. One by one, over immense spans of time, the galaxies will wink out like this. Not by dying, not by exploding, but by receding beyond the horizon of what can ever be seen. The rich, crowded sky of distant galaxies that our telescopes reveal today will thin and empty as the acceleration carries them all past the edge. The observable universe, the part we can actually see and reach, will shrink down, galaxy by galaxy, until almost nothing is left inside it. The lights are going out, one at a time, and they will not come back on. There is one small mercy, and it is a cold one. The galaxies closest to us, the few dozen that make up our local group, are bound together by gravity tightly enough to resist the expansion. The Milky Way, Andromeda, and their smaller companions will not flee from one another. Instead, as we saw earlier, they will merge over billions of years into a single giant galaxy. So the far future beings will still have that one galaxy, their own merged island of stars. But beyond it, in every direction, there will be only perfect, empty, expanding dark. The timescale for all this is vast, which is the only reason it does not keep more people awake. This emptying of the sky unfolds over roughly 100 billion years and more, far longer than the current age of the universe, which is only about 14 billion. But it is coming as surely as anything in this film. And the beings who might live in that era, whoever or whatever they are, will inherit a universe that looks nothing like ours, a universe that has hidden almost all of itself from them. Picture their sky, a single galaxy, their own, an island of a few trillion stars surrounded by an infinite, featureless black. No other galaxies, no distant smudges of light, just their own stars, and beyond them, nothing in every direction forever. To them, that single galaxy would appear to be the entire universe, a lone lit thing floating in an eternal void. They would have no reason to imagine anything else existed, because from their vantage point, nothing else does. The evidence would all be gone. And this is the truly haunting part. Those future astronomers, doing careful, brilliant science with everything available to them, would reach entirely wrong conclusions about the universe, and they would have no way of knowing they were wrong. They would see a single static galaxy, going nowhere, surrounded by darkness. They would find no other galaxies to reveal that space is expanding. The very evidence that taught us the universe is growing and had a beginning would have receded beyond their horizon long before they arose. It gets worse because the other great clue would also be gone. Today we can see the afterglow of the Big Bang, that faint microwave radiation filling all of space, the single most important piece of evidence that the universe began in a hot, dense state. But that afterglow is being stretched and diluted by the very expansion it reveals. In the far future, it will be redshifted and thinned so severely that it becomes undetectable, faded below any possible measurement. The birth certificate of the universe will have been quietly shredded by time. So the future scientists would look out and find a small, unchanging, lonely universe with no beginning and no expansion, a single eternal galaxy in an empty void. It would be a completely reasonable conclusion, rigorously supported by every observation they could possibly make. And it would be utterly, tragically false. They would be living in a universe that had erased the proof of its own true nature, leaving behind a tidy, misleading story that no amount of intelligence could see through. The cosmos will lie to its last children, and they will have no way to catch it. Scientists have a name for this coming state, and it is a chilling one: cosmic amnesia, a future in which the universe has forgotten how to remember what it was. Not through any catastrophe, not through fire or collapse, but through the simple, patient, unstoppable stretching of space, carrying the evidence away faster than light can bring it back. The knowledge we hold now, the true history of the cosmos, is not permanent. It is a candle in a widening dark, and one day the dark will win and the knowing will be gone. There's a strange responsibility that comes with realizing this. We are living in a privileged moment, cosmically speaking. The universe is old enough for us to have evolved and looked up, and young enough that the evidence of its grandeur and its origin is still visible in our sky. We can still see the other galaxies. We can still detect the afterglow of the beginning. We happen to exist during the brief window when the true story of the cosmos is still readable, before the expansion erases it. In a very real sense, we are among the last who will ever be able to know. That reframes the whole enterprise of knowing and gives it a kind of melancholy urgency. The understanding we have built, the map of the universe and its history, is more than knowledge. It is a memory the universe will not always be able to hold. What we learn now, in this fleeting bright era, is in some sense the universe knowing itself while it still can, before the lights go out and the great forgetting begins. There is grief in that, and there's also something close to duty. We are the cosmos remembering, during the only time remembering is possible. But if we truly are among the rare witnesses able to see the universe as it really is, then a very old and very unsettling question sharpens into focus. We look out at this vast cosmos, billions of galaxies, countless stars, uncountable worlds, and by every reasonable estimate it should be teeming with life, crowded with voices. So we listen. We have been listening for decades. And what comes back is silence. Total, échouing, impossible silence. The universe should be loud. Instead, it is a house that is far too quiet, and no one can explain why. The universe is old almost beyond comprehension, and it is vast beyond that, and it is full of worlds. Our own galaxy alone holds hundreds of billions of stars, and we now know that most of them have planets. By every reasonable calculation, life should have arisen countless times, and some of it should have become intelligent, and some of that should have built civilizations, and some of those should be out there right now, broadcasting, building, spreading. The galaxy should be crowded. It should be loud. So we listen, and there is nothing, just silence. And that silence may be the most frightening fact in this entire film. The problem was captured in a single question, asked almost casually over lunch in 1950 by the physicist Enrico Fermi, one of the sharpest minds of the century. He and some colleagues were talking about the likelihood of alien civilizations, agreeing that the universe should be teeming with them. And Fermi, doing the arithmetic in his head, suddenly asked the question that has haunted the field ever since. If they are out there, they should be, then where is everybody? Why do we see no sign of anyone at all? The force of the question comes from the numbers, so let us actually sit with them. There are a few 100 billion stars in the Milky Way. A large fraction have planets, and a meaningful fraction of those planets sit in the zone where liquid water, and therefore life as we know it, could exist. That is billions of potentially habitable worlds in our galaxy alone. And our galaxy is one of perhaps 2 trillion galaxies in the observable universe. Large does not begin to cover the number of chances for life to arise. It is so large that for life to be unique to Earth would itself be astonishing. There is even an equation for this, written down in 1961 by an astronomer named Frank Drake, that lays out the chain of factors: how many stars form, how many of planets, how many planets bear life, how many develop intelligence, how long such civilizations last. Plug in reasonable numbers, even cautious ones, and the equation tends to spit out a galaxy that should hold many communicating civilizations, sometimes thousands of them, all at once, all broadcasting. The math practically insists we should have neighbors. The sky insists we do not. Somewhere between the equation and the silence lies a truth we have not yet found. And the Milky Way is old. It has existed for over 13 billion years, and there are stars, and therefore possible worlds, far older than our sun, some of them billions of years older. That means that if intelligent life is at all common, some of it should have arisen long before us, with billions of years of head start. Whole civilizations could have risen, matured, and spread across the galaxy while the Earth was still a ball of molten rock. By now, the galaxy has had more than enough time to fill with life many times over. This is the part that turns a curiosity into a genuine paradox. Even at speeds far below that of light, using no physics we do not already understand, a determined civilization could send probes or colonies from star to star, and spreading slowly outward could cross the entire galaxy in something like a few million years. A few million years sounds enormous, but against the age of the galaxy is the blink of an eye. Any civilization with a head start of even a fraction of that time should, by now, be everywhere. The Milky Way should already be settled from end to end. So by rights, we should not have to search hard at all. We should see megastructures around distant stars, or the waste heat of vast civilizations, or probes in our own solar system, or a sky full of deliberate signals. We should have noticed the galaxy was inhabited the moment we built our first good telescopes. The evidence should be obvious, overwhelming, everywhere. Instead, we look out at that enormous, ancient, world-filled cosmos, and we find no structures, no probes, no signals, no ruins, no messages. Nothing that anyone made, nothing that anyone left. It is not for lack of trying. For over 60 years, we have been actively listening, pointing radio telescopes at the stars, scanning millions of frequencies, searching for any signal that carries the fingerprint of intelligence, any hum or pulse or pattern that nature does not make on its own. This is the search we call SETI, the search for extraterrestrial intelligence. Year after year, patient astronomers have swept the sky, comparing the noise from thousands of stars against the hope of a single deliberate whisper. And year after year, the answer has come back the same. Static. Only static. In all those decades of listening, there has been exactly one moment that made the hair on people's necks stand up, and it lasted 72 seconds. On the 15th of August, 1977, A radio telescope in Ohio nicknamed the Big Ear picked up a signal from the direction of the constellation Sagittarius. It was strong, narrow, and startlingly artificial looking, exactly the kind of transmission we have been hoping to find. When the astronomer Jerry Emmons saw it on the printout the next day, he circled the reading in red pen and wrote a single word beside it. Wow. And then nothing. The signal never came again. The Big Ear listened to that same patch of sky over and over for years afterward and never heard another peep. Whatever it was, it flared once for barely over a minute and fell silent forever. To this day, nobody knows what caused it. It might have been some rare natural event, some interference, some accident. Or it might have been the one time in all our listening that we caught the faint edge of a signal from another mind, arriving once and never repeating. We will very likely never know. It remains a single unanswered word, hanging in the dark. Wow. Apart from that lonely maybe, there's been silence. And you have to appreciate how strange, how genuinely wrong, that silence is given everything we know. It is not the quiet of an empty room. It is the quiet of a room that should be packed with people, a great hall built for a crowd, with every reason to be full. And yet when you open the door, there's no one there and no sign that anyone has ever been there, and no sound but your own breathing. The scale of the emptiness is exactly what makes it so unnerving. There are, of course, possible explanations, and they run the full range from comforting to terrifying. Perhaps life is far rarer than the numbers suggest, and the steps from dead chemistry to a thinking creature are so improbable that we truly are alone. Or nearly so. Perhaps intelligent civilizations are common but short-lived, destroying themselves not long after they arise. Perhaps they are out there, but not broadcasting or communicating in ways we cannot detect. Or perhaps, and this is the possibility that chills me most, they are staying silent on purpose because they have learned that being heard is dangerous. Each of those explanations carries its own weight of dread, and we will face the darkest of them in a moment. But step back first and feel the raw shape of the mystery. We live in a universe that appears, by every measure, perfectly capable of producing life, and that has had all the time in the world to do so on a nearly infinite number of worlds. And when we look and listen with everything we have, we find no one. The most reasonable expectation, that we should have company, collides head-on with the most stubborn observation, that we appear to be alone. That collision has a name, the Great Silence, and it is one of the deepest unsolved problems in all of science, because every answer to it is unsettling. If we are alone, then we are a fragile, singular accident in an indifferent cosmos, the only eyes it has, and unbearably precious and unbearably vulnerable. If we're not alone, then the silence means something is keeping everyone else quiet, or killing them, or has already come and gone, and any of those possibilities should worry us far more than being alone ever could. There is a particular human dread in an empty house that should be full. Walk into a home set for a feast, the table laid, the lights on, and find no one there, no host, no guests, no explanation, and the emptiness does not feel peaceful. It feels wrong. It feels like a warning. That is the emotional truth of the Great Silence. The universe is set for life. The conditions are met. The time has passed, and the guests have not come or will not speak, and we are left standing alone in the doorway, calling out and hearing only the echo of our own voice come back. For a long time, most scientists assumed the silence was innocent, a sign that life is simply rare and that we are early or alone. But there's a darker reading, one that has crept out of science fiction and into serious conversation. And once you have heard it, the silence stops sounding empty and starts sounding deliberate. What if the universe is not quiet because it is dead? What if it is quiet because everyone who is out there has learned, the hard way, that the ones who make noise do not survive? Here is a way of reading the silence that I wish I could unlearn. What if the universe is not empty at all? What if it is full of life, full of civilizations, and every single one of them is deliberately, desperately quiet, hiding because they have all arrived at the same terrible conclusion, that the safest thing to do in a cosmos you do not understand is to make no sound at all. That the ones who call out into the dark are the ones who do not survive. This is the dark forest, and is the most chilling answer to the great silence anyone has proposed. The idea was given its sharpest form by the science fiction writer Liu Cixin, but it rests on cold logic that many take seriously. Picture the universe as a vast, dark forest at night. In that forest, every civilization is a hunter moving silently between the trees. Each hunter knows there are others out there, but cannot see them, cannot know where they are or what they intend. There is only the dark and the sound of movement and the knowledge that you are not alone. In such a place, how do you survive? You keep quiet. You do not light a fire. You do not call out. The logic that leads there rests on a few grim assumptions. First, that every civilization wants, above all, to survive. Second, that resources and space, in the end, are finite, so civilizations may eventually compete. And third, and most important, that across the vast distances and long delays between stars, you can never truly know another civilization's intentions, and they can never know yours. You cannot chat it out. By the time a message crosses the light years and a reply returns, centuries or millennia have passed, and either side may have changed beyond recognition, or died, or decided to strike. Now follow the chain of suspicion, because this is where it turns cold. You detect another civilization. You cannot know if they are friendly or hostile. You cannot know if they will grow far more powerful than you. And crucially, you cannot know what they think you might do to them. They face the exact same uncertainty about you. Neither of you can trust the other. Neither of you can verify the other's intentions. And both of you know that the other is running through this very same calculation right now. In that situation, hesitation could be fatal. And so, the dark forest logic concludes, the only safe move, the rational move, is the horrifying one. If you detect another civilization, you destroy it immediately before it can grow, before it can decide to destroy you, before it can even realize you are there. Not out of hatred, out of pure self-preservation, in a universe where you cannot afford to guess wrong. And the corollary is just as grim. If striking first is the safe move for everyone, then the only way to survive is to make absolutely sure no one ever detects you. Stay silent. Stay hidden. Never reveal where you are. In this picture, the silence of a universe is not evidence of emptiness. It is evidence of fear. Every civilization that survived did so by learning to shut up. The ones that broadcast, that announced themselves, that lit a fire in the dark forest to say here we are, were noticed and were eliminated long ago. What we hear as a peaceful quiet is actually the held breath of a galaxy full of hunters, each one crouched in the dark, listening, waiting, and above all, hiding. The silence is not the absence of life. It is the strategy of life. It is only a hypothesis, and it may well be wrong. It rests on assumptions about alien psychology and cosmic scarcity that we cannot test. Maybe civilizations are not so paranoid. Maybe cooperation wins. Maybe the silence has a gentler cause entirely. But the dark forest cannot simply be dismissed because its logic is disturbingly sound, and because it turns our most natural instinct to reach out, to say hello, to find company in the dark, in a possibly the most dangerous thing our species could ever do. And we have already done it. Because we have not been quiet. For over a century, the Earth has been broadcasting, leaking radio and television signals out into space, an expanding bubble of our noise now more than 100 light years wide. And on a few occasions, we have done far worse than leak. We have deliberately aimed powerful transmitters at nearby stars and sent messages announcing our location, our biology, our existence on purpose to whoever might be listening. If the dark forest is real, those broadcasts were not a friendly gesture. They were a child, alone in a dangerous forest, standing up and shouting to see who is there. This is not a fringe worry confined to novels. Serious scientists have argued fiercely about whether humanity should ever deliberately send messages to the stars, and some of the most respected minds of our age have warned, plainly, that it could be a catastrophic mistake. Their reasoning is exactly the dark forest reasoning. We have no idea who is out there or what they are like, and a civilization able to receive our message and cross the stars to reach us would be so far beyond us that we would have no defense at all. Announce yourself to that, they warn, and you may not survive the reply. There's a second framework for thinking about the silence, and it is just as unsettling in a different way. It is called the Great Filter. The idea is simple. Somewhere along the enormous road from lifeless chemistry to a galaxy-spanning civilization, there's a barrier, a filter, that almost nothing gets past. Some step in the process is so improbable or so deadly that it stops nearly every candidate cold. That is why the galaxy is silent. Almost everything that starts down the road is stopped somewhere by the filter. The only question that matters is where the filter lies. And there are only two possibilities, and they could not be more different in what they mean for us. Either the filter is behind us or is ahead of us. If it is behind us, then the hard step, the great improbable barrier, is something we've already passed. Perhaps it was the origin of life itself, or the leap from simple cells to complex ones, or the emergence of intelligence. In that case, we are rare, precious, and possibly among the very first, and the future is open. That is the hopeful reading. It means the worst is already over. But if the filter is ahead of us, the news is very bad indeed. It would mean that the barrier almost nothing survives is not in our past, but in our future, still waiting, some challenge or catastrophe that reliably destroys civilizations once they reach a certain point. Maybe technological societies inevitably destroy themselves. Maybe something out there reliably destroys them. Maybe there's a trap we cannot yet see that everyone before us has walked into. In that case, the silence is not because life is rare. It is because life reliably dies right about where we are now standing. This gives rise to one of the strangest conclusions in all of science, a genuine reversal of what you would expect. Most people assume that discovering alien life would be wonderful news. Under the logic of the Great Filter, it might be the worst news imaginable. Because if we found life everywhere, especially complex life or the ruins of dead civilizations, it would mean the early steps are easy, but the filter is not behind us, which leaves only one place for it to be. Ahead, the more common life turns out to be, the more likely it is that something is killing it, and that the same something is waiting for us. So we are left holding a question we cannot answer, and it may be the most important question our species will ever ask. Is our hardest test behind us or in front of us? Are we survivors of a filter already passed, free to inherit the galaxy? Or are we walking, blind and noisy, toward a barrier that has stopped every civilization that ever came before, a barrier we will not see until we are already inside it? Everything, the whole future of everything we are, hinges on an answer we do not have and may not get until it is far too late. And underneath both the dark forest and the great filter lies the same raw, ancient fear, the one this whole movement has been circling. We are small, we are alone as far as we can tell, and we are surrounded by a silence we do not understand, in a cosmos that is under no obligation to be safe or kind or full. Maybe the quiet means we are precious and rare. Maybe it means we are prey that has not yet been noticed. We cannot tell the difference, and we have been calling out into it for 100 years without knowing which. Whatever the silence means, whether we are alone or hunted or simply early, every possibility shares a single certainty. Nothing out there lasts. The civilizations, if they exist, will end. The stars will burn out. The galaxies will fade. We have spent this movement staring into the emptiness of space. Now we must stare into something deeper and more final. The emptiness of time, the deep future where the universe itself grows old. and dies, and where the true scale of everything we are is measured against an eternity of dark that is only just beginning. Everything, every star you have ever seen, every sunrise, every civilization that has ever risen or fallen, all of recorded history, the whole of life on Earth, the entire age of the universe up to this moment. All of it is a single, brief spark struck at the very beginning of a night that lasts, for all practical purposes, forever. We think of the cosmos as ancient. It is not. It is a newborn. And what lies ahead of it is a span of time so vast that everything that has happened so far will round down completely to nothing. Start with the age of the universe, because even though we tend to get backward, the cosmos is about 13.8 billion years old. That is a genuinely enormous number by human standards, so large that our minds simply file it under very old and stop. But that instinct is exactly wrong. 13 billion years is not old for a universe. It is the first faint flush of dawn. The universe is not in its old age or even its middle age. It is a baby in the very opening moments of a life that will stretch on almost without end. To even discuss what comes next, we have to abandon the way humans normally count time. We cannot use years or millions or billions because the numbers ahead are too large for that. We have to switch to powers of 10, counting not the years themselves, but the number of zeros after the one. And once you start counting that way, something dizzying happens. The entire history of the universe so far, all 13 billion years, occupies the first small stretch of the scale, and then the scale keeps going and going into regions of time so deep that the mind loses its footing entirely. Cosmologists divide this immense future into great eras, like the acts of a play that lasts an eternity, and each act is defined by what kind of thing is still able to exist in it. Right now, we live in the first act, the Age of Starlight. They call it the Stelliferous Era, the Era of Stars, and it is the only cosmic age in which the sky is full of shining suns. It began a few 100 million years after the Big Bang, when the first stars ignited, and it is the age we, and everything we love, happen to inhabit. It feels permanent. It is not. It is the first and shortest act. The Age of Stars will last, in total, something like 100 trillion years. That sounds endless, and by any human measure it is. But hold on to it, because it is the largest of the small numbers in this story, and every era that follows is longer, far longer than this one. We are living near the very beginning of even this first act, barely 13 billion years into a 100 trillion year age of light. Almost all of the Age of Stars still lies ahead. And yet the Age of Stars is the mere flicker at the start of the true history of the universe. There is a genuine scientific puzzle hiding in this, one that some cosmologists find quietly disturbing. If the Age of Stars lasts 100 trillion years, and if life can arise throughout that whole span, then why do we find ourselves here at the very beginning of it, in the first tiny sliver? By rights, a random observer should appear somewhere in the middle of the habitable era, not crammed into its opening moments. Either we are cosmically early for reasons we do not understand, or there's something about these first ages that matters more than we realize. We are, statistically, in a very strange seat. After the stars comes the Age of Corpses. When the last stars finally burn out, the universe enters what is called the Degenerate Era, a long, cold epoch whose only inhabitants are the dead remnants of stars, the white dwarfs, the neutron stars, the black holes we have spent this film discussing. No new stars shine. The light is gone. There are only the slowly cooling embers of what used to be, drifting in an ever-darkening cosmos. And this era does not last for trillions of years. It lasts for a length of time written as a one followed by dozens of zeros. After even the corpses have faded comes the age of the black holes. In this era, so unimaginably far in the future that the previous ones seem sudden by comparison, the only significant objects left in the entire universe are black holes. Everything else has decayed, evaporated, or dispersed. The black holes reign alone across a cosmos of near total darkness, the last great structure standing. And then, slowly, over spans of time that make everything before them look instantaneous. Even they begin to die, bleeding away into nothing through that faint Hawking glow we spoke of long ago. And after the last black hole has evaporated, there is the final act, the one with no end. The Dark Era, a universe of almost perfect emptiness, spread thin and cold beyond all imagining, containing only a scattering of stray particles drifting through an infinite dark, with no stars, no structures, no events, nothing happening, forever. This is not a phase the universe passes through on its way to something else. There is nothing else. The Dark Era is where the story of the cosmos simply stops moving and stays for an eternity that has no upper limit at all. Let me try to give you the scale of these numbers, though I warn you it does not really help because the mind cannot hold them. The age of stars ends around 10 to the 14th year, a 1 with 14 zeros. The age of black holes stretches to something like 10 to the 100th year, a 1 followed by 100 zeros, a number so vast it dwarfs the count of every atom in the observable universe. And beyond that, the Dark Era runs on without limit. Against those spans, the current age of the universe is not even a rounding error. It is indistinguishable from zero. An analogy might help, even if nothing truly can. Imagine the entire life of the universe, from the Big Bang to the last flicker of the last black hole, scaled down so that it fits in the width of a single ordinary room. On that scale, the whole age of stars, the entire era in which any sky anywhere holds a shining sun, would occupy less than the thickness of a single sheet of paper pressed against one wall. And everything that has happened so far, all of cosmic history to this instant, would be a film far thinner than that, invisible to the naked eye. The rest of the room, wall to wall, is dark. This is what deep time actually means, and it is a kind of vertigo all its own. 1 trillion years, a number we can barely write, is early. The universe at 1 trillion years old will still be in its first act, the stars still shining. The real history not yet begun. 10 trillion years is early. 100 trillion is the very end of the age of light, and everything after it, the vast, overwhelming majority of the future, unfolds in darkness. Early does not capture where we sit in the universe's life. We are so early that almost the entire story is yet to come, and almost the entire story is dark. Now set our own existence against that scale, and try not to flinch. All of recorded human history is a few thousand years. Our species is a few 100,000. Complex life on Earth, a few 100 million. The whole age of the universe, so far, 13 billion. And ahead lies an expanse of time so much larger that if you compress the entire future of the cosmos into a single year, everything that has ever happened from the Big Bang until now would occupy less than the first breath of the first second of the first day. We are the opening flicker and nothing more. There is something almost unbearable about that smallness, and something clarifying too. Every fear we have walked through in this film, every asteroid and dying star and devouring black hole, every empire and every life, all of it is crowded into that first infinitesimal flicker at the dawn of time. The universe is not going to be full of stars and warmth for most of its existence. It is going to be dark and cold and empty and dead for almost all of the time there will ever be. We happen to have arrived during the one brief moment when the lights are still on. And that, strangely, is the frame for everything that follows in this final movement. We're going to walk forward now through those coming ages and watch the universe grow old and die, one stage at a time. We will see the last star ever born. We will see matter itself begin to dissolve. We will see the black holes reign and then perish. We will arrive at the cold, final, endless dark. It is a funeral that lasts longer than everything else combined, and we are among the very few who will ever have been alive early enough to see the body while it still breathed. So let us begin the descent into the future where it starts to hurt at the end of the age of light. Because the age of stars, our age, does not end all at once. It fades. The gas that makes new stars runs low, then runs out. The bright, massive stars die young and are not replaced. And eventually, somewhere in the deep future, the very last star of all will ignite, burn for a while, and then go out, and after it, no new star will ever be born again. Somewhere in the unimaginably distant future, a star will be born that has no successor. It will be the last star ever to form in the entire universe. It will ignite and shine for a while in a sky already emptying of light, and then it will die. And after it, no new star will ever be born again, anywhere, for the rest of eternity. There will be a final sunrise, somewhere for someone or for no one. And then the age of starlight, the only age in which skies can shine, will be over forever. To understand why the stars must end, you have to remember where they come from. Stars are born from vast clouds of gas, mostly hydrogen, drifting through galaxies. Where such a cloud grows dense enough, gravity pulls it together, it collapses, heats, and ignites into a new star. This has been happening since the universe was young. Galaxies steadily converting their gas into generation after generation of stars. But there is a catch, and it is a simple, fatal one. The gas is not infinite. Every star that forms uses some of it up, and it is not fully replaced. Each time a star forms and lives and dies, some of its material is locked away forever, trapped in dead remnants, in white dwarfs and neutron stars and black holes that will never give it back, or blown clear out of the galaxy entirely. Slowly, over cosmic time, the raw material for making stars dwindles. The galaxies are burning through their fuel, and although they recycle some of it through the deaths of stars, they cannot recycle all of it. The tank is enormous, but it is finite, and the needle, though we cannot see it move, is falling. Nobody can put an exact date on the last star, but the estimates land somewhere staggering. Star formation is expected to effectively cease within a few trillion years, as the usable gas finally gives out. And the very last red dwarfs, once formed, will keep burning for a good while after that, so that the final stellar light might linger until something like 100 trillion years from now. 100 trillion years. That is when the lights are scheduled, at last, to go out. It is almost incomprehensibly far away, and it is still only the end of the first act. And here's a fact that surprises most people. The great age of starbirth is not in the future. It is already behind us. The universe formed stars most furiously billions of years ago, when it was young and rich with gas, and the rate of star formation has been declining ever since. We live in a long, slow decline after the peak. Most of the stars that will ever exist have already been born. The fireworks are mostly over. We arrived, in cosmic terms, after the height of the celebration, as the lights are beginning, very gradually, to go down. As the gas continues to run low, star formation will keep slowing, and the character of the sky will change. The brilliant, massive, short-lived stars, the ones that blaze blue-white and die young in supernovae, will become rarer and rarer because there is less and less gas to build such extravagant things. The great luminous stars are expensive, and the universe is running out of money. What remains in the end will be the cheapest, smallest, most frugal stars of all, the ones that sip their fuel so slowly they can outlast everything else. The red dwarfs. Red dwarfs are the key to the long ending of the age of light, and they are strange, patient things. They are small, dim stars, far less massive than the sun, burning their hydrogen so slowly and so efficiently that they barely change over enormous spans of time. Where the sun will live for about 10 billion years, a red dwarf can burn steadily for trillions of years, some of them for more than 10 trillion. They are the marathon runners of the cosmos, the last stars that will keep shining long after every brighter star has died. And there is a strange truth about these humble stars. They are not rare. Red dwarfs are, in fact, by far the most common type of star in the universe right now. outnumbering stars like our sun many times over. We simply do not notice them because they are so dim that not one of them is bright enough to see with the naked eye, despite there being hundreds of billions of them in our galaxy alone. The most common star is the one you have never seen, and it is these overlooked, frugal little embers that will inherit the universe and hold the last light long after the grander stars are gone. So the far future of the age of light belongs to them. Picture that sky 100 billion, then a trillion years from now. The bright stars are gone. The galaxies, merged and dimmed, glow a deep sullen red, lit only by these small, cool, long-lived embers spread thin and fading. It is a twilight that lasts for trillions of years, a slow, dim, red evening for the whole universe, growing darker by imperceptible degrees. The age of light does not end in a sudden blackout. It ends in the longest, slowest dusk imaginable. If there is any life at all in that deep future, it will huddle around these last red dwarfs, warming itself at the final fires. And it may be the loneliest life imaginable, clinging to a dim red star in a cosmos where nearly all the other lights have already gone out, in galaxies drifting alone beyond the reach of any other, under a sky emptied by the expansion we spoke of earlier. Whatever thinks its thoughts around the last stars will do so in a universe already mostly dead at the very tail end of the age of light. And even the red dwarfs cannot burn forever. One by one, over trillions of years, they too will exhaust their fuel and fade, cooling from red to darkness, winking out across the emptying galaxies. And at some point, when the last clouds of usable gas are gone and the last small star is formed, there will be a final one, the last star ever to ignite. It will shine, a dim red point in an almost totally dark universe, for perhaps trillions of years of its own. And then it, too, will begin to die. When that final star fades, something happens that has never happened before in the history of the universe. The last light goes out. Not a light, the light. For the first time since a few 100 million years after the Big Bang, there will be no stars shining anywhere in the cosmos, no fusion, no new light being made, nothing to push back the dark. The universe will have entered a night with no morning at the end of it, a darkness that is not waiting for a dawn, because there will never be another dawn. The age of stars will simply be over. And most likely, there will be no one there to witness it. The last star will very probably ignite and burn and die in an empty universe, with no eyes to see it, no mind to mark the moment, the final light in all of existence flickering out unobserved, in silence in the cold. There is a special desolation in that image, a candle guttering in an empty room the size of the cosmos, with the door closing and no one left to notice that it has gone dark at last. Try to feel the weight of that transition, because it is one of the great turning points in the entire life of the cosmos. Everything we associate with the universe, the warmth, the light, the possibility of life clustered around shining suns, all of it belongs to this one early era, the age of stars. It is not the natural, permanent state of a universe. It is a phase, a brief, bright chapter near the beginning. And when the last star dies, that chapter closes and the universe becomes what it will be for almost all of the rest of time, a place of cold and dark and dead things. It reframes the sky above your head into something almost unbearably precious. Right now, tonight, you can walk outside and look up at thousands of stars, at a galaxy still ablaze with hundreds of billions of them, still making new ones. You are living inside the age of light, the one brief window in the whole of eternity when the universe is full of shining suns. Almost every being that could ever exist across the entire future of the cosmos will live in the dark long after the stars are gone. We are among the tiny, fortunate few who got to see them burn. But the death of the last star is not the end of the story. It is barely the beginning of the end, because when the light is gone, the universe still contains the cold corpses of all those dead stars, drifting in the dark, and the dead planets, and whatever else survives. For a long, long time, that dark, degenerate cosmos endures. And then, in the deep cold, something even more disturbing begins to happen. The matter itself, the very atoms that everything is made of, may start to quietly fall apart. Walk with me into the deep future, long after the last star has died. The universe is now a graveyard. It is cold and dark, and scattered across it are the frozen corpses of everything that once shone, the burned-out husks of dead stars, the lightless hulks of dead planets, drifting through an endless black. It is a desolate place and a quiet one, and you might think it could drift on like this, unchanging forever. But it cannot, because in this deep cold, something begins to happen to the matter itself. The very atoms may start to come apart. This epoch has a name, the Degenerate Era, and it stretches from the death of the last star across a span of time, so long it makes the entire age of stars look like a single afternoon. Its name comes from the degenerate matter that makes up the dead stars still lingering in it, but is a fitting word in the ordinary sense too. This is the universe in decline, run down, its energy spent, populated only by the remnants and leftovers of a brighter age that has ended and will never come again. Take an inventory of what is left. There are white dwarfs, the cooling cinders of ordinary stars like our sun, still holding their heat for now. There are neutron stars, the dead crushed cores we met earlier, slowing and cooling. There are black holes, patient and dark. And there are the failed stars and the dead planets, brown dwarfs that never quite ignited, and frozen worlds torn loose from their orbits, wandering alone. Nothing here makes new light. Everything here is an ending, a remainder, an ember. The universe has become a museum of its own dead. The white dwarfs are the ones that mark the passing of time in this era, because they are slowly cooling. When a star like the sun dies, it leaves behind a white dwarf glowing white hot from leftover heat. But with no fuel, it can only radiate that heat away, dimming over billions and then trillions of years, from white to yellow to red to a dull glow, and finally to nothing at all. When it is fully cold and dark, we call it a black dwarf. And here's the strange thing. The universe is not yet old enough for a single black dwarf to exist. Not one has ever formed. Their time is still unthinkably far away. Picture the sky of the degenerate era, if any I remain to see it. There would be no stars, in the sense we mean. At most, scattered here and there, the faint dying glow of a few white dwarfs not yet gone cold, dim red pinpricks in an overwhelming dark, growing fainter with every passing aeon. The galaxies would be black, sprawling collections of dead things, held together by gravity, but giving off almost no light. It is a cosmos lit, if at all, by the last fading warmth of corpses in a night without end. And even those dark galaxies do not hold together forever. Over the vast timescales of this era, the dead stars within a galaxy will slowly, through countless near encounters with one another, redistribute themselves. Some will be flung out entirely, cast into the empty space between galaxies to wander alone. Others will gradually spiral inward and fall into the great black hole at the galactic center, feeding it. Piece by piece, over spans of time that defy the imagination, the galaxies themselves come apart, evaporating into scattered remnants and swelling central black holes. Even the corpses do not get to rest together. The timescales here stop being numbers you can feel and become almost pure abstraction. The degenerate era does not last for billions of years or trillions. It lasts, by some reckonings, from around 10 to the 14th years until 10 to the 40th years and beyond, a span so long that if you wrote it out, the difference between its beginning and its end would swallow the entire prior history of the universe countless times over. Within it, whole processes unfold, galaxies dissolve, remnants cool completely, and matter itself begins to decay, each one taking longer than everything that came before combined. It is tempting to think that this, at least, is stable, that the dead universe could simply coast in its cold darkness forever. nothing left to happen. And for an enormous span of time, that is roughly true. Very little happens. The remnants drift and cool and occasionally interact across timescales so long that 1 trillion years is nothing. But there is one process still only theorized that would eventually reach into even this frozen stillness and take it apart, dissolving the dead stars and the dead planets, and everything else made of ordinary matter into a thin haze of nothing. It is called proton decay. To feel the weight of this, you have to appreciate what a proton is. Protons are among the fundamental building blocks of all ordinary matter, sitting in the nucleus of every atom, in every star and world and living body. And we have always assumed they're essentially eternal, that a proton, once made, lasts forever. Our entire sense of matter as something permanent rests on that assumption. But some of our deepest theories of physics suggest it might not be true. They suggest that a proton, given enough time, can decay, falling apart into lighter particles and radiation, and simply ceasing to be. If protons do decay, they do it with almost unbelievable reluctance. Experiments deep underground, watching enormous tanks of water for the faint flash of even a single proton dying, have found nothing so far, which tells us that if the process happens at all, a proton's average lifetime must be greater than around 10 to the 34th years, a 1 with 34 zeros. That is so long that in the entire history of the universe so far, essentially no protons have decayed. But given the endless stretch of the degenerate era, even a process that's slow becomes eventually unstoppable. And once it takes hold, it changes everything. Over timescales of perhaps 10 to the 40th years, proton decay would begin to eat away at all the ordinary matter left in the universe. The white dwarfs and neutron stars would slowly evaporate, their protons dying one by one, the dead stars quietly dissolving in a faint radiation over unfathomable spans of time. The frozen planets would go the same way. Anything made of ordinary atoms, any remnant, any structure, any possible artifact of any civilization that ever lived would slowly come undone at the most fundamental level, unmade atom by atom. Sit with what that means, because it is the deepest desolation we have reached yet. The horror runs deeper than the light going out or everything dying. It is that the very substance of things, the matter itself, may not be permanent. The atoms in your body, the same ones forged in ancient stars, may not last forever either. Given enough time, in the deep cold of the degenerate era, ordinary matter itself would evaporate away until there were no stars, no planets, no dead remnants, nothing solid left at all, only a thin, cold fog of stray particles and radiation drifting in the dark. There's a particular grief buried in this for anything that ever hoped to last. Every monument, every record, every trace a civilization might leave, no matter how durable, is made of ordinary matter, and ordinary matter is on the clock. Carve your name into the hardest stone, and given enough of the deep future, the atoms of the stone and the atoms of the name will simply cease to be. There is no material permanent enough to outlast this. Nothing you could build would still exist to be found. Oblivion here is total, and it reaches all the way down to the atom. I should be honest that we do not know for certain this will happen. Proton decay is predicted by some theories and not others, and despite decades of watching, we have never actually seen a proton die. It is possible that protons are truly stable, and that ordinary matter is safe from this particular fate. But even if the protons hold, other slow processes would still, over long enough spans, dissolve or disperse the remnants of the old universe. The details are uncertain. The direction is not. Ordinary matter, in one way or another, is running out of time. So the degenerate era ends the way everything in this final movement ends, with a subtraction. The stars were subtracted from the sky. Now the matter is subtracted from existence. What was a graveyard of dead but solid things becomes, over spans of time that make the graveyard itself seem fleeting, a nearly empty void, its old contents dissolved into radiation and drift. The dead stars are gone. The dead planets are gone. The very atoms are mostly gone. And yet, incredibly, even now the universe is not finished emptying, because a few things remain, and they are the most patient and the most terrible of all. When a matter has dissolved and the last remnants have faded, the universe enters an age when only one kind of object is left, the very thing this whole film has circled back to again and again. The black holes. In the deep future, long after the stars and the atoms are gone, the black holes will be the last great structures standing in all of creation, ruling a dark and empty cosmos utterly alone. And then, one by one, over spans of time that dwarf everything we have said so far, even they will begin to die. There will come a time so unimaginably far in the future that the universe will contain only one kind of significant object. Not stars, they died long ago. Not planets or dead remnants, they dissolved into nothing. Only black holes scattered across an almost perfectly empty cosmos, the last great structures left in all of existence. This is the black hole era, and the black holes rule it utterly, alone in the dark. And then, over spans of time that make everything before them seem to happen in an instant, one by one, even they begin to die. By this point, the universe is a place almost beyond description. The stars are a distant memory, gone for an eternity. Ordinary matter has largely evaporated away through proton decay, dissolved into a thin, cold drift of stray particles. The galaxies have long since fallen apart. What remains, holding out against the emptiness, are the black holes, ranging from the small stellar ones a few times the mass of the Sun to the supermassive giants of billions of solar masses that once anchored the hearts of galaxies. They're the last islands of anything in an ocean of nothing. For an enormous stretch of time, the black holes simply endure. In a universe with almost nothing left to feed on, they mostly just sit, patient and dark, holding their captured mass and their frozen light, the last monuments to a cosmos that used to be full. If there were any way to stand and watch, they would seem eternal, the one permanent feature of a dead universe, outlasting the stars, outlasting matter, outlasting everything. But they're not eternal. We learned that long ago from Stephen Hawking, and now, at the end of all things, that lesson comes due. Recall the faint glow we spoke of back at the turning point of this whole story. Black holes are not perfectly black. They very slowly leak energy through Hawking radiation, and in doing so they very slowly lose mass. For a black hole sitting in the warm, busy universe of today, this leakage is utterly negligible, overwhelmed by everything falling in. But in the cold, empty, dead universe of the black hole era, with nothing left to feed them, the black holes have nothing to do but evaporate, dribbling their mass away into the dark, atom of energy by atom of energy, growing imperceptibly smaller. The timescales for this are the longest we have yet encountered, and they break the mind completely. A black hole formed from a single star would take something like 10 to the 67th years to fully evaporate. Not 67 years, 10 to the 67th, a 1 with 67 zeros after it. And the supermassive black holes, the true giants, take vastly longer still, up to 10 to the 100th year and beyond for the very largest. These are the longest lasting objects that will ever exist, and even their reign, measured against eternity, is finite. There's a subtlety that had to wait for the universe to grow cold. A large black hole is actually colder than the faint background warmth of today's universe, which means that right now, the big ones are absorbing more energy from their surroundings than they radiate away and are very slowly growing, not shrinking. They cannot even begin to truly evaporate until the universe around them has cooled below their own faint temperature, which happens only in the deep future as expansion drains the last warmth from space. Only in the great cold can the black holes finally start to die. So the black holes die in order, smallest first. The stellar black holes, being lightest, evaporate soonest, winking out across the dead cosmos over those unthinkable spans. The larger ones follow, and the supermassive ones hold out longest of all, the last great things in the universe, ruling over an emptiness so complete that there's quite literally nothing else left. No matter, no light, no structure, only these few dwindling black holes and the endless dark between them, which by now is very nearly all there is. And here is a detail that gives the death of a black hole a strange, violent poignancy. As a black hole evaporates and shrinks, it does not fade away gently and evenly. The smaller it gets, the faster it radiates, and the faster it radiates, the faster it shrinks, in a runaway that accelerates toward the very end. So a black hole spends almost its entire existence, those unimaginable ages, barely changing, and then, in its final moments, it flares. Its last mass boils away in a sudden burst of radiation, a final flash of energy into the dark, and then it is gone. Think about that flash for a moment, because it may be among the last events of any significance the universe will ever produce. In a cosmos that has been almost perfectly dark and empty and still for spans of time beyond comprehension, the evaporation of a black hole is a rare flicker of something happening, a brief pulse of radiation marking the death of one of the last objects in existence. And these flashes grow rarer and rarer as the black holes die off, until there's only one left. The last one, the biggest one, the final black hole in the universe. Between these rare deaths, the stillness is almost total. We are talking about a universe in which nothing much happens for stretches of time, so long that the interval between one black hole evaporating and the next could itself dwarf the entire prior history of the cosmos. Imagine an emptiness so profound and so patient that a single event, one flash of radiation, might be separated from the next by more time than everything that has ever occurred. That is the texture of the black hole era. Vast, dark, silent waiting, punctuated ever more rarely by the quiet death of a monster. Somewhere out there in the almost infinite future, that last black hole will reach the end of its long evaporation. It will have been the most enduring thing the universe ever made, a supermassive monster that outlasted the stars, outlasted matter, outlasted every other black hole, holding on across a span of something like 10 to the 100th years or more. And then it, too, will shrink to its final moments, flare in one last burst of radiation, and vanish. And with it, the last significant object in the entire universe will be gone. When that final black hole evaporates, the universe crosses a line it will never cross back. Before, there was always something, some structure, some object, some island of matter or energy or gravity holding out against the void. After, there is nothing. No stars, no planets, no atoms, no black holes. Nothing but a thin, cold, ever-thinning soup of stray particles and dying radiation, spreading out into an eternal dark. The last of the great structures is gone, and there will never be another. The universe has finished emptying itself of everything it ever contained. There is a peculiar grief in the death of the black holes, and it took me a while to understand it. All through this film, they have been the villains, the monsters, the most terrifying and irreversible things we know. And here, at the end, we watch even them die, slowly and alone, the last lights in a dead cosmos going out one by one. The devourers themselves are devoured, not by anything larger, but by the simple, patient leaking away of their own being. Even the monsters are mortal. Even the things that eat stars come, in the end, to nothing. And that perhaps is the final lesson of permanence, or the lack of it, in this universe. Nothing lasts. Not the warm worlds, not the shining stars, not the enduring matter they are made of, not even the black holes, which seem for a while like they might be forever. Everything the cosmos builds, it eventually unbuilds. Everything it lights, it eventually darkens. Every structure, no matter how vast or how patient or how terrible, is temporary on a long enough clock. The universe is not a place of permanent things. It is a place where things happen briefly and then stop. It is worth remembering, standing at this imagined end where we are actually speaking from. All of this, the death of the black holes, the emptying of the cosmos, lies ahead by spans of time next to which the current age of the universe is less than an eye blink. We will never see it. Nothing we know will. But we can know that it is coming. And there is something staggering in that a species clinging to a damp rock near one ordinary star in the first faint moments of the universe can look ahead across 100 zeros of years and see, with real confidence, how the whole story ends. So what is left when the last black hole has evaporated and the final flash has faded into the dark? What is the actual ultimate state of the universe, the condition it settles into and stays in, not for a while, but forever? The answer is the most likely true ending of everything, and it is not fire, and it is not collapse. It is a cold, uniform, silent nothing, spread evenly across an infinite dark, in which nothing can ever happen again. It is called the heat death, and it is where all of this has been heading all along. We have watched the stars die, and the matter dissolve, and the black holes evaporate. So what is the final state, the condition the universe settles into and never leaves? It is not a bang. It is not a collapse. It is something quieter, and in its way more horrible than either. It is a cold, uniform, featureless nothing, spread thin across an infinite dark, exactly the same everywhere, at almost absolute zero, in which nothing can ever change and nothing can ever happen again for all of eternity. Scientists call it the heat death. It may be the truest ending there is. By the time the universe reaches this state, everything we have discussed is gone. The last black hole evaporated ages ago. There are no stars, no planets, no atoms, no structures of any kind. What remains is the thinnest imaginable scattering of stray particles and faint radiation, spread out across a space that has expanded to an unthinkable size, drifting in a dark so complete and so cold that the word empty barely does it justice. This is the dark era, the final act, and unlike every act before it, it does not end. It simply is forever. The concept that governs this ending is one of the deepest in all of physics, and it is called entropy. Entropy is roughly a measure of disorder of how spread out and mixed up and evened out the energy in a system has become. And there's a law, the second law of thermodynamics, that may be the most inviolable rule in all of nature. Entropy always increases. In any closed system, over time, things run down, mix together, even out, and grow more disordered. Never the reverse. The universe as a whole is a closed system, and so it too is running down. You see the second law at work every day, though you may not name it. A hot cup of coffee always cools to room temperature, never the reverse. It never spontaneously heats back up by drawing warmth from the cool air. An ice cube melts into a glass of water and mixes evenly through it, but the mixed water never spontaneously separates back into ice and warmth. Order becomes disorder. Differences even out. Heat flows from hot to cold, always, until everything is the same temperature. That one-way slide is the arrow of time itself, and it points relentlessly towards sameness. Now apply that to the entire universe, run all the way forward. Right now, the cosmos is full of differences of gradients, hot stars and cold space, dense matter beside empty void, energy concentrated here and absent there. And it is those differences that make everything happen. Every process, every star, every living thing runs on the flow of energy from a place that has more to a place that has less. But the second law says those differences are always shrinking, always evening out. And when they're finally completely gone, when everything is perfectly mixed and perfectly even, nothing can happen at all. There's a poignant way to think about life in light of all this. Every living thing, including you, is a temporary eddy running against the current, a little pocket of order that sustains itself by borrowing energy and dumping disorder into its surroundings. Life does not break the second law. It rides it, using the flow of energy from the hot sun to the cold sky to build and hold its order for a while. But the current always wins in the end. Everything smooths out. We are beautiful, brief exceptions, and the heat death is the rule finally catching up with all of us at once. That is the heat death, not a universe that is hot, despite the name, but a universe that has reached perfect thermodynamic equilibrium, where every part is at the same temperature as every other part, where there are no gradients, no differences, no concentrations of energy anywhere. It is called maximum entropy, the state of total, final, irreversible disorder. And in that state, although there may still be energy in the universe, there is no usable energy left, because energy can only do work when it can flow from more to less, and now there's no more and no less. It is all just the same. This is why nothing can ever happen again, and it is a subtle, devastating point worth being clear about. A star shines because its hot core differs from cold space. A living thing lives by feeding on energy gradients, eating, breathing, using differences to do the work of staying alive. A thought happens because signals flow. Every event, everywhere in all of history, has depended on some difference, some imbalance that could even out and release energy in the process. In the heat death, there are no imbalances left. And so there's no work, no process, no event, no change. Ever. And with change gone, something even stranger happens. Time itself, in any meaningful sense, ends. Not because clocks stop, but because time only has a direction, a difference between before and after, because entropy increases. Before is the state with lower entropy. After is the state with higher entropy. That is what makes time flow one way. But at maximum entropy, there is no more increase to be had. Every moment is identical to every other. There is no before and no after, because nothing distinguishes one instant from the next. Time, in the heat death, does not stop so much as become meaningless. Try to picture it, though the picture is almost the absence of one. An infinite, expanding darkness colder than anything, thinning toward absolute zero. A few last particles, unimaginably far apart, drifting without purpose or destination. No light, no heat in any useful sense, no structure, no events, no change, no difference between one place and another, or one moment and the next. Just an endless, uniform, silent nothing going on and on and on, with nothing to mark the passing of a time that no longer really passes. That is the most likely final state of everything that exists. And this is a different kind of horror than the film has offered before, because there is no violence in it at all. The heat death is not a catastrophe. Nothing is destroyed in a blaze or a collapse. It is gentler than that, and worse. It is the universe simply, quietly, running down like a clock whose spring has finally unwound completely, coming to rest in a stillness so total that stillness is all there is. Not an ending with a scream, but an ending with a sigh, fading into a silence that never, ever breaks. There is no suffering in the heat death, which is perhaps its one mercy, and also part of what makes it so bleak. By the time it arrives, there is nothing left to suffer, no life, no minds, no anything. It is not an eternity of pain. It is an eternity of absolute nothing, of a universe that has become perfectly, permanently featureless, and will remain so, unchanged and unchanging, not for 1 trillion years or 1 trillion, but literally forever, with no possibility ever again of anything else. Nothingness, not as a moment, but as a permanent condition of reality. And forever, here, means something the mind cannot approach. Not the longest timescales we have already strained to imagine, the tens and hundreds of zeros. Those were merely the road to the heat death. The heat death itself has no end at all. It is not a very long time. It is all the time there will ever be, endlessly, with nothing in it. Every span we have discussed in this entire film, the age of stars, the age of black holes, all of it is a vanishing flicker at the very start of an eternity of cold, still, featureless dark that simply never stops. It is worth pausing on how strange it is that this is where the physics points. We began this whole story with things that could kill you in an instant, fire and impact and radiation. And we have arrived at an ending that is the exact opposite of violent. An ending made entirely of absence, of evenness, of the quiet triumph of disorder over every structure the universe ever built. The most likely fate of everything is not to be destroyed, but to be smoothed out, diluted, and even into a cold, uniform nothing from which nothing can ever emerge again. In a way, the heat death is the natural conclusion of every theme in this final movement. The stars ran down, the matter ran out, the black holes bled away. Each was a step in the same direction, toward less structure, less difference, less happening. The heat death is simply the final destination of that long slide, the state where the running down is complete, where entropy has finally won its total victory, and there is nothing left to run down, because everything has already come to rest. It is the universe finished, at last, with the business of being a universe. Now, I have called the heat death the most likely ending, and it is, given what we currently understand. But it is not the only ending on the table. If our assumptions about that mysterious dark energy are wrong, the universe keeps darker options in reserve, and some of them are far faster and far more violent. There's a way for it all to end, not in a slow fade, but in a final, catastrophic tearing apart, in which every galaxy, then every star, then every atom in your body is ripped to pieces. If the slow, cold fade of the heat death feels too gentle for your imagination, do not worry. The universe keeps darker endings in reserve, because everything we just said depends on our assumptions about dark energy, that mysterious force driving the expansion, and we barely understand it. If it behaves a little differently than we think, the ending changes completely and not for the better. One of these alternatives ends not in a slow freeze, but in a violent, total tearing apart, in which every galaxy, every star, and finally every atom in your body is ripped to shreds. Remember what dark energy is, or rather what we think it is. It is the force pushing space apart and pushing harder as the universe grows. In the standard picture, its strength stays constant, and that leads to the heat death, an eternal, accelerating, but survivable expansion that simply dilutes everything into cold nothing over unimaginable time. But we do not actually know that dark energy is constant. It is entirely possible that its strength changes over time. And if it grows stronger, the ending becomes something else entirely, something with a name that captures it perfectly. The Big Rip. In the Big Rip scenario, dark energy is not constant, but increasing, a kind sometimes called phantom energy, and its outward push strengthens without limit as time goes on. The expansion of the universe does more than continue. It accelerates faster and faster, runaway and unbounded, until the rate of expansion races toward infinity in a finite amount of time. And as it climbs toward that point, it begins to overpower everything. First, the empty space between galaxies, then every structure that gravity and the other forces have ever held together, tearing them apart one after another. The Big Rip would unfold as a sequence of tearings, working its way down through every scale of structure, and the order is almost unbearable to follow. First, the great clusters of galaxies are pulled apart, the galaxies within them scattered as the expansion between them overwhelms their mutual gravity. Then, individual galaxies themselves are torn open, their stars flung outward as even the Milky Way can no longer hold itself together. The grand structures go first, ripped into pieces by a space that is expanding faster and faster beneath them. Then it comes for the smaller things, and the pace quickens horribly toward the end. Months before the final moment, the expansion grows strong enough to rip apart individual solar systems, tearing planets away from their stars, flinging worlds into a space that is coming undone. Then, in the last hour, it reaches the planets themselves, pulling them to pieces. The Earth, or whatever worlds exist then, will be torn apart from within, their own material ripped outward as the space inside them expands. Gravity loses. Everything that was ever held together starts to come undone. And in the final instant, it reaches all the way down. The expansion becomes so violent that it overpowers the forces holding atoms together, then the forces binding the particles inside them. Every atom in existence, including every atom in your body, is torn apart. And then, in the very last moment, the expansion tears apart the fabric of space-time itself, ripping reality down to nothing. It is the opposite of the heat death in every way. Not a slow, quiet dilution over an eternity, but a sudden, accelerating, all-consuming shredding of everything, from the largest structures to the smallest, ending in the destruction of space and time. And here's the part that should genuinely unsettle you, more than the heat death did. The Big Rip, if it is real, is not necessarily an unthinkable distance away. Some versions of the theory, depending on how dark energy actually behaves, put the end at something like 20 billion years or so from now. That is far, but it is not the incomprehensible 10 to the 100th years of the heat death. It is only a few times the current age of the universe. In some versions of this ending, the tearing apart of everything is not a remote abstraction. It is almost close. There is a second alternative ending, and it goes the other direction entirely back the way we came. It is called the Big Crunch. Suppose that dark energy weakens over time, or reverses, and that gravity eventually regains the upper hand. Then the expansion of the universe would slow, stop, and turn around. Everything that has been flying apart since the Big Bang would begin, instead, to fall back together. The universe would start to contract slowly at first, then faster, all the galaxies rushing back toward one another across billions of years. The Big Crunch is the Big Bang run in reverse, and it is its own kind of apocalypse. As the universe contracted, everything would grow hotter and denser and more compressed. The galaxies would merge, the space between stars would shrink, the background of the sky would brighten, and then begin to blaze as the whole cosmos heated up. Eventually, the stars themselves would be crushed together, then the atoms, then everything, all of it collapsing down, faster and faster, toward a single, unimaginably hot, unimaginably dense point. The universe would end the way it began, crushed into a singularity. But the Big Crunch carries within it one last, strange possibility, one that is almost hopeful in a cold way. What if when everything collapses back to that single point, it does not simply end there? What if it bounces? What if that ultimate collapse becomes a new Big Bang, and a new universe is born from the ashes of the old, expanding outward, forming new stars and galaxies, perhaps new life, ignorant of everything that came before? This is the idea of a cyclic universe, an endless series of bangs and crunches, universe after universe, each one rising from the grave of the last. It is a seductive idea, the eternal return, the phoenix cosmos rising again and again. But it offers no real comfort, if you look at it honestly. Even if the universe does bounce, everything from the previous cycle is still utterly destroyed in the crunch. Every star, every world, every memory, every trace that anything ever existed, all of it is crushed to nothing in the collapse. A new universe rising afterward would carry nothing of the old one forward. No record, no echo, no continuity. Rebirth here is not survival. It is total annihilation, followed by a stranger's fresh start. So we have, laid out before us, three main ways for everything to end, and they could hardly be more different. The heat death, a slow, cold, eternal fade into featureless nothing. The Big Rip, a violent, accelerating tearing apart of every structure down to the atom. The Big Crunch, a fiery collapse back into a single point, perhaps to bounce, perhaps not. Current evidence favors the heat death, but dark energy remains such a mystery that we cannot rule the others out. Whatever it is, it holds the fate of everything, and we do not understand it. Which of these awaits us is not a question of philosophy, but of measurement, and we are slowly trying to measure it. Enormous surveys are mapping millions of galaxies and ancient supernovae, trying to pin down, with ever greater precision, whether dark energy is truly constant or strengthening or weakening. The number they're chasing decides everything, whether we drift into the long freeze, get torn apart in the rip, or collapse in the crunch. It is a strange thing to know that somewhere in that data, still being gathered, is the answer to how the universe ends. We are, quite literally, measuring our way toward our own obituary. And notice what all three have in common, because that is the real point of this chapter. Every single road we can chart, every possible future the physics allows, ends in the same place. An ending. There is no version in any of these scenarios where the universe simply goes on comfortably forever, full of stars and warmth and life. Slow freeze, violent rip, fiery collapse. They differ in style and in speed, but not in outcome. Every path we can see leads to a grave. The only real question the universe leaves open is which kind of grave and how soon. There's a strange dignity in being able to hold all of this at once, to look at the several ways everything ends and simply face them, without flinching and without pretending. We are, as far as we know, the only part of the universe that can do this, that can foresee its own dissolution across every possible timeline and still keep looking. But we're not quite done with the endings, because there is one more, and it is different from all of these. The others come slowly, with warning, across billions or trillions of years. The last one could come tonight. Because there's a possibility, taken seriously by serious physicists, that our universe is not stable at all, that it only appears calm, resting in a state that is not truly the bottom. And if that is so, then at any instant, without any warning, a bubble of true, final reality could appear somewhere in the cosmos and expand outward at the speed of light, rewriting the laws of physics and erasing everything it touches. It may be the purest terror the universe holds, and it may, right now, already be on its way. Everything we have said so far assumes the universe is stable, that the rules of physics are fixed and reliable, the same today as tomorrow, the same here as everywhere. There is a possibility, taken seriously by some of the most careful physicists alive, that this is not true. That our universe only looks stable, that it is actually resting in a state that is not the deepest, most final one, and that at any moment, anywhere, without the slightest warning, it could suddenly drop to that deeper state. And when it does, a bubble of true reality would appear and expand at the speed of light, erasing everything that exists. The idea is called false vacuum decay, and to understand it, you have to let go of the notion that empty space is simply empty. In modern physics, the vacuum, the empty space between things, is not truly nothing. It is a field with a certain energy, and that energy sits at a particular level. We normally assume it sits at the lowest possible level, the true bottom, the most stable state there is. But what if it does not? What if the vacuum of our universe rests not at the true bottom, but in a dip partway down, stable enough to last billions of years, but not truly, permanently stable? Picture a ball resting in a valley on a hillside. It looks settled, at rest, going nowhere. But if there is a deeper valley further down the slope, then the ball is not truly at the bottom. It is only in a local dip, held there by a small ridge, a barrier of rock. Give it a good enough shove over that ridge, and it will roll down into the deeper valley below and settle there instead. Our universe, in this picture, is the ball. The dip it rests in is the false vacuum. And somewhere below us, there may be a deeper valley, a true vacuum, that our universe has simply never fallen into. Yet, in everyday life, a ball stuck in a dip stays stuck, unless something pushes it over the ridge. But the universe runs on quantum physics, and in the quantum world, things do not have to go over barriers. They can go through them. It is called quantum tunneling, and it is real, and it happens all the time on tiny scales. A particle trapped behind a barrier has a small but genuine chance of simply appearing on the other side, without ever having enough energy to climb over. And a false vacuum can do exactly the same thing. It does not need a push. It can simply spontaneously tunnel through the barrier all on its own at any moment. When that happens, it does not happen everywhere at once. It happens at a single point, somewhere in the vast universe, where a tiny region of space spontaneously drops into the true vacuum, the deeper valley. And that tiny region, that seed, is now in a lower energy state than everything around it. So it grows. A bubble of true vacuum forms, and its wall, the boundary between the old reality and the new, races outward in every direction, swallowing more and more space, converting the false vacuum into the true one as it goes. And it expands at nearly the speed of light. Inside that bubble, the laws of physics are different. This is the part that is genuinely hard to hold in your mind. In the true vacuum, the fundamental constants of nature would take different values. The forces that bind atoms together, the masses of particles, the very rules that allow matter to exist, would all be changed. Everything that depends on the current laws of physics, which is to say everything, every atom, every star, every living thing, could not survive the transition. Inside the bubble, the universe as we know it simply cannot exist. The bubble does not burn things or crush them. It rewrites the rules so that they can no longer be. And the wall of that bubble is expanding at almost the speed of light, which leads to the most horrifying feature of the whole idea. You would never see it coming, because the bubble wall travels at nearly the speed of the light that would warn you of it. There is no signal that outruns it, no flash on the horizon, no advance notice of any kind. The bubble would reach you at essentially the same instant as the first possible warning of its existence. One moment, everything is normal. The next, you and everything you have ever known are simply gone, rewritten out of existence before your nerves could even register that anything had changed. There would be no pain, no awareness, no final thought. The transition would sweep through your body faster than a signal could travel between two neurons. You would not experience your own destruction, because destruction implies a before and an after that you could perceive, and there would be no time for either. It is the cleanest, most total annihilation imaginable. Not death, exactly, because death is a process. This is more like never having been, applied instantaneously to everything, a silent edit to reality that removes you and your entire universe without leaving even the memory of Scream. This is not a fringe fantasy. The mathematics of how such a bubble would form and grow was worked out decades ago by serious theoretical physicists. One famous early paper described the aftermath with a dark wit that became legendary in the field, noting that inside the bubble of true vacuum, the new laws of physics would be, in its words, incompatible with the existence of anyone to lament the mistake. The people who study this for a living do not treat it as science fiction. They treat it as a genuine, if remote, feature of the reality we live in. For a long time, this was pure speculation, a mathematical curiosity. Then particle physics gave it teeth, and this is where it stops being comfortable. In 2012, we finally discovered the Higgs boson, the particle tied to the field that gives other particles their mass, one of the most fundamental features of reality. And when physicists measured its mass and combined it with the mass of the heaviest known particle, the top quark, and worked out what those numbers imply about the stability of the vacuum, they got an answer that nobody especially wanted. Our universe appears to sit right on the edge. The technical word is metastable, not clearly stable, resting safely at the true bottom, and not clearly unstable, already doomed to decay quickly, but right on the knife's edge between the two. The measurement suggests that the vacuum of our universe may indeed be a false vacuum, a dip partway down the slope, with a deeper valley waiting below, and only a barrier of quantum improbability keeping us from rolling into it. The numbers are uncertain, and there is real debate, and new physics could change the picture entirely. But as things stand, our best measurements hint that reality itself may not be permanently safe. Now, before you lose sleep, there is a crucial reassurance, and it is a real one. If the vacuum is metastable, the barrier keeping us in our current state is enormous, and the chance of tunneling through it in any given moment is fantastically, almost incomprehensibly small. The most likely timescales for such a decay, if it happens at all, are vastly longer than the current age of the universe, so long that the heat death itself might arrive first. On any human timescale, the odds of vacuum decay are effectively zero. You are not going to be erased by a bubble tomorrow. Almost certainly. But almost certainly is not the same as certainly. And here's the thought that gets under the skin. Because the decay can begin anywhere in the universe, and because it spreads at light speed once it starts, it does not have to begin near us to reach us. A bubble could have nucleated billions of light years away, billions of years ago, and be expanding toward us right now, at nearly the speed of light, silent and invisible, and we would have absolutely no way of knowing. It could be halfway here. It could arrive in the next second or in 1 trillion years. There is no way, even in principle, to see it coming. That is what makes false vacuum decay the purest form of cosmic terror. Every other thread in this film gives you something, a warning, a defense, a timescale, a chance, however small. This one gives you nothing. There is no shield against it, no escape from it, no place to hide, and no way to detect it before it arrives. It could be triggered anywhere, at any time, by nothing at all. It would unmake everything, instantly and completely, with no warning and no remainder. It is death for you, for the universe, and for the very laws that made a universe possible. And there is a final, vertiginous twist. If such a bubble ever does form, or has already formed, it would erase all matter and life, and the current laws of physics themselves, replacing them with new ones under which our kind of existence is impossible. It is not merely the end of everything that exists. It is the end of the possibility of things like us existing at all. The bubble does more than kill the players. It burns down the theater, rewrites the script, and ensures that this particular play can never be performed again, anywhere, ever. So that is the purest physical terror the cosmos can offer, a total, instant, unseeable annihilation that could already be on its way. But we are not quite at the bottom of this descent, because there is one more fear, and it is stranger than annihilation. Up to now, every horror has assumed that you, in this moment, and the universe around you, are real. What if that assumption is the shakiest one of all? What if you cannot even be sure that this, right now, is really happening, or that you're really here to experience it? We have reached the strangest fear of all, and it is not about how you might die. It is about whether you were ever really alive to begin with. Here is the problem, and it is a real one, argued in serious scientific papers. In a universe vast enough or old enough, pure random chance should, over enough time, conjure into existence far more disembodied minds briefly hallucinating a life exactly like yours than there are real people actually living such lives. And if that is true, then the odds say you are probably one of those fleeting phantoms. So how, exactly, do you know that you're not? This unsettling idea grows out of the work of a 19th century physicist named Ludwig Boltzmann, who helped us understand entropy and the random motion of particles. The thought that bears his name goes like this. In a universe that lasts long enough, especially one drifting in the near eternal stillness of the heat death, particles are still, very rarely, jostling and fluctuating at random. And given enough time, and the universe has effectively infinite time, even wildly improbable arrangements of particles will occasionally, by sheer chance, assemble themselves out of the chaos. Now, most such random fluctuations produce nothing interesting, a stray clump of gas here, a brief flicker there. But given truly endless time, more elaborate things can fluctuate into being, too. A rock, a planet, and, far more rarely but still inevitably, given infinity, a fully formed, functioning, conscious brain, complete with a full set of memories, thoughts, and the vivid sensation of a life being lived, popping into existence out of the random motion of particles in the void, existing for a single moment, and then falling apart again. This is what physicists, only half joking, call a Boltzmann brain. The horror of it comes from a comparison, which is more likely to be produced by random chance, a single brain, or an entire universe like ours, with its 100 billion galaxies and all their stars and its long, orderly history. Obviously, a single brain. A brain is fantastically complex, yes, but it is unimaginably simpler than a whole cosmos. It requires vastly fewer particles to fall into place by accident. So in a universe that lasts forever and fluctuates at random, lone brains should form far more often than whole-ordered universes, or even in the rare, lucky planets on which real observers slowly evolve. Follow that logic to its end, and it turns on you. If random fluctuations produce far more isolated, momentary brains than real, embodied observers, then the overwhelming majority of all the conscious experiences that ever occur across the whole infinite future of the universe belong not to real people, but to these fleeting phantom minds, flickering into being for an instant in the void, having an experience and vanishing. And each of those minds would feel completely real to itself. It would have memories, a sense of a past, a conviction of being a genuine person in a genuine world. Exactly, precisely like you feel right now. So here's the question that has no comfortable answer. Statistically, if such brains vastly outnumber real observers, then any given conscious experience, including this one, the one you're having as you take in these words, is far more likely to be a random fluctuation than the genuine article. You feel like a real person with a real past, sitting in a real place, watching a real film. But that is exactly what a Boltzmann brain would feel in a single instant of its existence, before it dissolved back into the chaos it came from. You cannot tell the difference from the inside. There's no test you could run. Your memories are no help, and this is the part that really bites. You might think, I know, I am real. I remember my whole life, my childhood, yesterday, a moment ago. But a Boltzmann brain would have all of those memories too, fabricated whole in the instant it formed, indistinguishable from real ones, memories of a past that never actually happened, of a childhood that was never lived, of a yesterday that never was. The sense of continuity you feel, the certainty that you have existed for years and will exist tomorrow, could be an illusion assembled a fraction of a second ago, along with everything else. Physicists do not raise this to torment anyone. They raise it because it is a genuine problem for cosmology. Any theory of the universe that predicts it will produce more Boltzmann brains than real observers is considered, for that very reason, to be probably wrong, because it would make our own observations untrustworthy. The fact that we seem to be real, ordered observers in an ordered universe is actually used as evidence against certain theories. The Boltzmann brain is more than a spooky thought. It is a tool physicists use to check their models, precisely because taking it seriously leads somewhere intolerable. And if the Boltzmann brain comes at this vertigo from the direction of random chance, there's another idea that arrives at almost the same place from the opposite direction through technology. It is the simulation hypothesis, and in recent decades, it has moved from science fiction into serious philosophical argument. The reasoning is disarmingly simple. If it is possible, even in principle, to build computers powerful enough to simulate conscious minds and the worlds they inhabit, then a sufficiently advanced civilization could run such simulations. And if they could, they very likely would, and they would run them in vast numbers. The philosopher Nick Bostrom laid out the argument formally, and its conclusion is hard to escape. If advanced civilizations run many simulations, each containing many simulated minds who believe themselves to be real. Then simulated minds would vastly outnumber the small number of original, biological ones in base reality. And if simulated minds hugely outnumber real ones, then, once again, statistically, any given mind, including yours, is far more likely to be one of the simulated multitude than one of the rare real originals. By the same cold arithmetic as the Boltzmann brain, you are probably not living in base reality at all. There are even people who hunt for evidence, searching for the seams of simulation, subtle limits or glitches in the laws of physics that might betray an underlying computation, a maximum resolution to reality, a cosmic speed limit that looks suspiciously like the refresh rate of some vast processor. So far they have found nothing conclusive, which settles nothing, because a good enough simulation would, by definition, be indistinguishable from the real thing. That is the trap of the idea. Any evidence you found could be part of the simulation, and the absence of evidence is exactly what a perfect simulation would show. It cannot be disproven, and that is precisely why it will not let go. Both ideas, however you feel about their assumptions, converge on the same shattering point. You cannot prove from the inside that your experience is real. Whether the threat comes from random fluctuations conjuring phantom minds, or from advanced computers running countless simulated ones, the result is identical. The reality you take for granted, the solidity of this moment, the certainty that you are a genuine being in a genuine world, rests on nothing you can actually verify. Every test you could imagine running to check would itself be part of the very thing in question. There is no ground beneath your feet that you can confirm is really there. This is the floor finally vanishing completely, which is where this whole descent has been heading since the turning point. We began afraid of things that could kill our bodies. Then we found things that could unmake our world and our universe and the laws of physics themselves. And now, at the very bottom, we find something that threatens the last thing we had left, the bare certainty that we exist at all, that this moment is happening, that you are here to be afraid. Even that, it turns out, is not solid ground. It is an assumption, one we cannot prove, hanging over a void. I want to be careful here because there is a difference between a fear you should act on and a fear you should simply look at. Nothing about these ideas changes how you should live. If you're a simulation or a fluctuation, you have no way to know it and no way to escape it, so it makes no practical difference to anything you do. Your love is still your love. Your morning coffee still tastes like coffee. The vertigo is real, but it is a vertigo of the intellect, not a call to despair. It is simply the discovery that certainty, even about your own existence, was always an assumption you were making without noticing. And yet the doubt does not fully go away, and it should not, because it reveals something true and permanent about our situation. We are minds trapped inside our own experience, with no way to step outside it and check it against reality. Everything we know from within. The universe, the past, other people, our own bodies, all of it reaches us only as experience, and experience, in the end, cannot certify its own truth. We have built this whole terrifying picture of the cosmos on a foundation we cannot, even in principle, prove is real. That is the final unease. Not that the universe will kill us, that we cannot be sure it, or we are even here. And that is the bottom of the descent. We have gone from a rock falling out of the sky to the possibility that the sky, the rock, the falling, and the one who fears it may not be real at all. It would be easy to end there, in that pit of doubt and dread. But there is one more thing to say, and it is the strangest and most important thing in this entire film, because it turns everything we have seen on its head. For all the terror, one impossible fact remains. The universe, for a single brief flicker, arranged itself into something that could look back at all of this and be afraid. For all the terror we had just walked through, here is the strangest fact in this entire film, and it is the one I want to leave you with first. Out of all the dead matter in the universe, all the burning stars and drifting dust and empty dark, some of it, on at least one small world, arranged itself into a shape that could look up at everything else and understand it, and be afraid of it. You're that shape. The universe, for one brief flicker of its long life, has arranged itself into something that can look back at the whole vast, indifferent cosmos and feel dread. That has never been guaranteed. It may be almost unique. Think about what that actually means in the light of everything we have said. We spent this film building a picture of a cosmos that is enormous, violent, cold, and utterly indifferent, a universe that does not know we are here and would not care if it did. All of that is true, but there is one thing that universe cannot do on its own, and did not do for almost all of its history. It cannot notice itself. It cannot know that it is vast, or violent, or beautiful, or doomed. For that, it needed something the dead matter could not provide on its own. It needed a witness, and somehow it grew one. Remember from long ago in this story what you are made of. The iron in your blood, the calcium in your bones, the carbon in every cell, all of it forged in dying stars and scattered by their explosions across billions of years. You are not separate from the cosmos, looking in at it from outside. You're made of it. You are a piece of the universe itself. And that means that when you look up at the night sky and feel wonder or dread or awe, something extraordinary is happening. The universe is looking at itself. The cosmos, through you, has opened its eyes. Consider the odds against you, just for a moment. The precise star had to form and die to make your atoms. The right cloud had to collapse into the right sun, with the right small wet world at the right distance. Life had to begin and survive every catastrophe we cataloged in the early chapters, every impact and extinction for billions of years without a single fatal break in the chain. And then, out of all the creatures that ever lived, awareness had to arise, and language and curiosity, and finally you, in this exact moment, taking this in. The chain of improbabilities behind your existence is longer than the age of the universe, and every link held. For nearly 14 billion years, as far as we can tell, none of this was witnessed. The first stars lived and died with no one to see them. The great galaxies wheeled and collided in silence. Supernovae blazed brighter than 100 billion suns, and no, I registered the light. The universe did all of it, all that violence and beauty and scale, entirely in the dark, unobserved, unknown, unmourned for billions upon billions of years. And then, on a small wet rock circling an ordinary star, matter slowly organized itself into something that could, at last, take notice. And the universe, for the first time, was seen. There's a thread that ties this back to the chapter on cosmic amnesia, on the universe erasing the evidence of its own past. We said then that we are living in the brief window when the true story of the cosmos is still readable, and that in a sense we are the universe remembering itself while it still can. This is the other half of that thought. We are more than the universe's memory. We are its awareness, its single moment of self-knowledge, the one time it gets to understand what it is before the long forgetting sets in. That is not nothing. That may be everything. We do not know how rare this is, and that uncertainty is the whole weight of the earlier chapter on the silence. Maybe awareness is common, scattered across a galaxy full of watchers. Or maybe, as the silence suggests, it is vanishingly rare, and we are among the very few places, or even the only place, where the universe has managed to wake up and look at itself. If that is true, then awareness is not a small thing. It may be the rarest and most precious phenomenon the cosmos has ever produced, more improbable than any star, any black hole, any explosion. A universe that can be understood, understanding itself. And notice the specific, strange thing our kind of awareness can do. We are creatures who live for a few decades, on a planet a few billion years old, and yet we have somehow worked out the age of the entire universe, the life cycles of stars we will never visit, the fate of the cosmos across 100 zeros of years we will never see. A brief, fragile mind, made of stardust, has held the whole scale of deep time inside itself, from the Big Bang to the heat death. There is no guarantee anywhere that the universe should be comprehensible or that anything in it should be able to comprehend. And yet, here and probably it is, and we do. And here is the reframing, the thing that turns this whole descent around without denying a word of it. Every terror in this film is real. The asteroids are real, the dying stars, the black holes, the emptiness, the heat death, all of it, exactly as frightening as we have said. But the capacity to know about them, to feel dread at the scale of a black hole or grief at the death of a last star, that capacity is itself the most remarkable thing in the entire story. The universe is full of things that can destroy you. It contains, as far as we know, only one kind of thing that can comprehend that it will be destroyed. And you are it. There is even a strange kind of tenderness buried in the dread. You do not feel fear at the death of a last star, or grief at the heat death of a universe that will not arrive for 100 trillion years, unless some part of you cares about it, is attached to it, finds it beautiful enough to mourn. The fear we have walked through together is not cold. It is a form of attention, even of love, for a cosmos that cannot love us back. To be afraid for the universe is, in its way, to cherish it. And the universe has nowhere else to be cherished from, except inside minds like yours. There is a peculiar dignity in that, and it does not require any comforting lie. We are small and brief and fragile and almost certainly doomed as individuals, as a species, and eventually along with the whole universe. Nothing in this film has softened that. But we are also the part of the cosmos that gets to know the cosmos, the one small region where the universe has become aware of its own existence, its own history, and its own end. To be able to feel the dread we have felt, walking through all of this, is not a weakness. It is the signature of the single most extraordinary thing the universe has ever done. The question, then, is not really how the universe ends, because we have answered that as well as anyone can. The question is what you do with the flicker, the brief, bright moment of being a conscious part of the cosmos before it closes. That is the one thing in this entire film that is not already determined by physics, not written into the fate of the stars or the expansion of space. How you spend the small, improbable window of your awareness is genuinely, entirely up to you. It is perhaps the only truly open question the universe has left on the table. So the awe and the grief turn out to be the same feeling, held from two sides. The grief is real, that all of this is temporary, that the stars will die and the warmth will fade, and we, the witnesses, will be gone long before the lights go out. But the awe is real too, that for one brief, improbable moment, in one small corner of an enormous and indifferent universe, matter woke up, looked around at the whole staggering scale of everything, and understood. Those two feelings do not cancel. They belong together. They are what it feels like to be the universe, briefly knowing itself. And that is the note I want to carry into the very last of this. Not a reassurance, because there is none to give. Not a resolution, because the universe does not offer one. Just an invitation to step outside tonight and look up and to see the night sky for what it truly is with everything you now know. Because that familiar sky, the one you have looked at 10,000 times without seeing, is not what it appears to be. It is older than you can feel, and much of what you see up there is already gone. So here is where we end, not with an answer, but with an invitation. Tonight, or on the next clear night, step outside and look up. Really look, because that night sky, the one you've seen 10,000 times and stopped noticing, is not what it seems. Some of those stars you're looking at burned out and died long ago. The light is still arriving, but the star that made it is already gone. When you look up at the night, you are not seeing the universe as it is. You're seeing ghosts, and the dark between them is not waiting for anything at all. It comes down to the one fact that has haunted this whole film from the very first chapter. Light takes time to travel. The stars are so far away that their light has been crossing the void for years, for centuries, for thousands of years before reaching your eye. The light from a star 1,000 light years away left it 1,000 years ago, when the world below was a very different place. You're never seeing the star now. You're only ever seeing where it was and how it shone a long, long time ago. And in all those years, all those centuries of travel, anything could have happened to the star itself. It could have swelled into a red giant. It could have exploded as a supernova. It could have collapsed into a black hole, or simply faded and gone dark. The light kept coming faithfully across the light years, long after its source was gone. So scattered across the night sky, mixed in with the living stars, are the ghosts of dead ones, still shining for us by the grace of the long delay. Stars that no longer exist, sending us the last of a light that outlived them. That is what the night sky truly is. Not a fixed ceiling of eternal lights, but a graveyard of ancient light, a scattering of images from across thousands of years, some of them from stars that still burn, some from stars long dead, all of it arriving here now in your eye, layered together into a single sky that does not actually exist in this form anywhere but in your looking. The heavens are a museum of the past, and every point of light in it is a message from a moment that has already ended. Take Betelgeuse, that orange star on the hunter's shoulder we visited long ago. It is around 600 light years away, and it is old, and it is dying. It could go supernova at any time, and given how the light works, it may have already exploded centuries ago, the flash still on its way to us across the dark. When you look at Betelgeuse tonight, you cannot know whether you are seeing a living star or the lingering ghost of one that died while its light was still traveling. That uncertainty, hanging in your own sky, is the truest small emblem of everything we have said. And that sky is old, older than anything you can feel in your body. It was blazing away, indifferent, long before there were eyes to see it, and it will go on, dimming by imperceptible degrees, long after the last human eye has closed. The cosmos we have spent all this time being afraid of does not know we are here. It did not make us on purpose, and it will not mourn us when we are gone. It is vast beyond feeling, patient beyond comprehension, and utterly, serenely indifferent to the small, warm creatures who briefly looked up and were afraid. There is no comfort to offer against that, and I promised at the start that I would not invent any. The universe is not going to reassure you. It is not going to make an exception. Everything we have walked through, the impacts and the dying stars and the black holes and the emptiness and the several ways it all ends, all of it is true and none of it cares. The scale is real. The indifference is real. The ending, in whatever form it takes, is real. This is the universe we actually live in, and it does not soften for being understood. We began this a long time ago now, inside a single ordinary morning, in a city that got no warning, its people cut by their own windows while they stood at the glass to watch a light in the sky. We have traveled a long way from that morning, all the way to the end of time, and the edge of reality and the doubt of our own existence. And the whole journey, every fear in it, has been a way of asking one quiet question. How do you live knowing all of this? There is no answer written in the stars. There is only the question, and you in the sky. And yet, here you are, at the end of all of it, still looking up. A small, warm, temporary thing, made of the ash of dead stars, standing on a rock at the edge of an ordinary galaxy, in the first faint moment of an almost endless night, and you are looking up at a graveyard of ancient light and feeling something. Wonder, maybe. Dread, certainly. But feeling it, which is the one thing all that vast, indifferent cosmos cannot do for itself. In all the dark and all the distance, you are the place where the universe stops being indifferent, just for a moment, just here. So I will not tell you it is all going to be fine, because it is not, and you already know that now. I will only ask you to sit with the scale of it, the way you might sit with any enormous and difficult truth. You are here. The universe is vast and cold and dying slowly, and it made you anyway, an accident of stardust that can look back at the whole terrifying sweep of it and understand. That will not last. Nothing does. But it is happening right now, in you, as you take this in, and that is not nothing. That may be the most that anything ever gets. The dark is not waiting for anything. It never was. It does not want us gone, and it does not want us to stay. It simply is, and it will still be there, long after the last star has faded and the last question has gone unanswered, patient and vast and empty. But tonight, the light is still arriving. The stars, the living and the dead alike, are still shining in your sky. And you are still here to see them, for a little while, in the brief warm flicker before the long dark that everything we have spoken of is quietly, patiently heading toward. So look up, while there is still a sky to look at, and something in you to do the looking. That is the whole of it. That is all any of us ever get. A small window of warmth and awareness, in an enormous and ancient dark, and the strange privilege of being the part of the universe that noticed. What you make of that, in the time you have before the light finishes crossing the distance and the dark finishes its slow, certain arrival, is the one thing left in all of this that was never decided for you.